Hello and welcome back. Tonight we're traveling to the edge of the solar system, to a small, frozen world that has captured human imagination for nearly a century. Before we discovered it, we didn't know it was there, and after we found it, we spent decades trying to understand what it was. A planet? Not quite. A moon? Not that either. Something else entirely? Perhaps. And in that uncertainty, in that refusal to fit neatly into our categories, Pluto became something more interesting than if it had simply been the ninth planet. It became a reminder that the universe doesn't organize itself for our convenience. Before we begin, I'd love to know where you are watching from tonight. And how was your day? Drop a comment below. I always enjoy reading your comments. If you enjoy falling asleep to these videos, please consider subscribing. It helps more people find their way here. Now, let's begin. In 1930, a young man named Clyde Tombaugh discovered Pluto. He was 23 years old and he had no formal training in astronomy. He was a farm boy from Kansas, the kind of person who understood machinery and hard work, who knew how to fix things with whatever happened to be lying around. His first telescope, the one that started everything, wasn't bought from a catalog or inherited from some university observatory. He built it himself from salvaged farm machinery and parts from his father's 1910 Buick. Imagine that for a moment. The gears and mirrors that would eventually lead to discovering a new world in our solar system came from a car that was already 20 years old, sitting in a barn somewhere in Kansas. There's something deeply human about that origin story. Not a wealthy aristocrat with the finest equipment, not an established professor at a prestigious institution. Just a young man with curiosity and determination, using what he had available, looking up at the night sky and wondering what else might be out there. The telescope worked. It worked well enough that the Lowell Observatory in Arizona saw his drawings of Mars and Jupiter and hired him, even without a degree. They put him to work on a specific project, finding Planet X, a hypothetical ninth planet that mathematical predictions suggested might be lurking in the outer solar system. And so Clyde Tombaugh began the work. Patient, methodical, exhausting work that would consume years of his life. He didn't know when he started that he would actually find something. Nobody really knew if Planet X existed at all. But he looked anyway. Night after night, comparing photographic plates of the same patch of sky taken days apart, searching for something that moved against the background stars. Sometimes the most important discoveries come not from the people with the best credentials or the most expensive equipment, but from those who simply refuse to stop looking. And sometimes what you find isn't quite what you were searching for, but it's wonderful anyway. Clyde Tombaugh spent 7,000 hours over 14 years staring through a device called a blink comparator. If you've never heard of one, picture this: a machine that rapidly switches between two photographic plates of the same region of sky, taken on different nights. If something moved, a planet, an asteroid, anything orbiting the sun, it would appear to jump back and forth, flickering in and out of position while the stars remained still. 7,000 hours. Think about that number for a moment. If you worked a standard 40-hour week, that would be more than 3 years of full-time work. But this wasn't spread across 3 years. It was 14 years of Tombaugh's life, hour by hour, session by session, plate by plate. The work was tedious beyond description. Most of the time, nothing moved. Most of the time, it was just stars, thousands and thousands of stars, all staying exactly where they should be. Occasionally, an asteroid would reveal itself, already known and catalogued. Sometimes there were flaws in the plates themselves, tiny imperfections that could look like movement but weren't. And then, on a Tuesday afternoon, February 18th, 1930, at 4 o'clock after lunch, something changed. Tombaugh was comparing plates taken in January, and there it was, a faint speck that popped in and out of view. Not a star, not an asteroid he recognized, something else. He checked it again, measured its position, compared more plates. The speck was moving, slowly, exactly the way a distant planet should move. His heart must have been thundering. After all those hours, all those years, all that patient searching through the darkness, he'd found it. The solar system had just gained its 9th member, though nobody knew it yet. That moment, that Tuesday afternoon in February, was one of those rare instances when the human understanding of our cosmic neighborhood expanded. One person, one machine, one persistent search, and suddenly we lived in a larger universe than we had that morning. And perhaps what makes it even more remarkable is this. Tombaugh didn't stop looking after he found Pluto. He continued his search for years, examining millions more stars, hoping to find another planet. He never did. Pluto was unique, singular, the only world he would ever discover. But what a world it was. The morning after Pluto's discovery was announced, an 11-year-old girl named Venetia Burney sat at breakfast in Oxford, England, reading about it in the Times. Her grandfather, a retired librarian, was reading the same article. Venetia had always been interested in mythology, the old stories of gods and heroes, the names that ancient people gave to the forces they couldn't understand. She'd learned that the planets were named after Roman deities: Mercury the messenger, Venus the goddess of love, Mars the god of war, Jupiter the king of the gods, Saturn the god of time, Uranus the god of the sky, Neptune the god of the sea. This new planet, the article said, hadn't been named yet. It was so far away, so dark, so cold. What would you call a world like that? And Venetia, 11 years old, eating breakfast, said, "Pluto." Her grandfather looked up. Why Pluto? Because Pluto was the Roman god who could make himself invisible, she explained. The god who ruled the underworld, the hidden realm beneath the earth where sunlight never reached. And this new planet was so distant, so dark, hiding in the outer reaches of the solar system where the sun's light barely touches. It seemed fitting. Her grandfather, charmed by this, thought it was perfect. He sent a telegram to the Lowell Observatory in Arizona, suggesting the name. The astronomers there agreed. It honored the Roman tradition of planetary names. It evoked the darkness and distance of this remote world. And, though this was just a happy coincidence, the first two letters, P and L, matched the initials of Percival Lowell, the man who had started the search for Planet X before he died. Venetia Burney received £5 for her contribution, about $6 at the time, maybe $500 in today's money, a modest reward for naming a world. But here's what makes this story even more wonderful. Venetia didn't actually see Pluto through a telescope until 2008, when she was 89 years old. 77 years passed between the moment she named it and the moment she saw it with her own eyes. She lived her whole life, childhood, adulthood, old age, with Pluto as this distant abstraction, a name she'd given to something she'd only read about in the newspaper. And then, in her final years, just before the New Horizons spacecraft would visit Pluto and show us what it actually looked like, she finally looked through a telescope and saw that faint point of light. The world she'd named, the God she'd chosen, still there, still distant, still mysterious after all those decades. Sometimes the things we name become more real to us than we ever imagined they could be. In Roman mythology, Pluto wasn't just any god. He was the ruler of the underworld, the realm of the dead, the hidden kingdom beneath the surface of the world, where souls went after their bodies failed them. But unlike the Greek version of this god, Hades, who was often depicted as grim and fearsome, Pluto had a particular quality that made him different. He could make himself invisible. He wore a helmet of invisibility, forged by the Cyclops, that allowed him to move unseen through the world of the living. When he wanted, he could simply disappear, becoming as intangible as shadow, present but undetectable. It was this quality, this ability to hide in plain sight, that made the name so perfect for the distant planet. Because Pluto the planet is invisible in a very real sense, not metaphorically, not poetically, actually invisible to the naked eye. Even on the clearest, darkest night, far from any city lights, with perfect vision and ideal conditions, you cannot see Pluto without a telescope. It's simply too far, away, too small, reflecting too little sunlight to register on the human retina. For all of human history, for every person who ever lived before 1930, Pluto was there, orbiting the sun, completing its slow 248-year journey around our star, and none of them knew it. Not the ancient astronomers who catalogued the stars, not the medieval scholars who tracked planetary motions, not even the brilliant minds of the scientific revolution who discovered Uranus and Neptune. Pluto remained invisible, hidden in the darkness, 3 billion miles away. And there's something almost poetic about the fact that when we finally did discover it, we named it after the god who could make himself invisible, as if the planet and the god had always been connected, as if the name was waiting there in mythology for thousands of years, ready for the moment when we'd finally need it. The initials P and L also honored Percival Lowell, the astronomer who had devoted the last years of his life to searching for this hidden world. He died in 1916, never knowing whether Planet X existed or not. But his obsession, his mathematical predictions, his belief that something was out there, all of that led to Clyde Tombaugh's search and eventually to the discovery. So the name worked on multiple levels: mythological, poetic, memorial, a god of invisibility and hidden realms, a tribute to the man who dreamed of finding it, a description of the planet itself, dark, distant, unseen for billions of years. Sometimes the right name finds its subject with such perfect precision that it feels inevitable, as if it could never have been called anything else. Venetia Burney, the girl who suggested naming Pluto, lived a long life. She grew up in England, lived through World War II, had a career as a mathematics and economics teacher, married, had children, grew old. Pluto remained out there, orbiting, unnamed to her personally, even though the whole world knew it by the name she'd given it. For 77 years, from 1930 to 2008, she lived with Pluto as something she'd named but never seen. She knew it was real. Astronomers had confirmed it. studied it, measured it, calculated its orbit. But she'd never looked at it herself, never pointed a telescope at that particular patch of sky and found that faint point of light, until 2008, when she was 89 years old. Someone at an observatory arranged for her to finally see Pluto through a proper telescope. And there it was, after all those decades, a tiny, dim speck, barely distinguishable from the background stars, exactly where it should be. What must that have been like? To see for the first time something you named when you were 11. To have the abstraction become concrete, the story become real. The newspaper article from 1930 transform into an actual photon of light that traveled 3 billion miles and landed on your retina. She didn't say much about it publicly. By all accounts, she was a private person, modest about her contribution. She seemed more amused than anything else that people made such a fuss about it. After all, she'd just suggested a name. Anyone could have done that. But what strikes me about this story is the patience of it. 77 years. Most people don't wait that long for anything. Most of us need immediate confirmation, instant gratification, proof that our actions mattered right away. But Venetia lived nearly her entire life with Pluto as this remote thing, this world that bore her name but remained essentially unknown to her personally. And here's another detail that makes this even more remarkable. Venetia's great-uncle, Falconer Madan, had also suggested names for celestial bodies earlier in his life. He'd proposed names for the moons of Mars, Phobos and Deimos, fear and dread. So in her family, there were 2 people who'd contributed to the naming of worlds. Imagine that legacy. Imagine Thanksgiving dinner conversations about who named which moon. Sometimes the small things we do, the suggestions we make, the ideas we offer, the names we propose, echo much farther than we expect. Sometimes they outlive us by centuries, attached to worlds that will orbit the sun long after humans have forgotten what a newspaper breakfast in Oxford ever was. Here's something that should make you pause and think about how discovery works. How easily we miss things, even when they're right in front of us. Lowell Observatory actually photographed Pluto in March of 1915. 15 years before Clyde Tombaugh officially discovered it. The tiny speck was there, captured on glass photographic plates, sitting among thousands of other specks that were stars. But nobody noticed it. Nobody recognized that one particular dot was different from all the others. It sat there, waiting, invisible not because of any physical law, but because of simple oversight. Because human eyes, no matter how carefully they looked, missed it. Think about that for a moment. Pluto was right there in the archive, documented, recorded, captured. If someone had looked at those plates more carefully, or with different expectations, or with better equipment for comparison, they might have discovered Pluto in 1915 instead of 1930. The history of astronomy would be slightly different. Clyde Tombaugh would have searched for Planet X and found nothing. Venetia Burney might never have suggested the name, but they didn't see it, and so Pluto remained undiscovered, even though it had already been found. This happens more than we'd like to admit in science. Data sits in archives, unexamined or misinterpreted, waiting for someone to look at it with fresh eyes or better context. Sometimes the breakthrough isn't new data, it's a new way of looking at old data. Sometimes we have the answer before we have the question. Those 1915 plates are still around, archived somewhere. Physical evidence that discovery isn't always about being the first to capture something. Sometimes it's about being the first to recognize what you've captured. The photons from Pluto fell on those glass plates in 1915, chemically altered the emulsion, created a permanent record. But the meaning of that record wouldn't be understood for another 15 years. There's something humbling about that. All our careful observations, all our methodical documentation, all our scientific rigor, and still we miss things. Still the universe hides its secrets in plain sight, waiting for the right moment, the right person, the right question to reveal them. Pluto was patient. It had been orbiting the Sun for 4.6 billion years. What was 15 more years? Percival Lowell died on November 12, 1916, at the age of 61. He'd spent the last years of his life obsessed with finding Planet X, convinced that mathematical irregularities in Neptune's orbit meant something massive lurked beyond. He built an observatory. He hired astronomers. He developed search protocols. He calculated where this hypothetical planet should be. And then he died, never knowing if he was right. 14 years later, Clyde Tombaugh discovered Pluto using the very protocols and equipment Lowell had established. And the announcement of the discovery was made on March the 13th, 1930. Which would have been Percival Lowell's 75th birthday. This wasn't entirely coincidental. The astronomers at Lowell Observatory chose that date deliberately, as a tribute to the man who'd made the search possible. But there's another layer of coincidence. March 13th was also the anniversary of the discovery of Uranus in 1781, exactly 149 years earlier. So on March 13, 1930, the world learned that the solar system had gained a 9th planet. On the birthday of the man who'd predicted it would be there. On the anniversary of the only other ice giant planet anyone had ever found. These kinds of cosmic coincidences don't mean anything really. They're not signs or portents. They don't suggest that the universe has a sense of narrative timing, but they feel meaningful anyway, don't they? They feel like the universe nodding along to the story we're telling ourselves about discovery and obsession and legacy. Percival Lowell never got to see Pluto. He never got the confirmation he spent his final years seeking. But his name is on the observatory. His initials are in the planet's name. His search protocols led directly to the discovery. In a very real sense, he found Pluto. He just didn't live long enough to know he'd succeeded. There's something bittersweet about that, about working towards something you'll never see completed, about planting trees you'll never sit under, about starting searches you'll never finish. Most of what we do in life is like that, really. We contribute to things larger than ourselves, things that will continue long after we're gone. Percival Lowell's obsession outlived him by 14 years, and the planet that obsession revealed will outlive all of us by billions. Here's where the story gets wonderfully strange. The mathematical predictions that led Percival Lowell to search for Planet X, the calculations that eventually guided Clyde Tombaugh to the right patch of sky, they were wrong, completely wrong. Lowell thought there were irregularities in Neptune's orbit that could only be explained by another massive planet tugging on it gravitationally. He did the math, predicted where this planet should be, and started searching. And he was right. There was something there, but it wasn't what he thought it was. The irregularities he'd observed in Neptune's orbit, they didn't exist. Later, more precise measurements showed that Neptune's orbit was perfectly fine, exactly where it should be based on the gravitational influences we already knew about. The mathematical foundation for Planet X was built on measurement errors and instrumental limitations from the 19th century. So the planet Lowell predicted, the massive world that should have existed to explain Neptune's motion, doesn't exist, never did, never will. And yet Clyde Tombaugh found Pluto almost exactly where Lowell said Planet X should be. How does that work? How do you search for something based on incorrect math and still find something? Luck mostly. Beautiful, cosmic luck. Pluto happened to be in roughly the right place at roughly the right time, purely by coincidence. It wasn't the planet Lowell was looking for. Pluto is far too small to affect Neptune's orbit in any measurable way. It's only about 0.2% of Earth's mass, a tiny thing, gravitationally irrelevant to Neptune. But it was there, and because Tombaugh was looking in that region of sky, because he was being methodical and thorough, because he was checking every possible location where Planet X might be, he found Pluto, even though Pluto wasn't what he was looking for. This happens in science more than we like to admit. You search for one thing and find another. You build an experiment to test one hypothesis and discover something completely unexpected. You follow incorrect math to a surprising truth. Pluto isn't Planet X. It never was. Planet X doesn't exist. It was a phantom, a mathematical ghost born from imperfect measurements. But Pluto is real, and it's far more interesting than the planet Lowell imagined, because Pluto isn't just a ninth planet. It's the first object discovered in an entire new region of the solar system, the Kuiper Belt, a vast collection of icy bodies that orbit beyond Neptune. Lowell was looking for a planet and accidentally found the key to understanding the solar system's outer architecture. His wrong math led to a discovery that was right in ways he never imagined. Sometimes being wrong in an interesting way is better than being right in a boring way. When Pluto was first discovered in 1930, astronomers thought it might be roughly the size of Earth. They couldn't measure it precisely. It was too far away, too faint, just a point of light in their telescopes. But they knew it had to be massive, enough to influence Neptune's orbit, even though it didn't. So they assumed it was large. Over the years, as telescope technology improved and measurement techniques became more sophisticated, Pluto kept getting smaller. By the 1950s, estimates had dropped to about the size of Mars. By the 1970s, maybe the size of our moon. In 1978, when astronomer James Christie discovered Pluto's largest moon, Charon, scientists could finally calculate Pluto's mass accurately by observing how the two bodies orbited each other. And the answer was shocking. Pluto was only about 1/5 the mass of Earth's moon. Imagine watching something shrink over decades, not actually shrinking. Pluto was always the same size, patiently orbiting out there regardless of what we thought about it. But our understanding of it kept contracting year by year, decade by decade, until we realized that this planet we'd discovered was actually smaller than many moons in the solar system. It's a cosmic case of diminishing expectations, the excitement of discovery meeting the humility of accurate measurement. By the time New Horizons flew past Pluto in 2015, we knew its diameter precisely. 377 kilometers, about 1,473 miles. That's roughly 2/3 the diameter of our moon. Its surface area is about 17.7 million square kilometers, slightly larger than Russia, but only about 3.3% of Earth's surface area. In terms of mass, Pluto is tiny. It weighs about 1.3 x 1022 kilograms, which sounds like a lot until you realize that Earth's moon is about 6 times more massive. Pluto is less than 0.2% of Earth's mass. If Earth were a basketball, Pluto would be smaller than a golf ball. This shrinking wasn't just about improving our measurements. It was about gradually understanding what Pluto actually was. Not the massive ninth planet that Percival Lowell imagined, but something else entirely. Something smaller, stranger, more representative of a whole population of objects we didn't yet know existed. Sometimes understanding something means accepting that it's not what you hoped it would be. And sometimes, paradoxically, that makes it more interesting. Pluto takes 248 Earth years to complete one orbit around the Sun. Think about that time scale for a moment. If you could somehow stand on Pluto's surface and watch the cosmos with a clock that marked Pluto's year instead of Earth's, you'd see a very different universe than we experience here. The last time Pluto was where it is now in its orbit, the year was 1778. The American Revolution was still being fought. The Constitution hadn't been written yet. Mozart was 22 years old, still years away from composing his greatest works. The Industrial Revolution was just beginning to transform England. Most of Earth's current population's great-great-great-great-great-great-grandparents hadn't been born yet. Pluto has been going around the Sun this whole time, through all of human history, completing one enormous circuit every quarter millennium. When Pluto was last at its perihelion, its closest point to the Sun, in 1989, it was the first time it had been there since 1741, the year before Bach wrote the Goldberg Variations, and Pluto won't return to where Clyde Tombaugh found it until 2178, 148 years from now. None of us will be alive to see it. Your children probably won't see it. Your grandchildren might be very old, if they see it at all. This is what time means on Pluto. Everything moves in slow motion from our perspective. Seasons last for decades. A Plutonian year spans multiple human lifetimes. If you were born on Pluto, you'd never live to see your first birthday. It's a time scale that challenges our intuition about planetary motion. We're used to Earth's quick lap around the Sun every 365 days. Mars takes a bit less than 2 years. Even distant Saturn only needs about 29 years. But Pluto? Pluto takes its time, moving through space at an average speed of 4.7 kilometers per second. Quick by human standards, but leisurely compared to Earth's 30 kilometers per second. That 248-year orbit is also highly elliptical, more stretched out than any other planet's path. At perihelion, Pluto comes as close as 4.4 billion kilometers from the Sun. At aphelion, its farthest point, it retreats to 7.4 billion kilometers. That's a huge difference, almost 3 billion kilometers of variation in distance. Sometimes the timescales of the cosmos make our own lives feel impossibly brief. But maybe that's not such a bad thing to contemplate as you drift off to sleep. On August 24, 2006, something unusual happened at a meeting of the International Astronomical Union in Prague. A vote was held, not about funding or research priorities or telescope allocations, but about something more fundamental: what counts as a planet. Only about 400 astronomers out of 10,000 in the organization were present to vote, less than 5% of the IAU membership. and they decided by majority vote to create a new definition of planet that would exclude Pluto. The definition had 3 criteria. A planet must orbit the Sun. It must be massive enough that its own gravity pulls it into a roughly spherical shape. And, this was the controversial part, it must have cleared the neighborhood around its orbit, meaning it has become gravitationally dominant in its orbital zone. Pluto failed that 3rd criterion. It shares its orbital space with thousands of other objects in the Kuiper belt. It hasn't cleared its neighborhood. Therefore, by this new definition, it wasn't a planet anymore. It was reclassified as a dwarf planet, a new category created specifically for objects like Pluto that are spherical but haven't achieved orbital dominance. Many planetary scientists disagreed with this vote. Many still do. They point out that the definition was created hastily, voted on by a tiny fraction of the organization, and includes problems. Earth hasn't cleared its neighborhood either. We share our orbit with thousands of asteroids. Jupiter hasn't cleared its orbit. It's surrounded by Trojan asteroids. By strict interpretation, only Mercury and perhaps Venus would qualify as true planets. But the vote stood, and on August 24, 2006, after 76 years as the 9th planet, Pluto was demoted. The word demoted carries weight, doesn't it? It suggests that Pluto lost something, that it was diminished somehow. But really, Pluto didn't change at all. It continued orbiting exactly as it always had, completely indifferent to what humans decided to call it. The only thing that changed was our classification system, our attempt to organize the solar system into tidy categories. And maybe that's what made the demotion so controversial. It wasn't really about Pluto. It was about us, about our need to categorize, to define, to create boxes that nature doesn't actually care about. Many planetary scientists still call Pluto a planet in their research papers. They argue that any spherical object in orbit around a star is a planet, regardless of what else is nearby. They point out that the clearing the neighborhood criterion is arbitrary and inconsistent. The debate continues, and Pluto, 3 billion miles away, continues its patient orbit, unconcerned with our definitions. In 2005, a year before Pluto's reclassification, astronomer Mike Brown discovered an object in the Kuiper belt that appeared to be larger than Pluto. He initially called it Xena, after the warrior princess, but it was eventually officially named Eris, after the Greek goddess of discord and strife. Eris is about the same size as Pluto, slightly smaller in diameter but more massive overall. It orbits even farther from the Sun than Pluto, taking 558 years to complete one orbit. And its discovery created a genuine crisis in astronomy. Because if Eris was a planet, then we suddenly had 10 planets, not 9. And if Eris was a planet, then what about all the other large objects being discovered in the Kuiper belt? Makemake, Haumea, Sedna, Quaoar. Where do you draw the line? Do we end up with 12 planets? 20? 100? The press immediately started calling Eris the 10th planet, and for a brief moment in 2005, many people believed we just expanded the solar system again. Textbooks would need to be rewritten. Mnemonics would need updating. Children would need to learn a new planet name. But astronomers looked at this situation and realized they had a choice. Either accept that the number of planets would keep growing as we discovered more Kuiper belt objects, or create a definition that would exclude these distant, small worlds. They chose the latter, and Pluto, caught in the same net as Eris, lost its planetary status. In a way, Eris really did live up to its name: discord and strife. Its discovery forced astronomers to confront questions they'd been avoiding. What makes something a planet? Is it size, mass, composition, orbital, characteristics? Or is it something more subjective? Historical precedent, cultural significance. Mike Brown, who discovered Eris, wrote a book about the whole affair titled How I Killed Pluto and Why It Had It Coming. He's become something of a controversial figure, celebrated by some as the man who brought order to planetary classification, reviled by others as the person who stole Pluto's planetary status. But really, all he did was find something. He pointed his telescope at a patch of sky, discovered a distant world, and accidentally triggered a debate that had been waiting to happen for decades. Because the truth is, astronomers had known for years that Pluto was weird. Too small, too distant, orbit too elliptical, too different from the 8 planets closer to the Sun. Eris just forced everyone to admit what they'd been quietly thinking. Maybe Pluto was never really a planet in the same sense as Jupiter or Earth. Maybe it was always something else. When the news broke that Pluto had been reclassified as a dwarf planet, the public reaction was swift and intense. People were angry, not just disappointed, actually angry. Protests were organized, petitions were signed. Social media erupted with defenses of Pluto. Elementary school students held demonstrations, carrying signs that said things like, "Pluto is still a planet in my heart," and "Give Pluto its planet status back." Teachers reported that children were genuinely upset, as if something beloved had been taken away from them. The American Dialect Society named Plutoed as its 2006 Word of the Year, defining it as to demote or devalue someone or something, as happened to the former planet Pluto. The verb entered casual language almost immediately. "I got Plutoed at work" meant you'd been demoted. "My proposal got Plutoed" meant it was rejected or downgraded. Why did this matter so much to people? Why did a change in astronomical classification trigger genuine emotional responses? Maybe it's because Pluto had always been the underdog planet, the smallest, the most distant, the last one discovered, the weird one that didn't quite fit. And people love underdogs. We identify with them. We root for them. When someone tells us the underdog doesn't count anymore, doesn't belong in the same category as the others, it feels personal. Or maybe it's simpler than that. Maybe it's just that we don't like change. We learned 9 planets in school. We memorized mnemonics. My very excellent mother just served us 9 pizzas, or variations thereof. 9 felt right, felt complete. Taking one away felt like theft, like something was being removed from our understanding of the universe. Scientists tried to explain that nothing had actually changed except our classification system. Pluto was still there, still interesting, still worthy of study. In many ways, they argued, being recognized as the largest member of the Kuiper Belt was more scientifically significant than being the runt of the planetary family. But the protests continued. People felt a genuine attachment to Pluto, one that transcended scientific definitions. And in that attachment, in that refusal to accept the demotion, there's something deeply human. We don't let go of things easily, even when experts tell us we should. We hold on to what we love, even when the universe, or at least the astronomers, tells us we're being irrational. Pluto remained in our hearts, even if it was no longer officially in the planetary lineup. In March 2007, the Illinois State Legislature passed a resolution declaring that Pluto would always be considered a planet while passing through Illinois skies. The resolution stated that Pluto was unfairly downgraded and that Illinois would restore its full planetary status. This was largely symbolic, of course. State legislatures don't have jurisdiction over astronomical classifications. Illinois can't actually change what Pluto is called in scientific papers or textbooks. But the gesture mattered anyway because Clyde Tombaugh, the man who discovered Pluto, was born in Illinois. The state was standing up for its native son's discovery. New Mexico followed with a similar resolution, declaring that Pluto would always be considered a planet while in New Mexico skies. Tombaugh had lived in New Mexico for much of his adult life, working at Lowell Observatory and later teaching at New Mexico State University. The resolution specifically designated March 13th, the anniversary of Pluto's discovery announcement, as Pluto Planet Day in New Mexico. These legislative actions were mostly ceremonial, a way for states to celebrate their connection to one of the 20th century's greatest astronomical discoveries. But they also represented something deeper, a refusal to accept that scientific consensus should overwrite cultural significance. Because Pluto meant something to people in Illinois and New Mexico that went beyond its astronomical classification. It was part of their state identity, their sense of pride, their connection to scientific history. When the IAU said Pluto is no longer a planet, these states essentially said, we don't care. It's a planet to us. There's something wonderfully stubborn about that, something very human. We don't always accept what authorities tell us, especially when it conflicts with our sense of loyalty or identity. We create our own definitions, our own categories, our own truths. And maybe that's okay. Maybe the universe is big enough to accommodate both scientific definitions and emotional attachments. Maybe Pluto can be a dwarf planet in astronomical papers and still be the 9th planet in the hearts of people who grew up with it that way. The cosmos doesn't care what we call anything. Names and categories are human inventions, tools we use to organize our understanding. They're not fundamental truths written into the fabric of reality. They're just agreements. And when we disagree with those agreements, when we decide that our local truth matters more than the global consensus, we're exercising a very human freedom. Pluto is a planet in Illinois. Pluto is a planet in New Mexico, and maybe that's enough. Here's the paradox. By demoting Pluto from planet to dwarf planet, astronomers actually increased its scientific significance. When Pluto was considered the 9th planet, it was always the weird one, the odd one out, too small, too distant, orbit too elliptical, too different from the others. It was the runt of the planetary litter, the planet that didn't quite fit, the mistake at the end of the lineup. But when Pluto was reclassified as a dwarf planet and recognized as a member of the Kuiper Belt, suddenly everything made sense. It wasn't a misfit planet anymore. It was the largest known member of an entire population, the king of the Kuiper Belt, the exemplar of a whole class of objects that outnumber the traditional planets by thousands to one. The Kuiper Belt is vast. It extends from Neptune's orbit at about 30 AU out to approximately 50 AU from the Sun. Within that region, there are hundreds of thousands of icy objects, all left over from the solar system's formation 4.6 billion years ago. They're time capsules, preserving the original conditions and materials that built our worlds. And Pluto is the largest of them all, or at least the largest we've found so far. It's not competing with Jupiter or Earth anymore. It's representing an entire population, a whole region of the solar system that we barely understand. This shift in perspective, from runt planet to king of the Kuiper Belt, transformed Pluto from an embarrassing anomaly into a scientifically crucial object. Studying Pluto now means understanding the Kuiper Belt. Understanding the Kuiper Belt means understanding how the solar system formed, how planets migrated, what the outer reaches of our cosmic neighborhood look like. So in a strange way, Pluto's demotion was actually a promotion. It went from being the least important planet to being the most important dwarf planet, from misfit to icon, from afterthought to ambassador. Scientists who study the Kuiper Belt don't mourn Pluto's lost planetary status. They celebrate it. Because recognizing Pluto as a Kuiper Belt object, as the first and largest member of this newly discovered population, gave us a framework for understanding an entire region of space. Sometimes being the biggest small thing is more important than being the smallest big thing. Sometimes finding your true category, even if it sounds less prestigious, reveals your actual significance. Pluto is more interesting as a dwarf planet than it ever was as a regular planet. And maybe that's the real lesson here, that categories matter less than what things actually are. Pluto's diameter is 2,377 kilometers, about 1,173 miles. To give you a sense of scale, that's roughly 2/3 the size of Earth's moon. If you could stand on one side of Pluto and look across to the other, you'd be looking across a distance about equal to the width of the continental United States. Its surface area is approximately 17.7 million square kilometers, which is slightly larger than Russia, the biggest country on Earth. If you could unfold Pluto's surface and lay it flat, it would cover more ground than Russia's 17.1 million square kilometers. But here's where things get interesting. Despite being larger in surface area than Russia, Pluto weighs only about 17.7% as much as Earth's moon. How is that possible? How can something be geographically large but gravitationally light? The answer is density. Pluto is made of different materials than our moon. The moon is rocky, dense, composed primarily of silicates and metal. Pluto is a mixture, about 2/3 rock and 1/3 water ice by mass. Ice is less dense than rock, so Pluto ends up being much lighter for its size. This has profound implications for what it's like on Pluto's surface. The gravity is weak, only about 6.3% of Earth's gravity. If you weigh 200 pounds on Earth, you'd weigh just about 12.6 pounds on Pluto. You could jump approximately 15 times higher than on Earth, though you'd fall back down in slow motion, taking much longer to land. Imagine walking on Pluto. Each step would launch you meters into the air. You'd bound across the landscape like an astronaut on the moon, except even more extreme. Running would be more like flying, each stride carrying you in long, graceful arcs across the nitrogen ice plains. But you'd have to be careful. The escape velocity on Pluto is only 1.2 kilometers per second, slow enough that if you could somehow throw a baseball at about 2,700 miles per hour, it would leave Pluto entirely and drift off into space. You'd be on a world where escaping completely is theoretically possible with the right technology. The weak gravity also affects how Pluto holds its atmosphere. On Earth, our strong gravity keeps air molecules close to the surface, compressed into a relatively thin layer. On Pluto, the weak gravity allows atmospheric gases to spread out over vast distances, creating an atmosphere that extends over 1,000 miles above the surface, proportionally much thicker than Earth's, even though it's far less dense. So when we say Pluto is the size of Russia, we're talking about surface area, about the amount of terrain to explore. But in terms of mass, in terms of gravitational influence, Pluto is surprisingly insubstantial. It's a small world, light and delicate, wearing a surface as large as a country, but weighing less than a moon. On Earth, if you're reasonably athletic, you might be able to jump 0.5 meter high, about 20 inches. That's the limit of what human legs can do against Earth's strong gravitational pull. Professional high jumpers with running starts and perfect technique can clear just over 2 meters. On Pluto, everything changes. With gravity at only 6.3% of Earth's normal pull, that same jump would carry you approximately 7.9 meters into the air, about 26 feet. That's higher than a 2-story building. Without even trying particularly hard, without any running start, just a regular standing jump would launch you to the height of a basketball hoop and then keep going. But it would happen in slow motion. You'd rise into the thin atmosphere, such as it is, accelerating upward from your jump, but decelerating much more gradually than on Earth. At the peak of your jump, you'd hang there for a moment, floating, suspended in the weak gravity, before beginning your slow descent. The entire jump would take much longer than on Earth. What normally lasts less than a second would stretch out over several seconds. You'd have time to think during your jump, time to look around, time to realize how high you were, and wonder if you'd calculated the landing correctly. Landing would be gentle, relatively speaking. You'd come down slowly, your weight distributed over weak gravity, touching the surface with far less force than on Earth. As long as you landed on your feet, you'd probably be fine. The impact would be maybe 1/10 as severe as landing from the same height on Earth. Running would be even stranger. Each stride would become a bound, carrying you meters forward and several meters up. You'd spend more time in the air than on the ground. It would be less like running and more like skipping in slow motion across an alien landscape, each step a miniature flight. But you'd have to be careful about velocity. The escape velocity on Pluto is only 1.2 kilometers per second, about 2,700 miles per hour. Obviously, you couldn't jump that fast. But it's a reminder that Pluto's grip on things is weak. It wouldn't take much energy to leave Pluto entirely, relatively speaking. A spacecraft launching from Pluto's surface needs far less fuel than one launching from Earth. There's something dreamlike about imagining movement in such weak gravity. The way you'd float more than walk. The way every action would be slowed down, stretched out, made graceful by the simple absence of weight. It would be like moving through water, except without the resistance. All the floating, none of the drag. Of course, you'd need a spacesuit. The surface temperature is around 230 degrees C, the atmosphere is barely there, and there's no breathable oxygen. But if you could somehow stand on Pluto safely, if you could jump in that weak gravity and survive the experience, you'd understand what it's like to move in a world where weight means almost nothing. Light from the sun travels at approximately 299,792 kilometers per second, and the fastest speed possible in our universe. Nothing with mass can move that fast. Information itself can't travel faster. When you flip a light switch, the electricity moves at roughly the speed of light. When you look at something, photons traveling at exactly light speed hit your retina. On Earth, we're about 150 million kilometers from the Sun, a distance defined as 1 astronomical unit, or AU. Sunlight takes about 8 minutes and 20 seconds to cover that distance and reach our planet. When you look at the Sun, which you shouldn't do directly, you're seeing it as it was 8 minutes ago. The light left the Sun's surface, traveled through space, and arrived at your eyes just now. Pluto is much farther away. On average, it orbits at about 39.5 AU from the Sun, though this varies significantly because of its elliptical orbit. At that distance, sunlight takes approximately 5 hours and 30 minutes to arrive. Think about what that means. When you observe Pluto from Earth, when you point a telescope at that faint speck of light, you're seeing Pluto as it was 4.4 hours ago minimum, sometimes as much as 6 hours ago, depending on where both planets are in their orbits. You're looking into Pluto's past the same way we see stars from years or centuries ago. If you were somehow standing on Pluto's surface and you looked at the Sun, you'd be seeing it as it was 5.5 hours earlier. If the Sun exploded right now, you wouldn't know for 5.5 hours. The light would continue streaming toward Pluto for that entire time, unchanged, carrying no information about the catastrophe, until finally the last photons arrived, and then darkness. This time, delay affected the New Horizons mission in interesting ways. When Mission Control sent commands to the spacecraft at Pluto, those signals, traveling at light speed, took 4.5 hours to arrive. The spacecraft would execute the command, send back confirmation, and Mission Control would receive that confirmation another 4.5 hours later. Total round-trip communication time, 9 hours. That means if something went wrong during the Pluto flyby, if the spacecraft encountered an unexpected problem, Mission Control wouldn't know about it for 4.5 hours. And then it would take another 4.5 hours for any corrective commands to reach the spacecraft. By then, the flyby would be long over. New Horizons had to be completely autonomous, making all its own decisions in real time, because Earth was simply too far away to help. This is what distance means in space. Not just physical separation, but temporal isolation. When you're 5.5 light hours away from the Sun, you're living in a different moment than anyone closer. You're experiencing the universe on a delay, seeing everything as it was hours ago, forever slightly out of sync with the rest of the solar system. If you could stand on Pluto's surface at noon, at the moment when the Sun is highest in the sky, you'd notice immediately that something is very wrong with the light. It would be dim, not dark exactly, but deeply twilight. The Sun would appear as an intensely bright star, far brighter than any star in Earth's night sky, but nowhere near the blazing disk we see from our planet. It would be about 900th as bright as the Sun appears from Earth. To give you a comparison, the Sun from Pluto would appear roughly 300 times brighter than Earth's full moon appears to us. That's bright enough to cast shadows, bright enough to see clearly, bright enough that you'd need eye protection if you looked directly at it. But it wouldn't illuminate the landscape the way sunlight does on Earth. Everything would be bathed in a ghostly, dim glow. Colors would be muted, shadows would be deeper and longer, and the overall feeling would be one of permanent, deep twilight. That particular quality of light you get on Earth about 30 minutes after sunset, when there's still enough light to see but the sun has dropped below the horizon. Your eyes would adapt, of course. Human vision is remarkably flexible. After a few minutes, Pluto's noontime brightness would seem normal to you. The same way your eyes adapt to indoor lighting and stop noticing how much dimmer it is than daylight. You'd be able to see clearly, move around, explore the terrain. But if you'd just arrived from Earth, the darkness would be shocking. It would feel like the sun was failing, like something fundamental was wrong with the universe. That instinctive sense that the sun should be bright, should be warm, should dominate the sky, it would be violated. You'd be standing in daylight that feels like evening, and this is at noon, at the brightest moment of the day. As Pluto rotates and the sun moves toward the horizon, the light would fade even more. By the time the sun sets, which takes much longer than on Earth because Pluto rotates so slowly, you'd be in genuine darkness, with only starlight for illumination. The temperature wouldn't change much between day and night, though. On Earth, we experience significant temperature differences between noon and midnight because sunlight heats the ground. But on Pluto, the sun is so weak and distant that it barely affects surface temperature at all. The difference between Pluto's day and night is mostly about light, not heat. It's cold all the time, whether the sun is up or not. This is what it means to live at the edge of the solar system. The sun is still there, still providing light, still technically the dominant source of illumination. But its power is so diminished, so reduced by distance, that it becomes almost symbolic, a reminder of the star at the center of our system, rather than a meaningful source of warmth or bright light. You'd spend your days in twilight, looking up at a sun that's barely more than a bright point, knowing that somewhere, impossibly far away, that same star is blazing bright enough to burn skin and bleach colors. But not here, not this far out. Here the sun is just a memory of brightness, a faint echo of what it means to be near a star. Pluto's average density is about 1.85 grams per cubic centimeter. That number might not mean much at first, but it tells us almost everything about what Pluto is made of and how it formed. Water has a density of 1.0 gcm3, by definition, since that's how the metric system was originally calibrated. Rock, specifically the silicate minerals that make up Earth's crust and mantle, typically has a density around 3.0 gcm3. Pure water ice is slightly less dense than liquid water, about 0.92 gcm3, which is why ice floats. Pluto's density of 1.85 gcm3 sits right between ice and rock, suggesting it's a mixture of both. Detailed models based on New Horizons data indicate that Pluto is approximately 70% rock and 30% water ice by mass. In other words, if you could somehow melt Pluto down and separate its components, you'd end up with a pile of rock about twice as large as your pile of ice. This mixture makes Pluto fundamentally different from the planets closer to the Sun. Earth, Venus, Mars, and Mercury are rocky worlds, made primarily of silicates and metals, with little to no ice. The gas giants, Jupiter and Saturn, are mostly hydrogen and helium, with small rocky cores. The ice giants, Uranus and Neptune, have larger cores surrounded by ices of water, ammonia, and methane. Pluto falls into this last category, sort of. It's similar in composition to the moons of the outer planets. Objects like Europa, Enceladus, Triton, and Titan which are all mixtures of rock and ice. This makes sense because Pluto formed in the same region of the solar system as these moons, from the same kinds of materials. The rock in Pluto likely consists of silicates similar to Earth's mantle. Minerals like olivine and pyroxene formed from silicon, oxygen, magnesium, and iron. These settled toward the center during Pluto's formation, creating a dense, rocky core roughly 1,700 kilometers in diameter. Above this core sits a thick mantle of water ice, possibly as much as 300 kilometers thick. This isn't the ice you find in your freezer. At the pressures and temperatures inside Pluto, water ice can exist in several different crystalline forms, some denser than others, some with different properties. The deepest layers might even be in a high-pressure form called ice seventh, which has a different molecular structure than normal ice. There's also evidence, fairly strong evidence, that between the rocky core and the ice mantle, there might be a liquid water ocean. We'll get to that later, but for now, just know that Pluto's interior is probably more complex than just rock below, ice above. The surface, meanwhile, is covered in more exotic ices, not just water ice, but frozen nitrogen, methane, and carbon monoxide, substances that are gases or liquids on Earth, but freeze solid at Pluto's frigid temperatures. These volatile ices are what make Pluto's surface so dynamic and interesting, but they're just a thin coating. Below them, Pluto is stone and ice, ancient materials from the solar system's formation, compressed together by weak gravity into this small, distant world. One day on Pluto, one complete rotation on its axis, lasts 153 Earth hours. That's 6 days and 9 hours by our reckoning. If you lived on Pluto, you'd experience sunrise once per week. Think about what that means for the experience of time. On Earth, we're so accustomed to the 24-hour cycle that it's become fundamental to how we organize our lives. We sleep when it's dark, wake when it's light. Our bodies have internal clocks calibrated to this rhythm, circadian cycles that expect darkness and light to alternate every 12 hours or so. On Pluto, everything would be stretched out. The sun would rise, slowly, taking hours to climb above the horizon, because Pluto rotates so gradually. It would arc across the sky over the course of more than 3 Earth days, moving so slowly you could barely perceive its motion. At noon, it would hang there, that dim, bright point, for what would feel like forever. Then it would set, again slowly, hours passing as the sun crept toward the horizon, the already dim light fading even further, until finally it dropped below the edge of the world and darkness arrived. And that darkness would last for 3 more Earth days, 76.5 hours of night, with no sun at all, just the stars, and perhaps Charon, Pluto's largest moon, hanging in the sky if you were on the right hemisphere. What would sleep cycles be like in a place like that? Would you adapt to the long day and night, sleeping for 20 or 30 hours at a stretch and staying awake for equally long periods? Or would your body maintain something closer to Earth's rhythm, forcing you to sleep and wake multiple times during each Pluto day and night? The Plutonian week would take on a different meaning. 1 rotation, 1 sunrise and sunset, 1 complete cycle of light and darkness. If you measured time by days on Pluto, 7 rotations would be about 44 Earth days, a month and a half. A Plutonian month, if you divided the year into 12 equal parts, would last about 20.6 Earth years. Time becomes strange at these scales. The normal markers we use, day and night, weeks, and months start to lose their meaning when days last 6 of our days and years last 248 of our years. You'd need new units, new ways of thinking about time's passage, but the physics remains the same. Pluto spins, completing one rotation every 153 hours. The sun appears to move across the sky, even though it's actually Pluto turning beneath it. Shadows shift and lengthen and disappear and return. The same fundamental process that gives us day and night on Earth happens on Pluto too, just much, much more slowly. If you were standing on Pluto's surface with nothing to do but watch, you could actually see the sun move. On Earth, the sun's apparent motion is too slow to perceive directly. You have to look away for minutes or hours and then look back to notice its changed position. But on Pluto, rotating so slowly, the sun would drift across the sky at a pace you could track in real time if you were patient enough. Not quickly, but noticeably, like watching the hour hand on a clock. The day would feel endless, and then the night would feel equally endless. And somewhere in that stretched out, slowed down experience of time, you'd have to find a new rhythm, a new way of existing that didn't depend on Earth's quick rotation and familiar cycles. Most planets in our solar system spin the same direction they orbit, counterclockwise when viewed from above the sun's north pole. This is called prograde rotation, and it's the natural result of how the solar system formed. The cloud of gas and dust that collapsed to form the sun and planets was already rotating in one direction, and that rotation got carried through into the motions of most objects. But there are exceptions. Venus rotates backward, clockwise instead of counterclockwise. Uranus is tipped on its side, rotating at a 98-degree angle, and Pluto, like Venus, spins backward. It has retrograde rotation. This means that if you could somehow see the sun from Pluto's surface, which you can, though it's dim, it would rise in the west and set in the east, opposite of Earth, opposite of what we consider normal. What caused this backward spin? We're not entirely sure, but the most likely explanation involves collisions. Early in the solar system's history, when Pluto was forming, it probably got hit by other objects, maybe many objects. The Kuiper Belt was a chaotic place 4 billion years ago, full of planetesimals crashing into each other, accreting, breaking apart, reforming. One particularly large impact, or perhaps several impacts from specific angles, could have reversed Pluto's rotation. It's like spinning a coin on a table and then flicking it from the side. You can change its direction of rotation with the right hit. The same process probably explains Uranus's extreme axial tilt and Venus's backward spin. Collisions during the solar system's youth were common, and they left their marks in strange rotations and unusual tilts. What's interesting is that Pluto's largest moon, Charon, also has retrograde rotation, and it's tidally locked to Pluto, meaning the same face always points toward Pluto. This suggests that whatever event caused Pluto's backward spin happened before Charon formed, or that Charon formed as a result of the same collision that reversed Pluto's rotation. There's a theory, which we'll explore more later, that Pluto and Charon formed through a massive collision between two large Kuiper Belt objects. In this scenario, the impact not only created the binary system, but also left both bodies spinning backward, locked together in their unusual dance. From a practical standpoint, the direction of rotation doesn't matter much. Physics works the same way whether you're spinning forward or backward. The Coriolis effect the force that makes weather systems rotate would be reversed, so storms would spin the opposite direction than on Earth. But there aren't really storms on Pluto in the traditional sense, so this is mostly theoretical. What matters more is the symbolism, perhaps. Pluto spinning backward, going against the grain, refusing to conform to the same pattern as most other planets. It's another way Pluto stands apart, another reminder that this distant world doesn't follow the rules established closer to the Sun. The Sun rises in the west on Pluto. After a 3-day climb across the sky, it sets in the east, and everything spins slowly backward, out of step with the rest of the solar system. Earth's axis is tilted 23.5 degrees relative to the plane of its orbit. This tilt is what gives us seasons. As Earth orbits the Sun, first one hemisphere tilts toward the Sun, summer, then the other, winter. It's a moderate tilt, enough to create seasonal variation without being extreme. Pluto's axial tilt is 120 degrees. Let that sink in for a moment. Not 20 degrees, not 40 degrees, but 120 degrees. Pluto is essentially rotating on its side, but even more extreme than that, it's past the 90-degree mark, meaning it's actually slightly upside down in addition to being sideways. To visualize this, imagine taking Earth and tipping it so that the North Pole points not up, but sideways, toward the Sun, and then tipping it even further, so the North Pole is actually pointing slightly downward. That's approximately Pluto's orientation. This creates seasons unlike anything we experience on Earth. When Pluto's North Pole is tilted toward the Sun, the northern hemisphere receives continuous sunlight for decades, while the southern hemisphere sits in complete darkness. Then, as Pluto continues its 248-year orbit, the orientation changes and the seasons reverse. At the poles themselves, the effect is most extreme. Imagine living at Pluto's North Pole. For roughly 100 years, more than an entire human lifetime, the Sun never sets. It circles around the horizon, that dim point of light, making slow circles in the sky as Pluto rotates every 153 hours. Daylight, such as it is, continues unbroken for a century. Then, over a period of years, the Sun starts dipping below the horizon for longer and longer periods. The periods of daylight get shorter. Eventually, the Sun sets for the last time, dropping below the horizon and disappearing. And then darkness. Complete darkness. For another 100 years, when you're at Pluto's pole, you experience one sunrise and one sunset per Pluto year. One day and one night, each lasting a century. Your children, grandchildren, great-grandchildren could all be born, live their entire lives, and die without ever seeing the Sun change from being up to being down. At Pluto's equator, the experience is different, but still strange. The Sun rises and sets every 153 hours as Pluto rotates, giving something like a normal day-night cycle. But over the course of Pluto's long orbit, the Sun's path across the sky changes dramatically. Sometimes it arcs high overhead. Sometimes it barely peaks above the horizon. The seasons, measured in decades, alter everything. This extreme tilt has profound effects on Pluto's atmosphere and geology. When a polar region emerges from a century of darkness into a century of light, massive amounts of nitrogen ice begin to sublimate, turning directly from solid to gas. The atmospheric pressure can increase by factors of 100 or even 1,000 in relatively short periods. When the Sun sets on a polar region after 100 years of daylight, all that atmospheric nitrogen freezes back out, forming layers of ice meters thick. The atmosphere collapses. pressure drops. The entire climate shifts. Pluto's seasons aren't subtle variations in temperature and weather. They're dramatic transformations of the entire world, driven by this extreme axial tilt and the long, slow orbit that takes 248 years to complete. Right now, we're in Pluto's summer in the northern hemisphere and winter in the southern hemisphere. The North Pole emerged from its century-long winter in the late 1980s and won't see sunset again until sometime in the 2070s. The South Pole has been in darkness since the 1980s and won't see sunrise until the 2070s. These are the seasons of Pluto, measured not in months but in generations, determined not by moderate tilts but by extreme orientations, experienced not as gentle transitions but as radical transformations of the entire world. The surface temperature on Pluto ranges from about 387 degrees to 400 degrees, or 232 degrees to 240 degrees. These aren't the coldest temperatures in the solar system. Triton, Neptune's largest moon, and parts of Uranus and Neptune's upper atmospheres get even colder. But they're cold enough that almost nothing behaves the way we're accustomed to. At these temperatures, nitrogen, which makes up 78% of Earth's atmosphere and is a gas at any temperature humans can survive, becomes a solid. It freezes. On Pluto's surface, nitrogen doesn't float in the air as a gas or pool as a liquid. It forms sheets of nitrogen ice, hard and cold, covering vast plains. Water, of course, is frozen solid, but not like the ice in your freezer. At Pluto's temperatures, water ice is as hard as granite. It's structural material, bedrock. Mountains on Pluto are made of water ice because nothing else is strong enough to support topography at those temperatures. Water ice is to Pluto what granite and basalt are to Earth. The foundation, the bones of the landscape. Methane freezes at 102 degrees, say. So at Pluto's temperatures it's solid too, forming ice deposits and frost layers. Carbon monoxide freezes at 205 degrees, also solid. The atmosphere itself, thin as it is, consists of these substances slowly sublimating from ice to gas and then condensing back to ice elsewhere. A global cycle of frozen materials becoming briefly gaseous and then freezing again. If you somehow stood on Pluto without protection, your body heat would radiate away in seconds. Your breath, warm, moist air containing nitrogen, oxygen, water vapor, and carbon dioxide, would freeze instantly. Not gradually, not over minutes, but immediately. Every molecule of water in your breath would crystallize into ice before it could disperse. You'd exhale clouds of frozen particles. Your body itself would freeze rapidly. The extreme cold would damage cells, forming ice crystals that puncture cell membranes, destroying tissue. But you wouldn't feel it for long, because you'd lose consciousness within seconds from lack of oxygen and pressure. But even the concept of cold becomes strange at these temperatures. Cold, as we experience it, is the absence of heat, molecules moving more slowly, vibrating less energetically. At Pluto's temperatures, molecules are moving about as slowly as they can while still remaining relatively mobile. There's still some thermal energy, still some vibration and motion, but it's minimal, barely above the absolute minimum required to maintain the liquid-like behavior of nitrogen ice as it slowly convects. In a strange way, Pluto exists at a temperature where solid materials can still flow, still move, still reshape landscapes, but just barely. Nitrogen ice at 230 degrees Celsius is close to its melting point, relative to Pluto's low pressure, which means it can deform and flow over geological time. It's solid, but it behaves like extremely thick honey, moving centimeters per year, convecting, circulating. This is the coldest place where geology still happens, where surfaces are still active and changing. Go much colder, and everything locks into place permanently. Even the slow creep of ice stops. But Pluto somehow maintains just enough warmth, just barely enough, for its frozen world to remain dynamic. It's a threshold environment, balanced at the edge between frozen stillness and glacial activity. And in that balance, remarkable things happen. For 20 years out of every 248-year orbit, Pluto comes closer to the Sun than Neptune. Yes, you read that correctly. The outermost planet, or dwarf planet, isn't always the outermost. This happens because Pluto's orbit is highly elliptical, much more elongated than any of the 8 planets. At perihelion, its closest approach to the Sun, Pluto comes within 29.7 AU, closer than Neptune's average distance of 30.1 AU. The most recent time this occurred was from 1979 to 1999. For 20 years, spanning the turn of the millennium, Neptune was technically the most distant planet in the solar system, not Pluto. Pluto had temporarily moved inward, closer to the Sun's warmth, relatively speaking, while Neptune maintained its steady circular orbit beyond. Now, before you worry about a collision, let me reassure you, Pluto and Neptune never actually get close to each other, despite Pluto crossing Neptune's orbital path. They're protected by something called orbital resonance, which we'll explore more deeply later. But the short version is that their orbits are synchronized in such a way that when Pluto crosses Neptune's orbit, Neptune is always far away on the other side of the Sun. This periodic shift in distance has real effects on Pluto. As it moves closer to the Sun, it receives more sunlight. Not a lot more, but enough to matter. The surface warms slightly from 233 cc to maybe 228 cc. That 5-degree difference, small as it seems, is enough to cause more nitrogen ice to sublimate into gas, thickening the atmosphere. Conversely, as Pluto moves back out toward aphelion, its farthest point at 49.3 AU, it cools down. The atmosphere begins to freeze out, condensing back onto the surface. For decades now, astronomers have been watching to see if Pluto's atmosphere will completely collapse as it retreats from the Sun, or if it will persist year-round. The most recent evidence suggests it's beginning to collapse. Observations from 2019 showed atmospheric pressure dropping significantly, faster than models predicted. This might mean that Pluto is entering a phase where its atmosphere largely freezes out, coating the surface in meters-thick layers of nitrogen ice, leaving only a thin wisp of gas behind. But we won't know for sure for decades. Pluto's seasonal changes happen so slowly that we need to watch for human lifetimes to see the full cycle. We're fortunate that Pluto reached perihelion relatively recently, in 1989, so we've been able to observe it during what is essentially its summer. But winter is coming slowly, inexorably, and the atmosphere may vanish with it. The fact that Pluto sometimes comes closer than Neptune creates an interesting question. Should we say Pluto is the 9th planet or 9th world from the Sun, or the 8th? Does order depend on average distance or instantaneous distance? It's another example of how Pluto refuses to fit neatly into categories. For those 20 years from 1979 to 1999, school children learning the planets had to know that Neptune was temporarily the farthest out. Textbooks had to note this quirk. Mnemonics had to be carefully worded. My very educated mother just served us 9. What? What comes after nachos for Neptune? pizzas for Pluto, but which one is last? Pluto reached aphelion, its farthest point from the Sun, in 1866, and won't reach it again until 2114. So for the next century, it's moving generally inward, though very slowly. It will reach perihelion again in 2237, another 212 years from now, and for 20 years around that time, Neptune will once again be the most distant planet. These cycles operate on timescales that dwarf human civilizations. Pluto doesn't care about our classifications or our textbooks. It follows its elliptical path, sometimes coming closer, sometimes retreating farther, indifferent to our attempts to rank it among the worlds of the solar system. Pluto completes exactly 2 orbits around the Sun for every 3 orbits that Neptune makes. This is called a 3.2 orbital resonance, and it's one of the most elegant examples of gravitational choreography in the solar system. Think about what this means. Every time Pluto goes around the Sun twice, taking 496 Earth years, Neptune goes around exactly 3 times, taking 495 Earth years. They're locked in a perfect mathematical relationship, their orbital periods related by a simple ratio of whole numbers. This isn't coincidence. It's the result of gravitational interactions over billions of years. When the solar system was young and Neptune was migrating outward from its formation point, its gravity swept through the Kuiper belt like an invisible broom, capturing certain objects into resonances and flinging others away. Pluto got captured in the 3-2 resonance, and once trapped there, it stayed there, because resonances are stable. They're gravitational sweet spots where the repeated tugs from Neptune always occur at the same points in Pluto's orbit, reinforcing the pattern rather than disrupting it. This resonance is what protects Pluto from ever colliding with Neptune, despite crossing Neptune's orbital path. When Pluto is at perihelion, its closest point to the Sun inside Neptune's orbit, Neptune is always far away, on the opposite side of the Sun. The resonance ensures they never get close. In fact, at their nearest approach, Pluto and Neptune are separated by at least 17 astronomical units, about 2.5 billion kilometers. That's farther than the distance from the Sun to Uranus. They're not even remotely close to colliding. The mathematics of resonance are beautiful. Imagine 2 dancers spinning around a central point at different speeds, but their steps are perfectly synchronized, so that every time the faster dancer completes 3 turns, the slower dancer completes exactly 2. They meet at the same spot in space at regular intervals, but they never collide because their timing is perfect. That's Pluto and Neptune, dancing for billions of years, perfectly synchronized, never touching. This 302 resonance has persisted for at least several million years, possibly for the entire 4.6 billion year history of the solar system. Computer simulations show it's stable into the far future as well. Pluto and Neptune will likely remain locked in this pattern for billions of years more, until something catastrophic disrupts the solar system. What's remarkable is that Pluto isn't alone. There are approximately 383 other known objects in the Kuiper belt that share the same 3.2 resonance with Neptune. They're called Plutinos, in honor of Pluto being the first one discovered and the largest known member of this family. These Plutinos are Pluto's siblings, in a sense. They all got captured by the same mechanism, all locked into the same gravitational pattern. They all cross Neptune's orbit safely because they all follow the same choreography. Some are just a few kilometers across, barely detectable. Others, like Orcus, are several hundred kilometers in diameter, small worlds in their own right. The existence of so many Plutinos tells us something important about the early solar system. It tells us that Neptune's outward migration was real and significant. It tells us that the Kuiper Belt was much more populous in the past, and that most objects were scattered or ejected. And it tells us that orbital resonances are powerful organizers, corralling thousands of objects into specific patterns that persist across geological time. When you look at Pluto, you're not just seeing one object. You're seeing the representative of an entire population, all bound by the same mathematical relationship to Neptune, all dancing the same slow dance through the outer solar system. 2 orbits for every 3, a simple ratio. But in that simplicity lies billions of years of stability, proof that gravity can be not just a force, but a conductor, organizing the cosmos into patterns that persist longer than worlds. Pluto's orbit is strange. It's tilted 17 degrees relative to the main plane where the 8 planets orbit. It's highly elliptical, stretching from 29.7 AU at perihelion to 49.3 AU at aphelion, and it crosses Neptune's orbital path, even though the 2 worlds never get close to colliding. These orbital characteristics are Neptune's signature, written into Pluto's motion billions of years ago when Neptune migrated outward through the primordial Kuiper Belt. Imagine the early solar system. Neptune formed closer to the Sun, probably around 1520 AU, much nearer than its current position at 30 AU. Then, due to gravitational interactions with Jupiter and Saturn, Neptune began migrating outward. This migration took millions of years, slow by human standards but rapid on geological timescales. As Neptune moved outward, its orbital resonances swept through the Kuiper Belt like invisible nets. The 3-2 resonance, where objects orbit the Sun twice for every 3 times Neptune orbits, caught Pluto and hundreds of other objects, dragging them outward along with Neptune's migration. But resonances don't just move objects outward. They also pump up their orbital eccentricity and inclination. Each time Pluto passed near Neptune, or more accurately, each time the resonance gave Pluto a gravitational nudge, its orbit became slightly more elliptical and slightly more tilted. Over millions of years, these small nudges accumulated. Pluto's orbit, which may have started relatively circular and flat, became stretched into its current ellipse and tilted to its current 17-degree inclination. Neptune sculpted Pluto's orbit through repeated gravitational interactions, leaving its fingerprints in the orbital elements. This process happened to all the Plutinos. They all have eccentric inclined orbits because they all underwent the same process of resonant migration. Some have inclinations even more extreme than Pluto's, up to 30 degrees or more, depending on exactly how their interaction with Neptune played out. The fact that we can still read this ancient history in Pluto's orbit is remarkable. Billions of years have passed since Neptune's migration, but the evidence remains. Orbital mechanics are written in mathematics that doesn't erode or decay. The tilt and eccentricity that Neptune imposed on Pluto's orbit 4 billion years ago are still there today, unchanged, like a fossil preserved in stone. And we can run the process backward. Computer simulations can take Pluto's current orbit, remove the influence of Neptune's migration, and estimate what Pluto's orbit might have looked like before. The answer: probably more circular, probably less inclined, probably farther from the Sun than it is now. Pluto was pushed inward and stirred up by Neptune's passage. Its original orbit was quieter, more stable, more typical of a Kuiper Belt object. Neptune made it weird, made it cross planetary orbits, made it stand out. So when we look at Pluto's strange orbital characteristics, the 17-degree tilt, the elliptical path, the resonance with Neptune, we're not seeing quirks. We're seeing history. We're seeing the signature of ancient gravitational interactions. The mark left by a planet that once passed through this region and rearranged everything. Neptune shaped Pluto's orbit, and that orbit, in turn, has shaped Pluto's history, determining how much sunlight it receives, how its seasons work, when its atmosphere thickens and thins. Everything about Pluto today traces back to that ancient encounter, that reshaping of the Kuiper Belt by a migrating ice giant. The cosmos remembers. And sometimes, if you know how to read orbital mechanics, you can hear it tell you stories about what happened billions of years ago, when the solar system was young and violent and still rearranging itself into the configuration we see today. Pluto didn't form where it is now. Computer models suggest it originally coalesced somewhere between 15 and 35 AU from the Sun, closer to where Neptune is today, or even closer to Uranus. This might seem strange at first. Why would Pluto form closer to the Sun and then end up farther away? Shouldn't objects generally stay where they formed? In a stable solar system, yes, but the early solar system wasn't stable. It was chaotic, dynamic, constantly rearranging itself as the giant planets grew, and their gravitational influences reshaped everything around them. Neptune's migration pushed Pluto outward. As Neptune moved from its formation location around 1520 AU to its current position at 30 AU, the 3.2 resonance swept through the region where Pluto orbited. When the resonance caught Pluto, it began dragging Pluto along, gradually increasing its average distance from the Sun. This process took time, perhaps tens of millions of years. Pluto didn't jump suddenly from 25 AU to 40 AU. Instead, each orbit, each interaction with Neptune's resonance, nudged it slightly outward. The semi-major axis of its orbit crept slowly larger, decade by decade, millennium by millennium, until Pluto settled into the orbital configuration we see today. The evidence for this is written in Pluto's composition. Objects that formed farther from the Sun should be more ice-rich, while objects that formed closer should have more rock. Pluto's 70% rock, 30% ice composition suggests it formed in a region where temperatures were warm enough that not all water froze immediately, probably somewhere in the 1530 AU range. If Pluto had formed at its current distance of 40 AU, it would likely be more ice-rich, similar to some of the smaller, more distant Kuiper Belt objects that have densities closer to pure ice. There's also the question of how Pluto got so large. Forming large objects in the outer solar system is difficult because the material is spread so thinly. The farther from the Sun, the less dense the protoplanetary disk, and the longer it takes for objects to grow through accretion. At 40 AU, the disk was probably too thin for an object of Pluto's size to form before the gas in the solar system dissipated, which happened within the first 10 million years. But closer in, around 2030 AU, conditions were more favorable. The disk was denser, collisions were more frequent, and large objects could grow more quickly. So Pluto probably formed closer, grew to roughly its current size, and then was pushed outward by Neptune's migration. It's a migrant, a refugee from the inner Kuiper belt, now residing in the outer region, where conditions are colder and more isolated than where it began. This migration explains something else about Pluto, why it's so different from the objects around it. Most classical Kuiper belt objects, the ones in circular, low-inclination orbits between 42-48 AU, are smaller than Pluto and have different compositions. They probably formed where they are now, in situ, growing slowly in the thin outer disk. But Pluto came from elsewhere. It formed in a different environment, under different conditions, and then got transported outward to where it currently resides. It's an immigrant to the outer Kuiper belt, which explains why it stands out, why it's larger and denser than most of its neighbors. The journey took millions of years. Pluto drifted outward, pushed by Neptune's resonance, gradually settling into its current orbit around 40 AU. And there it has remained for the past 4 billion years, orbiting in the place Neptune put it, far from where it was born. There's something poignant about that, isn't there? Pluto began its existence closer to the Sun, in a warmer, more dynamic region. Then it was exiled outward, pushed to the cold frontier, where it has orbited ever since, disconnected from its birthplace, residing in a region that wasn't originally its home. Migration is a fundamental process in planetary systems. We see it in exoplanet systems, where hot Jupiters orbit impossibly close to their stars. They formed farther out and migrated inward. We see it in our own solar system, where all 4 giant planets probably migrated significantly from their formation locations. And we see it in Pluto, a small world that formed in the middle distance and was pushed to the outer darkness, where it became the king of the Kuiper belt, ruling over a realm that wasn't its original home. Modern theories suggest Pluto didn't form the way we once thought most planets form, through the slow accumulation of small particles gradually sticking together, growing from dust to pebbles, to boulders, to planetesimals over millions of years. Instead, Pluto may have formed through a process called streaming instability, where millimeter-sized ice particles in the protoplanetary disk suddenly collapsed directly into large objects, condensing abruptly from a cloud of material into a solid world. Think of it like this. Imagine a room full of fog so thick you can barely see. Then suddenly all the water vapor in one corner condenses simultaneously into raindrops, leaving that region clear while the rest remains foggy. That's analogous to what streaming instability does. It causes regions of the protoplanetary disk to suddenly collapse into solid objects. The process works because of a feedback loop. When small particles in the disk concentrate slightly, perhaps due to turbulence or pressure variations, their collective gravity starts to become significant. This enhanced gravity pulls in more particles, which increases the gravity further, which pulls in even more particles. The process accelerates, becoming unstable, and within just a few orbits around the Sun, a huge swarm of small particles collapses into a single large object. Instead of taking millions of years to grow from dust to planet, streaming instability can create objects tens or even hundreds of kilometers across in just a few hundred or thousand years. It's remarkably fast by geological standards, almost instantaneous. Evidence from New Horizons supports this formation mechanism for Pluto. The The relative lack of small craters on Pluto's ancient surfaces suggests that the Kuiper Belt formed with fewer small objects than traditional models predict. If planets grew slowly through gradual accumulation, there should be a population of objects at all size scales, from kilometer-sized to Pluto-sized. But we don't see that. We see a deficit of small objects. This is exactly what streaming instability predicts. Objects would form already large, born as planetesimals tens of kilometers across rather than dust grains. There would never be a large population of small objects because the small particles went directly into making large objects without spending time as intermediate-sized bodies. Pluto then might have condensed from a cloud. Billions of icy particles, each less than a millimeter across, orbiting the Sun in a dense swarm. Then, triggered by some perturbation, perhaps a density wave in the disk, perhaps simple turbulence, the swarm began to collapse. Gravity took over. Within a few orbits, maybe a few centuries at most, the cloud condensed into a solid body, Proto-Pluto, already large, already massive enough to be spherical. It's like cosmic rain forming a frozen pond. The particles were always there, orbiting, waiting. Then conditions aligned, instability triggered, and suddenly there was a world where before there had only been a cloud. This process might sound exotic, but it's probably how most Kuiper Belt objects formed. The outer solar system was cold enough and dense enough with ices that streaming instability could operate efficiently. Objects would form in sudden bursts of creation rather than gradual growth, and once formed, these objects didn't change much. Small bodies in the outer solar system don't get hot enough to melt completely. They might differentiate partially, might develop layered interiors, but they retain much of their original structure and composition. So when you look at Pluto, you might be seeing something that condensed from a cloud 4.6 billion years ago and has remained largely unchanged since. A frozen snapshot of the moment of its birth, preserved by the cold and isolation of the outer solar system. Born from a cloud, condensed in an instant, frozen in time. That's one way to think about Pluto's origin story. When New Horizons captured high-resolution images of Pluto's surface, scientists noticed something surprising. There weren't as many small craters as they expected. Impact craters form when objects from space collide with a planetary surface. The size distribution of craters tells us about the size distribution of impactors. Large craters come from large impactors, small craters from small ones. If the Kuiper Belt contains objects at all size scales, from kilometer-sized chunks up to Pluto-sized worlds, then Pluto's surface should show craters at all scales too. But it doesn't. There's a deficit of small craters, fewer than models predicted should exist. This observation has profound implications for understanding how the Kuiper Belt formed. It suggests that there never were large numbers of small objects. The population of Kuiper Belt objects formed already large, without a substantial population of small bodies that would have created small craters through impacts over billions of years. This is consistent with the streaming instability formation mechanism. If Kuiper Belt objects formed by directly collapsing from clouds of small particles, they would be born large, tens of kilometers across at minimum. There would never be a phase where the region contained many small, kilometer-sized bodies, because those small particles went directly into making the larger objects. Of course, some of Pluto's surfaces show no craters at all because they're geologically young. They've been resurfaced within the last few 100 million years, or even more recently. Sputnik Planitia, the western lobe of the heart, is essentially crater-free because the nitrogen ice convects, constantly churning and erasing any impact scars. But even on Pluto's ancient surfaces, regions that appear to be billions of years old, based on their crater density, the small craters are missing. This tells us something about the primordial Kuiper belt, about the population of objects that existed there when Pluto's surface was young and vulnerable to impacts. There's another possible explanation, though it's less favored. Perhaps small objects existed, but were ejected from the Kuiper belt during Neptune's migration. If Neptune's gravitational scattering preferentially removed small objects while leaving large ones behind, that could also explain the crater deficit. But this seems less likely because gravitational scattering doesn't strongly depend on object size in the relevant range. Objects a kilometer across and objects 100 kilometers across should be ejected at roughly similar rates. So the selective removal of small objects would require some additional mechanism. The most straightforward explanation remains that small objects were rare from the beginning. The Kuiper belt formed with objects already large, born from streaming instability rather than gradual accumulation. Pluto's cratering record, or lack thereof at small scales, is evidence for this process. It's remarkable what you can learn from what's missing. The absence of small craters tells us as much about Kuiper belt formation as the presence of large ones. Negative evidence can be just as important as positive evidence when you're trying to reconstruct the past. Pluto's surface remembers the population that bombarded it billions of years ago. And that memory suggests a Kuiper belt born already large, already sorted into objects tens to thousands of kilometers across, without a substantial population of small bodies to create small impacts. The missing craters are ghosts of objects that never existed, evidence of a formation process that skipped the usual steps and went directly from dust to worlds. Pluto's orbit is inclined 17 degrees relative to the ecliptic, the plane where Earth and most other planets orbit. This is more extreme than any of the 8 planets. Mercury has the next highest inclination at just 7 degrees. Most planets orbit within a few degrees of the same plane, all aligned because they formed from the same flat protoplanetary disk. But Pluto is tilted far out of that plane. For most of its orbit, it travels above or below where the planets are, spending time in regions of space the planets never visit. This inclination is Neptune's signature, like the eccentricity we discussed earlier. When Neptune migrated outward and its resonances swept through the Kuiper belt, those resonances didn't just push objects outward and make their orbits more elliptical. They also pumped up their inclinations, tilting their orbits relative to the original plane. The process is called resonant pumping, and it happens because the gravitational kicks from the resonance don't always act in the plane of the orbit. Each time Pluto receives a resonant perturbation from Neptune, there's a small component that tilts its orbit slightly. Over millions of years, these small tilts accumulate into significant inclinations. Different objects ended up with different inclinations depending on exactly how their interaction with Neptune played out. Some Plutinos have inclinations of 20 or even 30 degrees, even more extreme than Pluto. They're on highly tilted orbits, looping far above and far below the plane where the planets orbit. This inclination means that Pluto spends most of its time above or below the plane of the solar system. At its highest point, it's about 1.2 billion kilometers above the ecliptic. At its lowest point, it's 1.2 billion kilometers below. That's 8 times farther from the plane than Earth ever gets. From Pluto's perspective, the solar system would look different than it does from Earth. The planets wouldn't all be clustered along a line, the zodiac constellation band that we see from Earth. Instead, some would be above Pluto, some below, scattered across different parts of the sky because Pluto is looking at the solar system from a tilted vantage point. The steep inclination also affects Pluto's seasons in subtle ways. Because Pluto's axial tilt is 120 degrees and its orbital inclination is 17 degrees, the relationship between Pluto's seasons and its distance from the Sun is complex. Sometimes Pluto's north pole points toward the Sun when it's at perihelion, sometimes when it's at aphelion, depending on where Pluto is in its slow orbital precession. This creates long-term climate cycles that span thousands of years, patterns in how much sunlight different regions of Pluto receive, averaged over many orbits. These cycles might drive very long-term changes in Pluto's geology and atmosphere, changes that occur on timescales much longer than a single Pluto year. The 17-degree inclination is part of what makes Pluto an outlier. Combined with its elliptical orbit and small size, this tilt marked it as different from the 8 planets, as something that didn't quite fit the pattern. Now we understand that this difference is diagnostic. It tells us that Pluto is a Kuiper belt object, that it underwent Neptune's scattering, that it has a different origin story than the planets closer to the Sun. The tilt is a scar, written in orbital elements, evidence of ancient violence when the solar system reorganized itself and scattered most of the Kuiper belt into chaos. Pluto survived that violence, but it carries the mark of it still in the 17-degree angle that tilts it out of the plane where planets belong. We can predict Pluto's position millions of years into the future with reasonable accuracy. Computer simulations can integrate the equations of motion for all the planets and major Kuiper belt objects, calculating where everything will be in 1 million years, 10 million years, even 100 million years. But beyond about 10 to 20 million years, the calculations become unreliable. Not because our equations are wrong or our computers are too slow, but because the solar system is chaotic. Chaos, in the mathematical sense, means that tiny differences in initial conditions lead to enormous differences in outcomes over time. If you start 2 simulations of Pluto's orbit with positions that differ by just a few meters, a completely unmeasurable difference given Pluto's distance, those 2 simulations will predict drastically different positions after 20 million years. This happens because planetary orbits are coupled. Every planet affects every other planet through gravity. These effects are usually small. Earth's gravity barely affects Pluto, and vice versa. But over millions of years, small effects accumulate. And because the planets are in resonances and near resonances with each other, these effects don't average out. They build up in complex nonlinear ways. The mathematics of chaos were discovered partly through studying planetary orbits. In the 1880s, Henri Poincaré proved that the 3-body problem, predicting the motion of 3 gravitationally interacting objects, has no general closed-form solution. The orbits are deterministic in the sense that the equations are precise, but they're unpredictable in practice because tiny uncertainties grow exponentially over time. The solar system has 8 planets, 5 dwarf planets, millions of asteroids, and countless other objects. It's vastly more complex than the three-body problem. That it remains stable and predictable for millions of years is remarkable. But beyond that timescale, chaos wins. This doesn't mean Pluto will suddenly fly out of the solar system or crash into Neptune. The chaos is bounded. Pluto will remain in approximately the same region of space, orbiting at roughly the same distance. But its exact position, the phase of its orbit, when it reaches perihelion versus aphelion, these details become unknowable beyond the chaotic timescale. There are also quantum limits to predictability, though these are much farther out. The uncertainty principle means that we can't simultaneously know both the exact position and exact momentum of any object. For something as massive as Pluto, these quantum uncertainties are vanishingly small, but they exist, and over extremely long timescales, trillions of years, even quantum uncertainties might become significant. In practice, the classical chaos dominates long before quantum effects matter. After 20 million years, we lose the ability to predict Pluto's exact orbit. We can make statistical statements. Pluto will probably still be in the Kuiper belt, probably still in resonance with Neptune, but we can't say precisely where it will be. This is a humbling realization. Even in the clockwork universe described by Newton's laws, even with perfect equations and infinite computational power, there are fundamental limits to prediction. The future is not just unknown, it's unknowable, not because of limitations in our knowledge, but because of the intrinsic properties of dynamical systems. Pluto's distant future is fundamentally uncertain. It will continue orbiting, continue its slow dance with Neptune, continue following the laws of gravity. But exactly where, exactly when, exactly how? These details are lost in the chaos of gravitational interactions, hidden behind a veil of mathematical impossibility. Even in the cosmos, some things remain mysteries not because we haven't looked hard enough, but because they're genuinely unknowable. And maybe there's something beautiful about that, about limits to knowledge, about a universe that refuses to be completely predictable, about a future that remains open even for a world as ancient and patient as Pluto. Pluto's most famous feature is a giant heart-shaped region called Tombaugh Regio, nearly 1,000 miles across, about the size of Texas and Oklahoma combined. When the first high-resolution images from New Horizons appeared in July 2015, this heart captured the world's imagination instantly. It was named after Clyde Tombaugh, the man who discovered Pluto 85 years earlier. There's something fitting about that, the discoverer's name written across Pluto's most prominent feature, visible in the images that finally showed us what this distant world actually looks like. But the heart is more than just a charming shape. It's a window into Pluto's geology, its climate, its history. The western lobe of the heart, the left ventricle, if you will, is a region called Sputnik Planitia, and it's one of the most scientifically significant features in the entire outer solar system. Sputnik Planitia is a basin, probably an ancient impact crater filled with nitrogen ice several kilometers deep. It's the largest known glacier in the solar system, not just on Pluto, but anywhere. All of Earth's glaciers combined would fit inside Sputnik Planitia with room to spare. The eastern lobe of the heart, the right side, is geologically different. It consists of highland terrain covered in reddish tholins, those complex organic molecules that form when sunlight breaks down methane. This region is called Cthulhu Macula informally, named after the cosmic horror entity because of its dark, ancient, slightly menacing appearance. The contrast between the two lobes is striking. The western side is brilliant white, the brightest region on Pluto's entire surface, reflecting 90% of the sunlight that hits it. The eastern side is dark reddish-brown, absorbing most sunlight, ancient and heavily cratered. They sit next to each other, two completely different geological provinces, forming this heart shape that humans find so emotionally resonant. Why is it heart-shaped? Pure coincidence, most likely. The basin of Sputnik Planitia happens to have a particular outline, and the highland terrain happens to abut it in a way that creates this recognizable form. Pareidolia, our tendency to see familiar patterns in random shapes, does the rest. But coincidence or not, the heart became iconic immediately. It transformed Pluto from an abstract dot in telescopes to a world with character, with personality, with something that felt almost intentional. People who had never cared about astronomy suddenly cared about Pluto because of that heart. And perhaps that's appropriate, because Pluto has always been the dwarf planet, that captured hearts, the underdog, the distant one, the misfit that didn't quite belong. Seeing it literally wear a heart on its surface felt like confirmation of something people had always sensed, that Pluto was special, was worth caring about, was more than just a cold rock at the edge of the solar system. The heart is not just a feature, it's a symbol. It represents everything that makes Pluto fascinating: the unexpected geology, the active processes, the refusal to be a boring, dead, frozen world. It's Pluto announcing itself to humanity after 85 years of waiting. Here I am. I'm beautiful. I'm strange. I'm worth the journey you took to see me. And we saw it, and we fell in love. Sputnik Planitia, the western lobe of Pluto's heart, is an ancient impact basin approximately 1,000 kilometers across and several kilometers deep, completely filled with nitrogen ice. This isn't a thin coating. This is a massive accumulation of frozen nitrogen, so deep that if you could somehow stand at the bottom and look up, you'd be buried under 3 or 4 kilometers of ice. That's deeper than the deepest ocean trenches on Earth are underwater. The volume of nitrogen ice in Sputnik Planitia is staggering. Estimates suggest approximately 10 million cubic kilometers of ice, enough to cover the entire Earth's surface in a layer 20 meters thick. It's the single largest known glacier in the entire solar system, dwarfing anything on Earth or Mars or Enceladus. Where did all this nitrogen come from? Partly from local deposition, nitrogen sublimating from sunlit areas and condensing in the cold basin. But mostly, scientists think, it accumulated over billions of years from Pluto's atmosphere. As nitrogen sublimates from various parts of Pluto's surface and circulates through the thin atmosphere, much of it eventually ends up condensing in Sputnik Planitia, because the basin is lower in elevation and slightly colder than surrounding terrain. This creates a feedback loop. More nitrogen ice means more mass, which means stronger local gravity, which means more atmosphere is drawn toward the basin, which means more nitrogen condenses there, which means even more mass. Over geological time, Sputnik Planitia has become a cold trap, the low point where nitrogen accumulates preferentially. The basin is so massive that it has actually affected Pluto's entire orientation. The concentration of all that nitrogen ice, which is denser than the water ice beneath it, created a mass excess, a heavy spot on Pluto's surface. Over time, Pluto reoriented itself so that this mass excess moved toward the equator, facing almost directly opposite to Charon. This process is called true polar wander. The whole planet tipped on its axis, rotating its crust relative to its interior, to minimize rotational energy by putting the heavy mass near the equator. Evidence of this reorientation is written in fracture systems that crisscross Pluto's surface, stress marks from when the planet's crust shifted relative to its interior. So Sputnik Planitia is not just a glacier. It's a geological force powerful enough to tip an entire world on its axis. It's a reservoir containing a significant fraction of Pluto's mobile nitrogen. It's a climate engine that drives atmospheric circulation. And it's one of the youngest surfaces in the solar system, constantly resurfacing itself through convection. The name Sputnik was chosen to honor the first artificial satellite, launched in 1957, 8 years before New Horizons was conceived, 48 years before New Horizons launched, 58 years before New Horizons revealed this feature. It's a reminder of how long the journey to Pluto took, how many decades of spaceflight history passed between humanity's first steps into space and our arrival at the solar system's edge. And Planitia just means plain, a flat, low-lying area. Sputnik Planitia, the Sputnik Plain, the largest glacier in the solar system, named after humanity's first satellite, sitting in Pluto's frozen heart. Sputnik Planitia has absolutely zero craters. None. Not one impact scar visible in the highest resolution images New Horizons captured. This is extraordinary. Every exposed surface in the solar system accumulates impact craters over time as asteroids, comets, and debris strike it. The older the surface, the more craters it should have. Heavily cratered terrain is ancient, sometimes billions of years old. Lightly cratered terrain is younger, perhaps hundreds of millions of years. And completely uncratered terrain is extremely young. Geologically speaking, it formed yesterday. Sputnik Planitia formed yesterday. Scientists estimate that some regions of the basin may be only 180,000 years old. Other parts might be up to 10 million years old at most. But all of it is recent by planetary standards, formed while modern humans existed, or at least while our evolutionary lineage was well established. This means Sputnik Planitia is being actively resurfaced right now. Something is erasing craters as fast as they form, or faster, and that something is convection. The nitrogen ice in Sputnik Planitia is convecting like a lava lamp, driven by heat from Pluto's interior. Warm ice rises from below, spreads across the surface, cools, and sinks back down. This circulation constantly renews the surface, erasing any impact craters that form. The timescale for this process is extraordinarily slow by human standards. One complete convection cycle, ice rising from the bottom, spreading across the surface, cooling and sinking back down, takes approximately 500,000 years. But that's fast enough, over millions of years, to erase all crater evidence. And because this process is ongoing, active, happening right now, Sputnik Planitia's surface age is essentially zero in the regions where convection is most vigorous. The ice you see in New Horizons images might have been at the bottom of the basin just a few 100,000 years ago. It will be at the bottom again in another few 100,000 years. This makes Sputnik Planitia one of the most geologically active surfaces in the outer solar system. It's comparable to Jupiter's moon Io, which is constantly resurfaced by volcanic eruptions, or Saturn's moon Enceladus, which has active geysers spraying material into space. Pluto, small and distant and supposedly dead, is doing something similar with ice instead of lava. The lack of craters tells us that Pluto is not a frozen, inactive world. It has an active interior, still warm enough, after 4.6 billion years, to drive convection in the near-surface ice. It has geological processes operating today that reshape its surface on timescales short compared to the age of the solar system. When New Horizons scientists saw the first high-resolution images of Sputnik Planitia and realized there were no craters, the room erupted in excitement and disbelief. Every prediction, every model, every expectation about what Pluto should look like was wrong. They expected ancient, dead, heavily cratered terrain. They got a surface younger than many lava flows on Earth, being actively resurfaced by processes they didn't predict. Sputnik Planitia should not exist, not on a world as small and cold as Pluto, not this far from the Sun, not after billions of years. But it does exist, and its existence means we fundamentally misunderstood what's possible in the outer solar system. At room temperature, nitrogen is a gas. It makes up 78% of Earth's atmosphere. Cool it down to 210°C and it becomes a liquid. Cool it further to 216°C and it freezes into a solid. But Pluto's surface temperature is around 230°C, which is only about 14 degrees colder than nitrogen's freezing point. This means nitrogen ice on Pluto is close to its melting point, the way ice on Earth at 0 degrees C is close to melting into water. And when ice is close to its melting point, it behaves strangely. It's still solid. You could walk on it without breaking through, but it flows, very slowly, glacially, you might say, except even more slowly than Earth's glaciers. Nitrogen ice on Pluto flows like extremely thick honey. Over decades and centuries, it deforms under its own weight, spreading out from high areas toward low areas, seeking gravitational equilibrium. Over millennia, it flows down valleys and into basins. Over millions of years, it convects, rising and sinking in slow circulation cells. This happens because molecules near the melting point have enough thermal energy to break their bonds with neighboring molecules and slide past each other. The ice is still crystalline, still ordered at the molecular level, but the crystals can rearrange themselves. It's like a crowd of people standing closely together. Everyone maintains their position relative to immediate neighbors, but the crowd as a whole can slowly flow and shift. The convection cells in Sputnik Planitia are driven by this flow. Warm nitrogen ice at the bottom of the basin, heated by geothermal warmth from Pluto's interior, becomes slightly less dense than the colder ice above it. Density differences create buoyancy forces. The warm ice begins rising slowly, pushing upward through kilometers of overlying ice. When it reaches the surface, it spreads horizontally, forming a broad dome a few tens of meters high. As it spreads, it cools, radiating heat into space, losing thermal energy. The cooling makes it denser. Eventually, it becomes dense enough to sink again, creating downwelling currents at the edges of the convection cell. The result is a pattern of polygonal cells, 10 to 40 kilometers, Across, visible in New Horizons images as a surface texture, like enormous bathroom tiles. The centers of the cells are slightly raised where warm ice is upwelling. The edges are slightly depressed where cool ice is downwelling. This pattern is similar to convection patterns seen in Earth's lava lakes, where molten rock circulates beneath a solid crust. It's similar to convection in Earth's mantle, where hot rock rises and cool rock sinks over millions of years. The physics is the same, just the materials and timescales are different. The ice moves at about 7 centimeters per year, roughly the speed your fingernails grow. Fast enough to matter over geological time, slow enough that you'd never perceive it directly, even if you could stand there and watch for decades. This flowing, convecting behavior is what keeps Sputnik Planetia's surface young and crater-free. Any impact that creates a crater is gradually erased as the surrounding ice flows into the depression, filling it in. After a few 100,000 years, the crater is gone, smoothed away by the patient flow of nitrogen ice, solid material acting like liquid, ice flowing like honey, a surface that's technically frozen but behaves like it's molten. This is the strange physics of materials near their melting point, operating on a world where temperatures and pressures are utterly alien to human experience. The surface of Sputnik Planitia is divided into polygonal cells, each one 10 to 40 kilometers across. These cells fit together like tiles on a bathroom floor, with raised centers and depressed boundaries forming a distinctive pattern visible in New Horizons images. These are convection cells. They're the surface expression of nitrogen ice circulation happening kilometers below. Imagine a cross-section through Sputnik Planitia. At the bottom, several kilometers down, nitrogen ice sits on top of water ice bedrock. Heat from Pluto's interior, residual warmth from formation, plus heat from radioactive decay in the rocky core, slowly conducts upward through the water ice and into the nitrogen ice above. This heat warms the bottom layer of nitrogen ice. Warmer ice is less dense than colder ice. Molecules vibrate more, taking up slightly more space. The warm ice at the bottom becomes buoyant, lighter than the colder ice above it. Buoyancy drives motion. The warm ice begins rising, forming a plume that pushes upward through the overlying layers. This ascent takes hundreds of thousands of years. The ice moves slowly, just centimeters per year, but it's persistent. Eventually, the rising plume reaches the surface. At the surface, the warm ice spreads horizontally, forming the raised center of a convection cell. As it spreads, it's exposed to the extreme cold of Pluto's environment, temperatures around 230 giga, and the vacuum of space overhead. The ice radiates heat into space and cools rapidly. Cooling increases its density. The ice becomes heavier. After spreading across several kilometers, having cooled sufficiently, it becomes denser than the ice below it. Now gravity pulls it downward. It sinks, creating downwelling currents at the edges, where adjacent cells meet. The downwelling ice descends back toward the bottom of the basin, completing the circulation loop. As it descends, it gradually warms again from geothermal heat. Eventually, it becomes buoyant and begins rising, starting the cycle over. One complete cycle takes approximately 500,000 years. Think about that. The ice at the center of a convection cell might have been at the bottom of the basin 250,000 years ago, when Neanderthals still existed on Earth. It will be at the bottom again in another 250,000 years, long after human civilization has either transformed beyond recognition or ceased to exist. This is what we mean by geological timescales. Processes too slow to perceive directly, but fast enough to reshape landscapes over the age of species. The pattern of cells changes over time too. Computer models suggest that cells merge and split, that their boundaries shift, that the configuration we see today will look different in 1,000,000 years. The surface is dynamic, constantly reorganizing itself, driven by the patient circulation of ice. It's remarkably similar to a lava lamp. You know the kind, colored wax floating in liquid, heated from below, rising and falling in slow cycles. The physics is identical. Warm material rises, cools, sinks. The difference is that lava lamps cycle in minutes, while Sputnik Planitia cycles in 500,000 years. But the fundamental process, thermal convection, is the same. Pluto is a cosmic lava lamp, frozen in ultra-slow motion, circulating nitrogen ice in a pattern that will continue for billions of years, long after the sun expands into a red giant and the solar system as we know it comes to an end. In the images of Sputnik Planitia, you can see something unexpected along the boundaries of the convection cells. Chunks of material that look different from the surrounding nitrogen ice. These chunks are darker, more irregular, and they seem to be floating at the edges where convection cells meet. They're icebergs. But not water icebergs floating in water. These are water ice icebergs floating in nitrogen ice. At Pluto's temperatures around 230 degrees C, water ice is less dense than nitrogen ice. This is opposite to the situation on Earth, where ice floats in liquid water because solid water is less dense than liquid water. But on Pluto, solid water ice is less dense than solid nitrogen ice, which means water ice floats in nitrogen, or more accurately, water ice floats on nitrogen ice, because the nitrogen is solid too. But the nitrogen is flowing, convecting, behaving like an extremely viscous fluid on geological timescales. And in that slowly flowing nitrogen, chunks of water ice bob around like icebergs in a frozen sea. These water ice blocks probably originated as mountains or hills in the highlands surrounding Sputnik Planitia. Over time, as the basin filled with nitrogen ice, some of these topographic features were surrounded and eventually broken off by the flowing nitrogen. Now they drift with the convection currents, carried along by the circulation cells. They collect at the cell boundaries because that's where the downwelling currents are, where cool nitrogen ice sinks back down. The icebergs can't sink because they're less dense than the nitrogen. So they accumulate at the downwelling zones, piling up like foam at the edges of a coffee cup, where the liquid circulates. Some of these icebergs are enormous. Several are 10 to 20 kilometers across, roughly the size of Manhattan. They dwarf anything we'd call an iceberg on Earth. And they've been floating there, drifting with Pluto's ice circulation for potentially millions of years. The existence of these icebergs tells us several things. First, it confirms that the nitrogen ice really is flowing. The icebergs have clearly moved from their original positions. Second, it tells us that water ice and nitrogen ice are separate materials on Pluto with different densities and properties. And third, it gives us a way to measure the convection. By tracking where icebergs are located, we can map the boundaries of convection cells and understand the pattern of circulation. There's something almost poetic about it, isn't there? Icebergs drifting in frozen seas, floating on ice that flows like liquid, carried by currents that take 500,000 years to complete one cycle. It's like some kind of ultra slow motion ocean, where everything that happens quickly on Earth, waves, currents, drifting, happens on Pluto too, just stretched out over timescales that make glaciers look fast. If you could somehow stand on one of these water ice icebergs and watch for a few hundred years, you might notice that you're moving, very slowly, drifting with the nitrogen ice beneath you, carried by convection currents you can't see, floating in a sea that's technically solid but behaves like thick syrup over long enough timescales. The icebergs of Pluto drift in seas made of frozen air, on a world where the distinction between solid and liquid loses its usual meaning, where patience is measured in millennia and motion is measured in centimeters per year. Along the edges of Sputnik Planitia and scattered across other regions of Pluto, there are mountains. Not small hills, actual mountains rising 11,000 feet above the surrounding terrain. That's about 3,400 meters, comparable to peaks in the Canadian Rockies or the Alps. These mountains are made entirely of water ice. On Earth, mountains are made of rock, granite, basalt, limestone, rocks that are hard and strong enough to support their own weight against gravity. You couldn't make a mountain out of ice on Earth because ice isn't strong enough at Earth's temperatures. It would flow and collapse under its own weight. But on Pluto, at temperatures around 230 degrees C, water ice is as hard and strong as granite. It doesn't flow on timescales shorter than millions of years. It can support vertical cliffs, angular peaks, rugged topography, all the features we associate with rocky mountains. Water ice is Pluto's bedrock, its structural material, the substance that forms the permanent geological foundation beneath the more volatile ices like nitrogen and methane. The mountains around Sputnik Planitia are particularly impressive. They form blocky, angular peaks, some isolated, some clustered in ranges. They have steep sides and sharp ridges, features that suggest they're geologically young. If they were ancient, billions of years of micrometeorite impacts and cosmic ray weathering would have softened their features. How did these mountains form? The most likely explanation is that they're blocks of Pluto's water ice crust that have been pushed upward by geological processes, perhaps by the convection in Sputnik Planitia itself. The enormous mass of nitrogen ice creates stresses in the surrounding crust, causing it to buckle and fracture, lifting blocks of water ice into mountains. Or perhaps they formed earlier, during a time when Pluto's interior was warmer and more geologically active. Tectonic processes could have thrust these mountains upward, creating the topography we see today. Either way, they stand as testament to the fact that water ice, despite being a substance we think of as temporary and fragile, can be as permanent and solid as any rock when conditions are cold enough. Some of these mountain peaks wear caps of methane snow. Unlike Earth, where snow forms from water vapor condensing in the cold upper atmosphere, Pluto's atmosphere has a temperature inversion. It's actually warmer at altitude than at the surface due to a methane greenhouse effect. This creates a unique situation where methane concentrates in the warmer upper atmosphere and then condenses directly onto mountain peaks that extend into that warmer air. Any peak above about 1 mile elevation will have methane frost on top, creating bright white caps that look remarkably like Earth's snow-capped mountains, even though the process creating them is completely different. So Pluto has mountains made of water ice, capped with methane ice, rising out of plains of nitrogen ice, under a sky that's technically an atmosphere but so thin you'd consider it vacuum. It's a landscape built from materials that are gases on Earth, arranged into forms that look almost familiar, until you remember where you are and what everything is made of. Mountains on Pluto will stand for billions of years. Water ice at those temperatures doesn't erode the way rock does on Earth. There's no liquid water, no freeze-thaw cycles, no chemical weathering. Just the slow grinding of micrometeorite impacts and the patient deposition of frost. The peaks you see in New Horizons images might stand essentially unchanged until the sun becomes a red giant and vaporizes everything. Southwest of Sputnik Planitia, there are two enormous dome-shaped mountains, unlike anything else on Pluto. They're called Wright Mons and Piccard Mons, and they're tentatively identified as cryovolcanoes, ice volcanoes. Wright Mons is about 4 kilometers high and 150 kilometers wide at its base. Piccard Mons is even larger, rising about 6 kilometers and spanning roughly 200 kilometers. Both have deep depressions at their summits, possible calderas, and both show remarkably few impact craters, suggesting they're geologically young. If they are volcanoes, and the evidence strongly suggests they are, they didn't erupt molten rock. They erupted ice, but not simple water ice. Instead, they likely erupted a slurry mixture of water ice, nitrogen ice, ammonia ice, and methane ice, all mixed together into a paste-like material sometimes called cryomagma. At Pluto's surface temperatures, this mixture would have the consistency of toothpaste. It would ooze out of vents, flow slowly down slopes, and eventually freeze solid into the domes we see today. The eruptions wouldn't be explosive like volcanic eruptions on Earth. There's not enough volatile material to create explosive gas pressure. Instead, they'd be effusive, with material slowly extruding from the summit and piling up around the vent. These would be some of the largest cryovolcanoes in the entire solar system. For comparison, Ahuna Mons on the dwarf planet. Ceres is about 4 kilometers high and was considered a major discovery. Wright Mons and Piccard Mons are comparable or larger, and there are two of them. The existence of cryovolcanoes on Pluto raises immediate questions. Where is the heat coming from? What's driving these eruptions? How recently were they active? Small worlds cool quickly. They have high surface area to volume ratios, which means they radiate heat efficiently. Pluto should have frozen solid billions of years ago, with all geological activity ceasing. Yet here we have evidence of possible cryovolcanism, potentially within the last few 100 million years, or even more recently. The heat source is mysterious. Radioactive decay in Pluto's rocky core generates some heat, but probably not enough to drive volcanism after 4.6 billion years. Tidal heating from Charon is negligible. The two are tidally locked, so there's no ongoing tidal flexing to generate heat. One possibility is that Pluto's interior contains ammonia mixed with water. Ammonia acts as an antifreeze, lowering the melting point of water ice significantly. A water-ammonia mixture might remain liquid at temperatures well below pure water's freezing point, creating a subsurface ocean that could persist to the present day. If such an ocean exists, it might occasionally break through to the surface, erupting as cryomagma and building these dome-shaped mountains. The ammonia would help keep the material liquid or slushy during eruption, allowing it to flow before freezing solid. Another possibility involves clathrate compounds, cage-like. structures where one type of molecule traps another. Methane clathrate, where methane is trapped inside a lattice of water ice, can store significant energy. If these clathrates break down, perhaps triggered by stress changes or temperature variations, they could release enough energy to drive cryovolcanic eruptions. The surfaces of Wright Mons and Piccard Mons appear young. They have far fewer craters than the ancient terrain surrounding them. This suggests they were active relatively recently, perhaps within the last 200 million years, possibly much more recently. Could they still be active today? It's possible, though we have no direct evidence of ongoing eruptions. New Horizons flew past too quickly to observe any changes. But if these volcanoes erupted as recently as 1 million years ago, a blink of an eye in geological terms, they might erupt again. The idea of active ice volcanoes on Pluto, slowly oozing frozen slurry onto the surface, reshaping the landscape over millions of years, is both alien and fascinating. It's geology operating with completely different materials than on Earth, but following the same fundamental principles. Heat drives convection, pressure drives eruptions, and material flows from hot regions toward cold. Pluto might still be geologically alive, building new mountains while we watch, adding material to its surface through processes we're only beginning to understand. In several locations on Pluto, New Horizons images revealed something unexpected. Dune fields, long, regular ridges of material, spaced about 400 to 1,000 meters apart, stretching across plains and valleys. They look exactly like sand dunes on Earth or Mars, parallel ridges with gentle windward slopes and steeper leeward slopes, aligned perpendicular to the wind direction. But they're not made of sand. They're made of methane ice grains, each grain about 200 to 300 micrometers across, roughly the size of table salt crystals. The existence of dunes on Pluto is surprising, because dune formation requires wind, and Pluto's atmosphere is incredibly thin, about 100,000 times less dense than Earth's atmosphere at sea level. That's basically vacuum by Earth standards. How can winds in such a thin atmosphere move particles and form dunes? The answer lies in Pluto's weak gravity. On Earth, with strong gravity and dense atmosphere, it takes winds of about 25 to 35 mph to move sand grains. But on Pluto, with gravity only 6% as strong and particles made of low-density methane ice rather than dense quartz sand, winds of just 20 mph are sufficient. And Pluto does have winds. The convection in Sputnik Planitia drives atmospheric circulation. Nitrogen sublimates from the sunlit basin and condenses elsewhere, creating pressure gradients that drive winds. These winds aren't strong by Earth standards, probably no more than 20 to 30 mph at most. But in Pluto's weak gravity, that's enough to move methane ice grains across the surface. The dunes are found downwind, from mountain ranges and crater rims, suggesting that the methane particles are eroded from these highlands, lofted by winds, and then deposited in lower areas where they form dune fields. The dunes are geologically young. They show no impact craters, suggesting they've formed or been resurfaced within the last 500,000 years. This makes them some of the most dynamic features on Pluto's surface. While the convection cells in Sputnik Planitia take hundreds of thousands of years to turn over, the dunes might be actively moving right now. Winds during Pluto's summer might shift these dunes meters per year, slow by Earth standards, but fast compared to most geological processes on Pluto. The existence of dunes tells us that Pluto has an active wind regime, that material is being eroded and transported, that the landscape is changing. It's not a static, frozen world, but one where atmospheres drive geology, where climate shapes terrain, where processes we recognize from Earth operate under utterly alien conditions. Imagine standing on Pluto and watching a dust devil, or rather a methane ice devil, drift across the plains. In the thin atmosphere, it would be almost invisible, just a faint shimmer of suspended particles moving across the frozen surface in the dim sunlight. The winds would make no sound. There's not enough atmosphere to carry sound waves over long distances, but the dunes would record its passage, grains saltating across the surface, building new ridges, grain by grain, millimeter by millimeter, over the centuries. In Pluto's equatorial regions, particularly in the area informally called Tartarus Dorsa, New Horizons discovered one of the most alien landscapes in the entire solar system. Fields of tall ridges made of methane ice, standing like vertical blades or fins, some reaching 500 meters high, about 1,600 feet, taller than the Empire State Building. These structures are called penitents, after similar but much smaller formations found in high-altitude regions near Earth's equator. On Earth, penitents form through differential sublimation. Ice sublimates faster in some areas than others, carving deep troughs between tall ridges. They're typically a few meters tall at most. On Pluto, the same process operates, but on a vastly larger scale. The ridges are hundreds of meters tall, spaced hundreds of meters apart, aligned roughly north-south like rows of enormous knife blades embedded in the surface. The formation process takes advantage of Pluto's extreme axial tilt and its location near the equator. Sunlight hits the surface at very steep angles for long periods during certain parts of Pluto's orbit. This creates situations where vertical surfaces receive more sunlight than horizontal surfaces, counterintuitively, because we're used to Earth where horizontal surfaces get the most direct sun. When vertical surfaces receive more sunlight, they sublimate faster. Methane ice evaporates from vertical faces while horizontal surfaces remain relatively protected. Over millions of years, this differential erosion carves deep valleys between tall ridges, creating the bladed terrain. The ridges align north-south because that's perpendicular to the sun's path across the sky at Pluto's equator. The pattern maximizes the difference between sunlit and shaded surfaces, allowing the most efficient carving of troughs between blades. These structures are found nowhere else in the solar system except Earth's high-altitude equatorial regions, and on Earth they're tiny compared to Pluto's versions. They're essentially a unique terrain type, something that forms only under very specific conditions. Steep axial tilt, low gravity, volatile ice that can sublimate, and a position near the equator. If you were somehow standing in the bladed terrain, which would be nearly impossible because the ridges are too tall and steep to climb easily, you'd be in a forest of ice blades, each one towering hundreds of meters above you, stretching as far as you can see in regular rows. The spaces between blades would be deep, shadowed valleys where sunlight rarely reaches, while the tops of the blades gleam in the dim light. Walking through this terrain would be impossible. You'd have to navigate between the blades, following the valleys, unable to see more than a few ridges ahead because of the vertical walls surrounding you. It would be like walking through a city where all the buildings are narrow walls rather than blocks, creating a maze of tall, parallel corridors. The bladed terrain covers thousands of square kilometers. It's not a small, local feature, but a major geological province shaped by Pluto's unusual axial tilt and orbital characteristics over millions of years. Its geology creating art, erosion sculpting abstract patterns, all through the patient removal of methane ice molecule by molecule as the sun's light converts solid into gas and carries it away. Near Pluto's equator, there's a vast, dark region informally named Cthulhu Macula, after H.P. Lovecraft's cosmic horror entity, because it appeared mysterious, ancient, and slightly menacing in the early low-resolution images. It stretches about 2,000 kilometers across, roughly the length of Greenland, and it's one of the darkest regions in the entire solar system. The darkness comes from tholins, complex organic molecules that form when ultraviolet light from the sun breaks down methane in Pluto's atmosphere. These molecules are large, carbon-rich compounds with complicated structures, usually appearing dark red or brown. They rain down from the atmosphere onto Pluto's surface, coating everything they touch. Cthulhu Macula is ancient. Unlike Sputnik Planitia with its 0 craters, Cthulhu is heavily cratered. The surface here is billions of years old, possibly dating back to Pluto's formation 4.6 billion years ago. It's some of the most primitive terrain on Pluto, a window into what the dwarf planet's surface looked like in its youth. The reason it's so dark is that it's been accumulating tholins for billions of years. Layer upon layer of these organic molecules have settled onto the surface, building up a coating perhaps meters thick in some places. This coating absorbs most of the sunlight that hits it. Only about 5–10% of light is reflected, making Cthulhu among the darkest, large-scale features on any planetary surface. The contrast between Cthulhu Macula and Sputnik Planitia, sitting right next to each other, is visually striking. Sputnik reflects 90% of sunlight, brilliant white nitrogen ice. Cthulhu reflects less than 10%, ancient tholins. The boundary between them is sharp, almost as if someone drew a line across Pluto's surface, dividing light from darkness. But this contrast is scientifically significant, too. It tells us that Pluto has regions that are geologically active, being constantly resurfaced, staying young, right next to regions that have been geologically dead for billions of years. This kind of dichotomy is common on planetary bodies. Mars has it. The Moon has it. But seeing it on Pluto, so dramatically visualized through albedo contrast, was unexpected. The tholins themselves are fascinating from an astrobiology perspective. These complex organic molecules are the building blocks of even more complex compounds. On Earth, similar molecules might have been precursors to the chemistry that eventually led to life. On Pluto, they're just interesting chemistry. There's no liquid water, no energy source, no mechanism for them to evolve into anything more complex. But if Pluto-like objects were delivered to the early Earth by comets or asteroid impacts, which they almost certainly were, these tholins might have arrived too, seeding our planet with organic material that contributed to the origin of life. Studying the tholins on Pluto is, in a sense, studying a preserved sample of the organic chemistry that might have been present on Earth 4 billion years ago. Cthulhu Macula represents Pluto's deep past. It's the surface that formed when the solar system was young, before billions of years of evolution created the nitrogen ice plains and convecting glaciers and methane dunes. It's the baseline, the original state, the foundation upon which everything else was built. And it's dark, dark with the accumulated weight of billions of years, dark with organic molecules that have been slowly raining down from the atmosphere since before complex life existed on Earth. Dark with an ancient patience that makes human timescales feel insignificant. When you look at images of Pluto and see that dark region next to the bright heart, you're seeing time itself made visible, the ancient past preserved in darkness, the active present gleaming in reflected light, sitting side by side on a world that contains multitudes despite its small size. Nitrogen ice doesn't just convect in Sputnik Planitia, it also flows like glaciers, carving valleys and streaming down from highlands into the basin in patterns that look remarkably similar to glacial flow on Earth. In the New Horizons images, you can see features that look exactly like outlet glaciers in Greenland or Antarctica, flows of nitrogen ice starting in elevated terrain, channeling through valleys, and emptying into Sputnik Planitia. The flow lines are visible, streaks and patterns in the ice showing the direction of movement, similar to medial moraines on Earth's glaciers. Some of these nitrogen glaciers are 100 kilometers long or more, flowing from highlands thousands of meters above Sputnik Planitia down into the basin. They show features like flow bands, shear zones, and sometimes even features that might be crevasses, all characteristics of glaciers on Earth, but made of nitrogen instead of water. The physics of glacial flow is universal. On Earth, ice flows because gravity pulls it downslope, and because the ice deforms under pressure. The same principles apply to nitrogen ice on Pluto. Gravity, weak as it is, pulls the nitrogen downward. The ice deforms because it's close to its melting point, allowing it to flow slowly over time. The flow rates are probably similar to Sputnik Planitia's convection, centimeters per year, maybe a bit faster in steep terrain. Fast enough to create obvious flow features over thousands or millions of years, slow enough that you'd never perceive motion directly. What's remarkable is how similar these features look to Earth's glaciers, despite being made of completely different materials at completely different temperatures. A glaciologist studying New Horizons images could identify outlet glaciers, tributary glaciers, flow bands, and convergence zones using exactly the same terminology and concepts they'd use for Antarctic ice sheets. This is an example of what scientists call convergent evolution in planetary science. Different materials, under similar physical constraints, create similar forms. Gravity, pressure, flow mechanics, these don't care what material you're working with. They create the same patterns whether the ice is water at 10 degrees C or nitrogen at 230 degrees C. The valleys carved by these nitrogen glaciers are evidence that Pluto's surface has been shaped by flowing ice for potentially millions or billions of years. The highlands have been eroded, material has been transported into basins, landscapes have been sculpted by the patient flow of frozen gases behaving like liquid. If you could stand at the edge of one of these nitrogen glaciers and watch for a few decades with time-lapse photography, you'd see it move. The surface would advance down the valley, the flow lines would shift, the ice would continue its patient journey from highlands to basin. It would look like time-lapse footage of glaciers on Earth, except colder, darker, more alien, but fundamentally the same process. Ice flows, on Earth, on Mars, on Pluto. The materials differ, the temperatures differ, but gravity and physics remain constant. And so the landscapes they create, while exotic in composition, are familiar in form. Beneath Pluto's frozen surface, scientists believe there's an ocean. Not a small pocket of liquid, a global ocean, roughly 100 to 180 kilometers thick, sitting at the boundary between Pluto's rocky core and its icy outer shell. This might sound impossible. Pluto is small, distant, cold. How could it possibly maintain liquid water after 4.6 billion years? The answer involves several factors working together. First, Pluto's interior contains radioactive elements, primarily uranium, thorium, and potassium, in its rocky core. These elements decay over billions of years, releasing heat. This radiogenic heating is why Earth's interior is still molten, despite being the same age as Pluto. Second, when Pluto formed, the process of accretion released gravitational energy as material fell together. Some of this heat was retained in the interior, taking billions of years to radiate away through the insulating layers of ice and rock. Third, and this is crucial, the ocean likely contains ammonia dissolved in the water. Ammonia acts as antifreeze, lowering the freezing point significantly. A water-ammonia mixture can remain liquid at temperatures as low as 100 degrees Celsius, much colder than pure water's freezing point of 0 degrees Celsius. Fourth, there may be a layer of methane clathrate, a compound where methane is trapped inside a lattice of water ice, sitting above the ocean. Clathrates have very low thermal conductivity, much lower than pure water ice. This layer acts like a thermal blanket, insulating the ocean below and preventing it from freezing. The evidence for this ocean comes from several observations. The most compelling is Pluto's orientation relative to Charon. The heavy mass of Sputnik Planitia should have caused Pluto to reorient itself through true polar wander, which it did. But the mathematics of this reorientation, the way Pluto tipped and how quickly, tells us something about the interior structure. If Pluto were frozen solid all the way through, the reorientation would have happened differently than if there's a liquid layer beneath the surface. The presence of a subsurface ocean acts like ball bearings, allowing the outer ice shell to rotate more easily relative to the rocky core. Computer models that include a subsurface ocean match the observed features better than models without one. There's also evidence from Pluto's surface features. Some of the fractures and tectonic structures suggest that Pluto's ice shell has expanded over time. This could happen if the ocean has been gradually freezing. When water freezes, it expands, pushing the surface outward and creating extensional fractures. If this ocean exists, it's probably salty, perhaps 8% salt by mass, similar to Utah's Great Salt Lake, or about twice as salty as Earth's oceans. The salt comes from chemical reactions between the liquid water and the rocky core material, dissolving minerals over billions of years. Could there be life in Pluto's ocean? It's extremely unlikely, but not completely impossible. The ocean would be dark. No sunlight penetrates through kilometers of ice. It would be cold, probably around 70 degrees, even with ammonia antifreeze. There's no obvious energy source beyond the slow chemical reactions between water and rock. But if the ocean interacts with the rocky core through hydrothermal systems, underwater chemistry where hot rock meets liquid water, then there might be chemical energy available. On Earth, Hydrothermal vents support entire ecosystems of bacteria and other organisms that live without sunlight, getting energy from chemical gradients instead. Pluto's hypothetical ocean is unlikely to have hydrothermal systems. The interior is probably too cold for that, but we can't completely rule it out. And if there's one lesson we've learned from studying life on Earth, it's that life finds ways to survive in conditions we thought were impossible. The ocean, if it exists, has been there for billions of years, sealed beneath ice, in darkness, slowly mixing, gradually freezing from the top down as Pluto's interior cools. It's a remnant of Pluto's formation, a preserved sample of the liquid water that probably existed throughout the outer solar system when the planets were young. And it might still be there today, hidden beneath the frozen surface, waiting for some future mission to drill through the ice and taste water that has been isolated from the universe for most of the history of the solar system. Between Pluto's surface ice and the hypothetical subsurface ocean, there might be a layer of methane clathrate, a strange compound where methane molecules are trapped inside cage-like structures of water ice molecules. Clathrates are weird substances. They look like ice, but they contain significant amounts of gas locked inside their crystal structure. When you heat them or reduce pressure, they decompose rapidly, releasing the trapped gas. On Earth, massive deposits of methane clathrate exist beneath ocean floors and in permafrost, containing more carbon than all other fossil fuels combined. On Pluto, methane clathrate would form naturally if methane and water ice are present together at appropriate temperatures and pressures. The layer might be tens of kilometers thick, sitting above the liquid water ocean, below the pure water ice that makes up most of Pluto's mantle. The importance of this layer is its thermal properties. Methane clathrate has thermal conductivity about 5 to 10 times lower than pure water ice. It's an excellent insulator. Heat passes through it very slowly. This means it acts like a blanket, preventing the ocean below from losing heat to the surface above. Without this insulating layer, Pluto's ocean would probably have frozen solid billions of years ago. The heat from the rocky core wouldn't be sufficient to maintain liquid water, while also conducting through hundreds of kilometers of ice to radiate into space. But with the clathrate layer acting as insulation, the heat is retained more efficiently, allowing the ocean to persist. This is similar to how Earth's atmosphere acts as an insulating blanket through the greenhouse effect, keeping our surface warmer than it would be otherwise. Or how a layer of snow insulates the ground beneath it, keeping soil warmer than the air above. Insulation allows systems to maintain temperature differences that wouldn't be possible otherwise. The clathrate layer also has implications for Pluto's possible cryovolcanism. If stresses in the ice shell create fractures that reach down to the clathrate layer, the sudden pressure release could cause rapid decomposition of the clathrates, releasing methane gas explosively. This gas release could drive cryovolcanic eruptions, pushing slurries of water, ammonia, and methane ice toward the surface. Evidence for this comes from the young surfaces of Wright Mons and Piccard Mons, the possible ice volcanoes we discussed earlier. If these features are indeed cryovolcanoes, they need an energy source to drive eruptions. Decomposing clathrates could provide that energy. Methane clathrate is also important for understanding Pluto's atmosphere. If methane from decomposing clathrates reaches the surface, it can sublimate into the atmosphere, maintaining the trace of methane that astronomers observe. Without a subsurface source, surface methane would be destroyed by ultraviolet light within a few hundred years. Yet Pluto's atmosphere contains methane continuously. There must be a source replenishing it, possibly from clathrate decomposition. So this hypothetical layer of methane clathrate, if it exists, serves multiple functions: insulating blanket preserving the ocean, potential energy source for cryovolcanism, and reservoir supplying atmospheric methane. It's a crucial component in the models that describe Pluto's interior structure and geological activity. All of this is inferred, of course. We don't have direct proof that a clathrate layer exists. We can't drill through Pluto's ice shell to sample it. But the indirect evidence, the persistence of the ocean, the young cryovolcanic features, the atmospheric methane, all points towards something like this existing. Pluto might be wrapped in an insulating blanket of frozen methane and ice, keeping its ancient ocean liquid, maintaining geological activity, allowing this tiny world to remain dynamic and interesting billions of years after it should have frozen, solid, and died. When New Horizons looked back at Pluto after the flyby, capturing images of the dwarf planet backlit by the sun, it revealed one of the mission's most beautiful and surprising discoveries. Pluto's atmosphere is blue, not metaphorically blue, not blue in false color images, actually blue, the same color as Earth's sky, for entirely different reasons, but visually identical. Earth's sky is blue because of Rayleigh scattering. Air molecules are very small, much smaller than the wavelength of visible light. When sunlight passes through the atmosphere, the small molecules scatter short wavelengths, blue light, much more effectively than long wavelengths, red light. The scattered blue light fills the sky, making it appear blue from the ground. Pluto's atmosphere is blue for a different reason. The blue color comes from haze particles, tiny grains of tholins, those complex organic molecules formed when sunlight breaks down methane. These particles are larger than air molecules, but still smaller than the wavelength of light, typically around 0.1 to 0.5 micrometers across. Particles in this size range scatter blue light more effectively than red light through a process called scattering. The result is that when you look at Pluto's atmosphere backlit by the sun, you see blue light scattered toward you, while red light passes through relatively unscattered. The atmosphere contains more than 20 distinct haze layers, visible as concentric rings in the backlit images. These layers form at different altitudes where temperature and pressure conditions favor the condensation or formation of haze particles. They're stacked like the layers of an onion, each one contributing to the overall blue color. The haze extends incredibly high, over 200 kilometers above Pluto's surface, proportionally much higher than Earth's atmosphere, despite being far less dense. This happens because Pluto's weak gravity can't pull the particles down as effectively as Earth's strong gravity pulls down our air molecules. Over time, these haze particles settle out of the atmosphere and fall onto Pluto's surface, where they accumulate as those red and brown tholins we see in regions like Cthulhu Macula. The atmosphere is constantly producing new haze particles to replace the ones that fall out, creating a cycle. Methane sublimates from the surface, rises into the upper atmosphere, gets broken down by sunlight into complex organics, forms haze particles, and eventually falls back to the surface. The blue atmosphere was completely unexpected. Before New Horizons, scientists thought Pluto's atmosphere might be clear or perhaps slightly hazy. Nobody predicted that it would be filled with photochemical smog, stratified into dozens of layers, glowing brilliant blue when backlit. The images of Pluto's blue atmosphere, with the dark silhouette of the surface below and the black of space above, are some of the most iconic from the entire New Horizons mission. They transform Pluto from an abstract concept into a real place, somewhere with a sky, with atmospheric layers, with colors that human eyes would actually see. If you stood on Pluto's surface and looked up, what would you see? During the day, probably not much. The haze layers are too thin to be visible from below. The sky would appear almost black, like the sky from the moon, because there's not enough atmosphere to scatter significant light toward the ground. But if you could, hover above Pluto and look at the limb, the edge where surface meets space. You'd see that blue glow, those concentric haze layers, the atmosphere revealing itself through scattered sunlight. You'd see a world that, for all its alien chemistry and extreme conditions, produces a color our eyes associate with home. Blue sky above a frozen world 3 billion miles from the sun. It's a reminder that beauty and complexity can emerge anywhere in the universe, that the cosmos doesn't restrict its artistry to warm, familiar places. Most planetary atmospheres get colder as you go higher. On Earth, temperature drops about 6.5 degrees Celsius per kilometer of altitude in the troposphere. The reason mountain peaks are snow-covered even in summer. This makes intuitive sense. You're getting farther from the warm surface and closer to the cold of space. But Pluto's atmosphere does the opposite. It has a temperature inversion. It's actually warmer at altitude than at the surface. The surface temperature is around 40 Kelvin, 233 degrees Celsius. But in the upper atmosphere, around 30 kilometers altitude, temperatures rise to about 110 Kelvin, 163 degrees Celsius. That's 70 degrees warmer than the surface, even though you're farther from any heat source. This inversion is caused by a methane greenhouse effect, but it works differently than Earth's greenhouse effect. On Earth, greenhouse gases trap infrared radiation that would otherwise escape to space, warming the surface. On Pluto, methane in the upper atmosphere absorbs sunlight directly, specifically ultraviolet and near-infrared wavelengths, heating that layer of the atmosphere while the surface below remains cold. It's like having a heating element suspended in the sky rather than on the ground. The upper atmosphere warms directly from solar radiation, while the surface stays cold because it receives so little sunlight to begin with. This temperature inversion has profound effects on Pluto's atmospheric dynamics. Warm air rising from below would normally drive convection and create weather patterns. But on Pluto, the air is already warmest at the top, so there's no convective overturning in the traditional sense. The atmosphere is stably stratified. Each layer sits contentedly at its altitude, with no tendency to rise or sink. This doesn't mean the atmosphere is static. There are winds driven by pressure gradients and the sublimation-condensation cycle of nitrogen ice. But the winds are different from Earth's weather. They're not driven by convection but by horizontal pressure differences. The temperature inversion also explains why methane snow forms on mountain peaks. At altitudes above about 1 mile, mountains extend into the warmer upper atmosphere. In this warmer air, Methane can remain as vapor rather than condensing to ice. But when that methane-rich air contacts a cold mountain peak made of water ice at 40 K, the methane condenses directly onto the surface, forming bright frost caps. It's the reverse of Earth's situation. On Earth, mountain peaks are cold because you're in a colder part of the atmosphere. On Pluto, mountain peaks extend into a warmer part of the atmosphere. But the peak surfaces themselves are still cold because they're made of water ice at 40 K. So methane condenses on them preferentially, creating the bright caps we observe. This temperature structure is fragile, though. It depends on having enough methane in the atmosphere to absorb sunlight. As Pluto moves farther from the Sun in its orbit, the atmosphere may thin, reducing the methane content. If methane concentration drops too low, the greenhouse warming might disappear, causing the upper atmosphere to cool dramatically. Scientists still don't fully understand all the details of Pluto's atmospheric temperature structure. Before New Horizons, models predicted temperatures around 100 K in the upper atmosphere, and measurements confirmed this roughly. But the exact heating mechanisms, which wavelengths of sunlight are most important, how the heat is distributed vertically, whether there are day-night temperature variations, remain subjects of ongoing research. What's clear is that Pluto's atmosphere, despite being 100,000 times thinner than Earth's, is complex and structured in ways that defy simple intuition. It's warmer above than below. It contains dozens of haze layers. It drives surface geology through sublimation and condensation, and it changes over Pluto's long orbital cycle in ways we're only beginning to predict. An upside-down atmosphere on an upside-down world, where the normal rules are inverted and warm air sits above cold ground, patiently absorbing the faint sunlight that reaches this distant realm. Before New Horizons arrived, scientists worried that Pluto's atmosphere might collapse. As Pluto moves away from the Sun along its elliptical orbit, surface temperatures drop. When temperatures drop, less nitrogen ice sublimates, thinning the atmosphere. If enough nitrogen freezes out onto the surface, the atmosphere could disappear almost entirely, collapsing from a thin but measurable presence to essentially nothing. Computer models predicted this might happen when Pluto reached aphelion, its farthest point from the Sun. All the atmospheric nitrogen would rain back down as frost, coating the surface in meters-thick deposits, leaving behind only the faintest trace of an atmosphere. But New Horizons data suggested something different. The atmosphere was thicker than expected. Atmospheric pressure measured around 1 pascal at the surface, higher than earlier observations predicted. And the thermal structure suggested the atmosphere might be more stable than models indicated. In the years since the flyby, astronomers have continued monitoring Pluto's atmosphere through stellar occultations, watching how starlight dims when Pluto passes in front of a background star. These observations provide information about atmospheric density and temperature structure. The results have been surprising. From 1988 to 2015, Pluto's atmospheric pressure actually increased roughly threefold, even as Pluto moved farther from the Sun. This counterintuitive result happened because Pluto's North Pole, which contains major nitrogen ice deposits, emerged from 124 years of darkness in 1987. Sunlight hitting these fresh ice deposits triggered massive sublimation that continued for decades, thickening the atmosphere even as overall solar heating decreased. But by 2019, observations suggested the atmosphere might finally be collapsing. Atmospheric pressure dropped 20 to 30% in just 1 year, a dramatic change. The nitrogen ice in Sputnik Planitia was cooling enough that sublimation rates were declining rapidly. Does this mean Pluto's atmosphere will disappear over the next few decades? Not necessarily. The atmosphere might stabilize at a lower pressure rather than collapsing completely. Or the collapse might be temporary, reversing when other regions start sublimating more vigorously as Pluto's seasons progress. We simply don't know. Pluto's atmospheric cycle operates on timescales of decades to centuries, and we've only been watching carefully for about 35 years, a tiny fraction of one Pluto year. We're seeing a snapshot of a long, complex process, trying to predict how it will unfold without having witnessed a complete cycle. What's clear is that Pluto's atmosphere is more resilient than early models suggested. It hasn't collapsed yet, despite predictions. It increased in pressure when it was supposed to be thinning, and even if it does collapse over the coming decades, it will almost certainly return when Pluto next approaches perihelion in the 2230s, sublimating anew and filling the vacuum with nitrogen gas once more. The atmosphere is holding out, resisting predictions, behaving in ways that challenge our understanding. And that's exactly what makes Pluto so scientifically valuable. It keeps surprising us, keeps teaching us that our models are incomplete, keeps reminding us that the universe is more complex than our equations suggest. At Pluto's poles, where 100 years of continuous sunlight alternate with 100 years of continuous darkness, something dramatic happens when the seasons change. Explosive atmospheric surges. Imagine a polar region that has been in darkness for a century. During that time, nitrogen from the atmosphere has been slowly condensing onto the cold surface, building up layers of frost tens of microns thick, maybe more in some locations. This nitrogen is frozen solid at temperatures around 30 to 35 Kelvin, trapped as ice on the surface. Then spring arrives. After 100 years, sunlight returns. It's not much sunlight. Remember, even at noon on Pluto, the sun is dim. But compared to a century of darkness, it's enough to matter. The frozen nitrogen begins to warm. Remember, nitrogen's freezing point at Pluto's pressures is around 37 K. When sunlight warms the frost to this temperature, it sublimates, transforms directly from solid to gas without passing through a liquid phase. But this happens suddenly, rapidly, almost explosively. All the nitrogen that accumulated over a century of winter sublimates over a period of weeks or months as temperatures cross the threshold. The atmospheric pressure in that region can increase by a factor of 1,000 in just days, from near vacuum to measurable pressure. This surge of nitrogen gas flows away from the pole, seeking lower pressure regions, creating strong winds that reshape surface features and transport material across large distances. Then over the following decades, as the season progresses and the sublimation surge subsides, the atmosphere gradually returns to equilibrium. And 100 years later, when winter returns to that pole, the cycle reverses. The atmosphere begins condensing onto the surface again, slowly at first, then more rapidly as the pole cools below nitrogen's freezing point. By the end of the 100-year winter, meters of nitrogen frost might have accumulated, ready to sublimate explosively when spring next arrives. We haven't observed this directly. We'd need to watch Pluto continuously for decades or centuries to see it happen. But the evidence is written in the seasonal models and in the variations in atmospheric pressure that astronomers have measured over the past few decades. Charon's poles show evidence of this too. Charon's northern polar region, called Mordor Macula, is stained dark red with tholins. But the darkness isn't uniform. There are variations that suggest seasonal frost deposition and sublimation. When methane that escaped from Pluto reaches Charon, it freezes onto the winter pole. Then when spring arrives after 100 years, that methane sublimates, explosively, atmospheric pressure increasing by factors of 1,000, methane bursting back into gas phase, only to condense again at the opposite pole, now entering its century-long winter. These explosive seasonal surges are unique to worlds with extreme axial tilts and volatile ices. Earth doesn't experience anything like this. Our seasons are moderate. Our atmospheric pressure doesn't vary by factors of 1,000 between winter and summer. Mars has mild variations, with carbon dioxide condensing at the winter poles and sublimating in spring, but nothing as dramatic as Pluto's century-long cycles. Its climate operating on timescales that dwarf human civilizations. Spring arriving after 100 years of darkness. Atmosphere surging into existence, frost sublimating in a geological instant. Then slow accumulation again as winter returns, building toward the next explosive spring a century hence. The poles remember these cycles in their surface features, variations in albedo, patterns of frost, evidence of winds that blow only during seasonal transitions. And if we could watch long enough, we'd see Pluto's atmosphere pulse with these polar surges, each one driven by the patient turning of seasons on a world where a year spans 2.5 centuries. One of the most hauntingly beautiful images from the New Horizons mission shows something that shouldn't exist but does. Crepuscular rays on Pluto, those beams of light and shadow that we call God rays on Earth, streaming through the atmosphere when the sun is low on the horizon. On Earth, these rays form when sunlight shines through gaps in clouds, creating alternating bands of brightness and shadow that seem to radiate from the sun's position. We see them at sunset, at sunrise, whenever clouds partially block the sun and light streams through the gaps. On Pluto, there are no clouds. The atmosphere is far too thin and cold for anything like Earth's cumulus formations. But there are mountains, tall peaks of water ice, rising thousands of meters above the surrounding terrain. When New Horizons looked back at Pluto after the flyby, capturing images with the sun behind the dwarf planet, it saw something remarkable. Shadows cast by mountains through the atmospheric haze layers, creating bright and dark bands stretching across the limb. The mountains blocked the low-angle sunlight, casting shadows that extended through the atmosphere for hundreds of kilometers. Where sunlight passed, unobstructed between peaks, it illuminated the haze layers, making them glow blue. Where mountains blocked the light, the haze layers remained in shadow, appearing darker. The result was a series of radial bands, light, dark, stretching across the atmospheric layers, looking exactly like crepuscular rays on Earth, despite forming through a completely different mechanism. These rays revealed the three-dimensional structure of Pluto's atmosphere in a way no other observation could. You could see the layers stacked at different altitudes, each one illuminated or shadowed independently. You could trace how far the shadows extended, hundreds of kilometers, telling you about the atmosphere's vertical extent. You could measure the angle of the rays to determine the sun's position and the geometry of the observation. The image became iconic immediately. It showed Pluto not as an abstract dot or a flat map, but as a place, somewhere with terrain casting shadows, with atmosphere bending light, with spatial depth and structure. It was one of those moments where planetary science becomes art, where the data is so visually striking that it transcends technical interest and becomes genuinely moving. If you could stand on Pluto at sunset, or more accurately, at the end of the 3-day day, as the sun slowly descended toward the horizon, would you see these rays? Probably not from the surface. The atmosphere is too thin to scatter much light toward the ground. From below, you'd see the mountains silhouetted against the dim sky. But the rays themselves would be invisible because there's not enough atmosphere between you and the rays to scatter light toward your eyes. But if you could hover above the surface or stand on a mountain peak looking toward the horizon, you might see them. Faint bands of light and shadow stretching through the thin blue haze, marking where other mountains block the sun's light. These shadows are transient. As Pluto rotates, the sun's position changes, the shadows shift, and the pattern of rays evolves. Over the course of Pluto's slow rotation, 153 hours for one complete turn, the rays would sweep across the atmosphere, appearing and disappearing as different mountains came into the right geometry to cast shadows toward the viewing angle. New horizons captured them at one particular moment, one specific geometry, when everything aligned just right to make the shadows visible. A few hours earlier or later, they would have looked different. A few days earlier or later, they might not have been visible at all. It's a reminder that these flyby missions capture snapshots, single moments frozen in time out of the billions of years these worlds have existed. We see Pluto as it was on July 14, 2015, at the exact moment New Horizons flew past. We don't know what it looked like the day before or the day after. We can infer, we can model, but we don't have direct observations. The crepuscular rays are a gift from that particular moment, a perfect alignment of sun, mountains, atmosphere, and spacecraft that created one of the most beautiful images of the mission. Their shadows through haze, light through darkness, complexity emerging from the interaction of terrain and atmosphere and photons traveling 3 billion miles to illuminate something no human will likely ever see in person. Pluto loses atmosphere to space, not rapidly, very slowly by human standards, but continuously. Atmospheric gases in the upper reaches, where molecules move fastest and gravity is weakest, occasionally achieve escape velocity and drift away into the vacuum, never to return. Before New Horizons arrived, scientists estimated that Pluto might be losing atmosphere at rates as high as 1027 to 1028 molecules per second. That sounds like a lot, and it is. Billions of trillions of molecules escaping every second. But New Horizons measurements showed the escape rate is actually much lower, only about 1025 to 1026 molecules per second. That's still a huge number, but it's 100 to 1,000 times slower than early predictions. Why is the atmosphere escaping so slowly? Several factors contribute. First, Pluto is colder than expected in the upper atmosphere, which we discussed earlier. Colder molecules move more slowly, and slower molecules are less likely to achieve escape velocity. Second, the dominant escaping molecule is nitrogen, which is relatively heavy. Lighter molecules like hydrogen or helium escape much more easily, but nitrogen molecules have enough mass that even at the temperatures in Pluto's upper atmosphere, most of them don't move fast enough to escape. Third, Pluto's upper atmosphere is surprisingly dense, thicker than models predicted. This means there are more collisions between molecules, and collisions tend to thermalize the velocity distribution, preventing the fastest molecules from achieving escape. Instead of a few molecules moving very fast, you get many molecules moving at moderate speeds, and moderate speeds aren't sufficient for escape. Despite the slower than expected escape rate, Pluto does lose atmospheric mass over time. Over the course of Pluto's 248-year orbit, it might lose the equivalent of a few centimeters of nitrogen ice from its surface. Not enough to drastically change the atmosphere, but measurable. Interestingly, some of this escaping material doesn't leave the Pluto-Charon system entirely. About 2.5% of the atmospheric gases escaping from Pluto can reach Charon, 12,000 miles away. These molecules travel through the space between the two worlds, eventually encountering Charon's surface and freezing out. This creates the longest distance atmospheric transfer known in the solar system. Methane molecules sublimate from Pluto's surface, enter the atmosphere, rise to the upper layers, escape Pluto's gravity, drift across 12,000 miles of vacuum, and land on Charon's surface, where they freeze and are processed by ultraviolet light into the reddish tholins that stain Charon's polar regions. It takes days for molecules to make this journey. They travel at speeds of hundreds of meters per second, fast by human standards, but slow compared to the distance involved. The molecules that land on Charon today sublimated from Pluto a week ago. This transfer process has been ongoing for billions of years. Charon's polar regions contain who knows how much material originally from Pluto, transported one molecule at a time across the void between them. It's a bond between the two worlds, Pluto literally giving part of itself to Charon, adorning its companion's poles with colors that originated on Pluto's surface. The atmospheric loss also tells us something about Pluto's long-term evolution. If the escape rate has been roughly constant over geological time, Pluto might have lost a significant fraction of its original atmosphere. Perhaps several meters worth of surface ice, maybe more. This could explain why Pluto's atmosphere isn't even thicker than it is, why the surface ice deposits aren't deeper. But the loss is slow enough that Pluto won't run out of atmosphere anytime soon. Even if it loses a centimeter of ice per orbit, that's only 4 meters per millennium, 4,000 meters per million years. Pluto has kilometers of nitrogen ice available. At current loss rates, it would take billions of years to lose all its volatile ices to space. So Pluto bleeds atmosphere slowly into the vacuum, molecules escaping one by one, some falling back, some drifting to Charon, some leaving the system entirely. It's been happening since Pluto formed, and it will continue until the sun becomes a red giant and changes everything. A slow leak measured in molecules per second, adding up over eons to reshape the surfaces of two small worlds dancing together in the darkness. Pluto's largest moon, Charon, is extraordinary, not just because of its size, but because of its relationship to Pluto. Charon is half Pluto's diameter, 212 kilometers across, compared to Pluto's 377 kilometers. In terms of mass, Charon is about 12.2% as massive as Pluto. This makes Charon the largest moon relative to its parent body in the entire solar system. Earth's moon is impressive at about 27% of Earth's diameter and 1.2% of Earth's mass, but Charon is proportionally twice as large in diameter and 10 times as large in mass compared to its planet. The size ratio is so extreme that the center of mass around which both objects orbit, called the barycenter, lies outside Pluto's physical body, in the empty space between the two worlds. Pluto and Charon don't orbit like planet and moon, with the moon circling the planet while the planet stays mostly stationary. Instead, both objects orbit their common center of mass, tracing out circular paths through space. This is why astronomers sometimes call the Pluto-Charon system a binary dwarf planet, two worlds of comparable size orbiting each other, neither one clearly dominant. It's more like a double planet than a planet with a moon. The barycenter sits about 960 kilometers from Pluto's center, which is about 1,200 kilometers from Pluto's surface. So if you were standing on Pluto's surface, you'd see Charon orbiting around a point in empty space about 11,000 miles away. Both you and Charon would be circling that invisible point, completing one orbit every 6.387 Earth days. Charon orbits remarkably close to Pluto, only about 9,600 kilometers center to center, or about 17,000 kilometers surface to surface. For comparison, Earth's moon orbits at an average distance of 384,000 kilometers. Charon is about 20 times closer to Pluto than the moon is to Earth. This close proximity and large relative size create strong tidal forces between the two bodies. Over billions of years, these tidal forces have locked both Pluto and Charon into synchronous rotation. Each world keeps the same face toward the other at all times. This mutual tidal lock is unique in the solar system among planetary-scale bodies. The moon is tidally locked to Earth, but Earth isn't locked to the moon. Our planet rotates once per day, while the moon orbits once per month. But Pluto and Charon are both locked, their rotation periods exactly matching their orbital period. If you stood on the Charon-facing hemisphere of Pluto, Charon would hang motionless in the sky, never rising or setting, always showing you the same face. Over the course of 6.387 days, you'd see Charon go through phases: full Charon, gibbous Charon, half Charon, crescent Charon, new Charon, as sunlight illuminated different portions of its surface. But it would never move from its fixed position in the sky. And if you walked to the opposite side of Pluto, the non-Charon hemisphere, you'd never see Charon at all. It would be permanently below your horizon, invisible, as if it didn't exist. Half of Pluto's population, if Pluto had a population, would never see Charon, while the other half would see it always. From Charon's surface, Pluto would appear enormous, covering about 3.8 degrees of sky, about 8 times the angular size that our moon appears from Earth. It would dominate the sky, showing its full disk and going through phases, but never moving, always hanging in the exact same position. This is the strange geometry of tidal locking, the result of billions of years of gravitational interactions, slowly matching rotation periods to orbital periods until everything synchronized into perpetual mutual embrace. Charon has a canyon system called Serenity Cosma, and potentially several other major canyon systems that might contain some of the tallest cliffs in the entire solar system. The canyons appear to be tectonic features formed when Charon's surface fractured and pulled apart. Some of these fractures are enormous, stretching hundreds of kilometers in length tens of kilometers in width and potentially up to 9 kilometers deep. 9 kilometers. That's deeper than Earth's Grand Canyon by a factor of 5. It's deeper than the walls of Valles Marineris on Mars, previously thought to be the tallest cliffs in the solar system at about 7 kilometers. If you stood at the bottom of Serenity Chasma and looked up at the rim, you'd be looking up more than 5.5 miles, vertically, at walls of water ice towering above you. These canyons likely formed when Charon's interior froze. Early in Charon's history, tidal heating from Pluto, before the system became tidally locked, and residual heat from formation might have kept a subsurface water-ocean liquid. Then, as the system achieved tidal lock and heating decreased, the ocean gradually froze. When water freezes, it expands, about 9% in volume. This expansion would have pushed Charon's surface outward, creating global stress in the icy crust. Eventually, the stress exceeded the strength of the ice, and the surface fractured, creating enormous canyons as the crust pulled apart to accommodate the expanding interior. This is essentially the opposite of what happens on terrestrial planets. On Earth or Mars, when the interior cools and contracts, the surface compresses, creating wrinkle ridges and thrust faults. On Charon, cooling caused expansion due to water's unusual property of being less dense as a solid than as a liquid, creating extensional features like canyons instead. The canyon walls are made of water ice at around 40 Kelvin. Remember, water ice at these temperatures is as hard as granite. The walls are nearly vertical, possibly overhanging in places, carved by the fracturing of the crust and shaped by subsequent erosion from micrometeorite impacts over billions of years. At the bottom of these canyons, temperatures might be slightly different than at the surface due to reduced exposure to sunlight and cosmic rays. Shadows cast by the canyon walls might create permanently shadowed regions that never see direct sunlight, similar to permanently shadowed craters at the moon's poles. Could you climb these walls? Even with Charon's weak gravity, about 3% of Earth's, a 9-kilometer vertical climb would be formidable. The ice would be hard and smooth, offering few handholds. The walls might be fractured in places, creating ledges and discontinuities, but overall it would be like climbing a 30,000-foot vertical wall of frozen glass. More likely, you'd descend using ropes or rappelling equipment, lowering yourself slowly down the enormous cliff face, taking hours to reach the bottom. At the floor, you'd stand in a chasm so deep that the rim would be barely visible above you, a narrow strip of star-filled sky bounded by towering walls of ancient ice. New Horizons didn't have perfect resolution across all of Charon's surface, so the exact depth of these canyons remains somewhat uncertain. But the measurements suggest they're among the most extreme topographic features in the solar system, evidence of global-scale geological processes that reshaped Charon's entire surface billions of years ago. The canyons are fractures in frozen time, cracks that open when Charon's interior completed its transformation from liquid to solid. When the last of its primordial ocean froze and expanded, pushing the surface apart and creating these monumental scars that will remain for billions of years more. Beyond Charon, Pluto has 4 additional moons, Styx, Nix, Kerberos, and Hydra, all discovered after 2005 using the Hubble Space Telescope. These moons are tiny compared to Charon, ranging from about 10 to 55 kilometers across, and they orbit much farther out. All four are named after figures from Greek underworld mythology, continuing the theme established by Pluto and Charon. Styx is named after the river separating the living world from the underworld. Nyx is named after the goddess of darkness and night, also Charon's mother in mythology. Kerberos is named after the three-headed dog guarding the underworld, more commonly spelled Cerberus, but using the Greek spelling to get the initial K. Hydra is named after the nine-headed serpent that guarded one entrance to the underworld. These moons orbit in a nearly perfect plane aligned with Charon's orbit. They're all part of the same system, suggesting they formed together, probably from the same collision or series of collisions that created Charon. But unlike normal moons, which rotate once per orbit while keeping the same face toward their planet, tidal locking, Pluto's small moons tumble chaotically. Nyx, for example, completes 89 rotations for every orbit around Pluto. Its rotation axis isn't stable. It wobbles and precesses unpredictably. This happens because the gravitational field these moons experience is complex. They're orbiting not just Pluto, but the Pluto-Charon binary system. The combined gravity of both Pluto and Charon creates a complicated, non-uniform field. Add to that the moon's irregular shapes. They're probably potato-shaped, not spherical, and you get rotational dynamics that are sensitive to small perturbations. Computer models show that the rotation rates and axes of these small moons are chaotic in the mathematical sense. Tiny changes in initial conditions lead to completely different outcomes. If you could rewind the solar system and let it evolve again with initial conditions changed by just meters in position or millimeters per second in velocity, these moons might be rotating completely differently today. The tumbling has been going on for billions of years, and it will continue for billions more. Tidal forces from Pluto and Charon are too weak to damp out the rotation and lock these moons into synchronous spins. They're too far away, too small, too irregularly shaped for tidal locking to work efficiently. So they spin wildly, tumbling end over end, their rotational periods changing over timescales of years or decades as gravitational perturbations nudge them in different directions. An observer on one of these moons, say Nyx, would experience a constantly changing orientation relative to Pluto and the stars. Up would have no stable meaning. The sun would rise from different directions on consecutive orbits. The small moons also orbit in precise gravitational resonances with each other and with Charon. Styx, Nyx, and Hydra are locked in a three-body resonance. Their orbital periods are related by ratios of whole numbers, creating a synchronized pattern. These resonances are stable, protecting the moons from close encounters that might otherwise lead to collisions. All 5 moons appear to be made of water ice, similar in composition to Charon. They likely formed from debris left over from the impact that created Charon, material that didn't fall back onto either Pluto or Charon, but remained in orbit, eventually coalescing into these small satellites. The tiny moons are fragments of Pluto's violent past, spinning, reminders that the current orderly system emerged from collision and chaos. That stability can arise from catastrophe, given enough time for orbital mechanics to settle into their resonances and equilibria. Charon's composition is noticeably different from Pluto's, despite the two bodies forming in the same region, and possibly from the same collision. This difference reveals something important about their formation and evolution. Pluto's surface is dominated by volatile ices, nitrogen, methane, and carbon monoxide, materials that sublimate easily and cycle through the atmosphere. Water ice is present on Pluto but is mostly buried beneath or mixed with these more volatile materials. Charon, by contrast, has a surface that's almost entirely water ice. Very little nitrogen, virtually no methane deposits, except the seasonal frost at the poles deposited from Pluto's atmosphere. No carbon monoxide, just water ice, covering the entire surface. Why the difference? Several factors contribute. First, Charon is smaller and has even weaker gravity than Pluto, only about 28% of Pluto's surface gravity. This means Charon can't hold on to an atmosphere as effectively. Any nitrogen or methane on Charon's surface would sublimate into space and escape, while on Pluto, the same materials cycle between surface and atmosphere. Over billions of years, Charon lost its volatile ices to space, while Pluto retained most of its. Charon was winnowed down to just the materials with low vapor pressures, primarily water ice, which doesn't sublimate significantly at outer solar system temperatures, and so remains permanently on the surface. Second, if Charon formed from a collision, it might have formed from material that was already depleted in volatiles. The impact might have preferentially ejected water ice-rich material, while the nitrogen and methane-rich materials remained on Pluto or were lost to space during the collision. Third, Charon likely had a subsurface ocean that froze billions of years ago. When that ocean froze, it would have drowned any surface deposits of volatile ices, burying them beneath hundreds of kilometers of water ice. The surface we see today is relatively young, perhaps only a few billion years old, rather than 4.6 billion, exposing water ice from the frozen ocean rather than primordial surface deposits. The compositional difference means the two worlds have had very different geological histories, despite orbiting each other for billions of years. Pluto remained geologically active, with flowing nitrogen glaciers and convecting ice plains and seasonal atmospheric changes. Charon froze solid relatively early, preserving ancient canyons and impact craters with little subsequent modification. Looking at Pluto and Charon side by side is like looking at two different evolutionary paths from similar starting points. They began in the same place, possibly formed from the same material, orbited together through the same radiation environment and bombardment history. But small differences in size, composition, and internal heat budget led them to diverge dramatically in appearance and activity. Pluto is colorful: white nitrogen plains, dark reddish-brown tholins, methane frosts. Charon is monochrome: gray water ice everywhere except the red polar cap. Pluto is geologically young in places, ancient in others. Charon is mostly ancient everywhere except possibly in regions that experienced ancient cryovolcanism. They're companions, but they're not twins. They're siblings that grew up together but developed different personalities, different appearances, different stories, united by gravitational bonds, but separated by the different paths their geological evolution took. NASA's New Horizons spacecraft, launched on January 19, 2006, became the fastest spacecraft ever launched from Earth, reaching a velocity of 36,400 miles per hour, about 8,500 kilometers per hour, as it left our planet. To put that speed in perspective, New Horizons crossed the moon's orbit in just 9 hours. The Apollo astronauts took 3 days to make that same journey. The spacecraft traveled so fast that it passed the orbit of Mars in just 78 days, reached Jupiter for a gravity assist in only 13 months, and arrived at Pluto after a 9.5-year journey covering more than 3 billion miles. That initial velocity was necessary because of how far Pluto is. Without it, the journey would have taken decades, perhaps 20 or 30 years instead of 9.5. Mission planners needed the spacecraft to arrive while the scientists who designed it were still working, while the technologies on board were still relatively current, while public and political interest could be maintained. The speed was achieved through a powerful Atlas V rocket with an additional kick stage, essentially stacking 3 rocket stages to accelerate New Horizons to escape velocity and then some. The spacecraft itself is relatively small and light, about 1,050 pounds, which helped. Less mass means less fuel needed to accelerate to high speeds, but that speed came with trade-offs. New Horizons couldn't slow down when it reached Pluto. There wasn't enough fuel on board to break from 31,000 mph relative to Pluto to anything approaching orbital velocity. The spacecraft would get one chance, one flyby, racing past at tremendous speed with only hours to collect data before continuing into the Kuiper Belt. At closest approach, New Horizons passed just 700 to 800 miles above Pluto's surface, closer than some satellites orbit Earth. At 31,000 mph, the spacecraft was moving so fast that Pluto's gravity barely affected its trajectory. It was there and gone in a matter of hours, capturing as much data as possible during the brief encounter. The high speed also affected communication. Radio signals take time to travel, about 4.5 hours from Pluto to Earth at light speed. When New Horizons made its closest approach on July 14, 2015, Mission Control had no way to intervene if something went wrong. The spacecraft was completely autonomous during the flyby, executing pre-programmed commands without any possibility of real-time human guidance. If there had been a problem, if the spacecraft encountered unexpected debris, if an instrument failed, if the targeting was off, Mission Control wouldn't know about it until 4.5 hours after it happened. And by then, the flyby would be over. New Horizons would be millions of miles past Pluto, and there would be nothing anyone could do. Fortunately, everything worked perfectly. The spacecraft executed its complex sequence of observations flawlessly, rotating to point different instruments at Pluto and Charon, collecting images and spectra and composition data, then turning to aim its antenna back at Earth to begin the long process of transmitting everything home. That transmission took over 15 months. The data rate from Pluto was incredibly slow, about 1 to 2 kilobits per second, roughly the speed of a dial-up modem from the 1990s. The spacecraft collected about 50 gigabits of data during the flyby, and sending all of it back to Earth at such slow speeds required patient waiting. The last data from the Pluto encounter arrived on October 25, 2016, more than a year after the flyby. Only then could scientists say they had the complete data set, everything New Horizons observed during those brief hours when it raced past the edge of the solar system. Since then, New Horizons has continued outward, now more than 5 billion miles from Earth, moving at about 31,000 mph relative to the Sun. It will never return. It doesn't have the fuel to turn around, and there's nowhere it would return to anyway. Its journey is one way, outward forever, carrying its cameras and instruments into the Kuiper Belt and eventually beyond, into interstellar space. The fastest launch, one brief encounter, and an eternal voyage into darkness. That's New Horizons, proof that sometimes you only get one chance and you have to make it count. On board New Horizons, sealed in a small container mounted to the spacecraft's interior, are approximately 30 grams of Clyde Tombaugh's ashes, the man who discovered Pluto in 1930. Tombaugh died in 1997 at the age of 90, 9 years before New Horizons launched. He never knew if anyone would visit the world he discovered. The mission was approved in 2001, funded and built in the early 2000s. But Tombaugh didn't live to see it. His widow and children, knowing about the planned mission, agreed to have a portion of his cremated remains placed aboard the spacecraft. It's a tradition in spaceflight, carrying small mementos, meaningful objects, symbols of what the mission represents. Other spacecraft have carried plaques, golden records, lists of names. New Horizons carried the discoverer himself. The container is small, roughly the size of a shotgun shell, inscribed with the words, "Interred herein are remains of American Clyde W. Tombaugh, discoverer of Pluto and the Solar System's third zone. Adele and Muron's boy, Patricia's husband, Annette and Alden's father, astronomer, teacher, punster, and friend, Clyde W. Tombaugh, 1906-1997. When New Horizons flew past Pluto on July 14, 2015, Clyde Tombaugh finally reached the world he discovered 85 years earlier. Not in person, he'd been gone for 18 years by then, but in the most literal sense possible for someone who died. His physical remains passed within 7,800 miles of Pluto's surface, closer than he'd ever dreamed possible when he spotted that faint speck moving against the background stars in 1930. There's something poignant about that completion. A young man building telescopes from car parts, spending years staring through a blink comparator, finding a dot that moved. And decades later, part of that man, physically, materially, traveling to that dot, seeing it up close, revealing it not as an abstract point of light, but as a real world with mountains and glaciers and blue skies. Tombaugh never got to see the images New Horizons sent back. He never saw the heart-shaped region named in his honor, Tombaugh Regio. He never saw Pluto resolved into anything more than a blurry disk in the best telescopes available during his lifetime. But his remains were there when New Horizons looked, when the spacecraft's cameras captured those images, when humanity finally saw Pluto as a place rather than a point. New Horizons is now more than 5 billion miles from Earth, carrying Tombaugh's ashes deeper into the Kuiper Belt. The spacecraft will eventually run out of power, probably sometime in the 2030s, and go silent. But it will continue coasting outward, carrying Tombaugh with it, into the region he discovered by finding its largest member. In tens of thousands of years, New Horizons will drift beyond the Kuiper Belt entirely, entering the vast empty space between stars. Tombaugh's remains will be aboard, traveling through the galaxy, part of the spacecraft that fulfilled his discovery by visiting the world he found. He spent his life looking at Pluto from afar. Now he's traveling past it, carried by the fastest spacecraft humans have ever launched, journeying into the darkness beyond, representing everyone who's ever looked up at the sky and wondered what's out there waiting to be discovered. Among the various mementos aboard New Horizons is a Pluto Not Yet Explored U.S. postage stamp issued in 1991, showing an artist's conception of Pluto and Charon with the words "Not Yet Explored" printed clearly across the design. When that stamp was issued, Pluto was indeed unexplored. Voyager 2 had flown past Neptune in 1989, but didn't have a trajectory that would take it near Pluto. No spacecraft had visited the outer Kuiper belt. Everything we knew about Pluto came from telescopic observations, measurements of brightness, spectroscopy revealing surface composition, occultations providing rough atmosphere data. The stamp was part of a series showing planets and space exploration, celebrating humanity's journey through the solar system while acknowledging that one world remained beyond our reach. It was aspirational, a reminder that exploration was incomplete, that there were still frontiers waiting. 15 years later, when New Horizons launched, mission planners included that stamp aboard the spacecraft. It would finally get to travel to the place it depicted, transforming from artistic representation to actual visitor. On July 14, 2015, the stamp passed within 7,800 miles of Pluto's surface. The words "not yet explored" became obsolete at that moment. Pluto was being explored right then by the spacecraft carrying the stamp that said it wasn't. The stamp holds a Guinness World Record as the farthest traveled postage stamp. At over 5 billion miles from its origin and still traveling, no other stamp has journeyed remotely as far. It started on Earth, perhaps in someone's collection or in a post office, printed as part of a routine postal service. And now it's beyond Pluto, beyond the main Kuiper belt, heading toward interstellar space. There's something wonderfully human about this. We put stamps on letters to help them travel from one place to another, usually just a few hundred or thousand miles. But this stamp traveled 3 billion miles, carried by a spacecraft moving 31,000 nautinerg, to reach the very world it depicted and declared unexplored. It's a reminder that not yet doesn't mean never. It means eventually, if we're patient and determined enough. It means that the things we label as out of reach today might be visited tomorrow, or next year, or next decade, or next century. But eventually, if we keep trying, we get there. The stamp represents aspiration fulfilled, a symbol of incompleteness that completed itself by traveling to the place it said hadn't been visited yet, and now it continues outward, carrying the message that was once true and is now false. Pluto, not yet explored, into regions that truly remain unexplored, regions we don't even have stamps for yet. 9 days before the Pluto flyby on July 4, 2015, New Horizons experienced a serious computer anomaly. The spacecraft went into safe mode, a protective state where all non-essential systems shut down and the spacecraft stops its scientific observations, instead focusing on staying alive and maintaining contact with Earth. The timing could not have been worse. New Horizons was just days away from the most important observations of the entire mission. The reason the spacecraft was built? The culmination of 9 years of travel. And suddenly it had stopped working properly. The problem was traced to a command sequence error that caused the main computer to become overloaded, trying to compress data while simultaneously preparing for the upcoming flyby observations. Essentially, the computer was asked to do too much at once, couldn't handle the load, recognized it was in trouble, and shut itself down to prevent damage. This erasure wiped out all the stored flyby commands, the detailed instructions that told New Horizons exactly when to point which instrument at what target, when to take images, when to collect spectra, when to turn the antenna toward Earth. Hundreds of commands representing months of careful planning, all gone. The mission team had 76 hours to rebuild everything. They worked around the clock, recreating the command sequence from backups and documentation, uploading it to the spacecraft, testing it as much as possible given the time constraints. They had to get it right. There would be no second chance, no opportunity to correct mistakes after the fact. They completed the restoration with only 4 hours to spare before the spacecraft would have started executing the now missing commands. 4 hours of margin out of 9 years of travel. If they'd needed more time, if the problem had been more complex, if they couldn't fix it fast enough, the entire mission might have failed. On July 7th, New Horizons resumed normal operations. The computer glitch was resolved. The command sequence was restored. The spacecraft continued toward Pluto, now less than a week away, with everything back on track. That glitch was one of the most dramatic behind-the-scenes moments of the mission. The public saw beautiful images and scientific discoveries, but the team experienced genuine crisis just days before success, a moment when everything nearly fell apart, saved only by desperate 24-hour work shifts and the expertise of people who knew every detail of the spacecraft and its programming. When New Horizons successfully flew past Pluto on July 14th, when the first images started arriving, showing that everything had worked perfectly, the relief among the team must have been overwhelming. Not just because the science was successful, but because they'd overcome a near-catastrophic failure just days earlier, rebuilt their mission from scratch under impossible time pressure, and succeeded anyway. It's a reminder that space exploration isn't just about the hardware or the science. It's about people solving problems under pressure, making decisions when everything is on the line, pulling together when failure seems imminent. New Horizons made it to Pluto not just because the spacecraft was well designed, but because dozens of people refused to let a computer glitch 9 days before the flyby destroy 9 years of work. They fixed it. They made it work. And Pluto revealed itself exactly as planned, as if the glitch had never happened at all. Before New Horizons arrived, planetary scientists thought they had a reasonable idea of what Pluto would look like. It would be cold, obviously. Dead, geologically speaking, frozen solid for billions of years, heavily cratered, like the Moon or Mercury, because small worlds cool quickly and cease geological activity early in their history. The surface would be ancient, perhaps 4 billion years old, covered in impact scars accumulated over the age of the solar system. Maybe there would be some interesting color variations from different ice compositions, but fundamentally, Pluto would be a frozen time capsule, preserving the conditions from the solar system's youth without much subsequent change. Every major prediction was wrong. Pluto turned out to be one of the most geologically active bodies in the outer solar system. It has surfaces that are effectively 0 years old, regions with no craters whatsoever, being constantly resurfaced by convection. It has flowing glaciers, active sublimation and condensation cycles, possible cryovolcanoes, dune fields, and evidence of ongoing geological processes. Scientists expected ancient, dead, boring. They got young, active, fascinating. The surprise wasn't just scientific, it was philosophical. It challenged fundamental assumptions about how geology works, about what small worlds can do, about the conditions necessary to maintain activity over billions of years. Small bodies should freeze quickly. They have high surface area to volume ratios, meaning they radiate heat efficiently. Within a few 100 million years, they should be cold all the way through, with all geological activity ceased. This is true for most small bodies, asteroids, most moons, small Kuiper Belt objects. But Pluto defied this expectation. Somehow it retained enough internal heat to drive convection in surface ice layers. Somehow it maintained enough energy to potentially drive cryovolcanism. Somehow, despite being only 1/5 the mass of Earth's moon and 40 times farther from the sun, it remained geologically alive. Scientists still don't fully understand the energy source. Radioactive decay in the rocky core generates some heat, but probably not enough to explain everything. Tidal heating from Charon is negligible. The system is tidally locked, so there's no ongoing tidal flexing. Seasonal heating from the sun is too weak to penetrate more than meters below the surface. Perhaps it's the insulating properties of certain ice layers, preventing heat from escaping efficiently. Perhaps it's chemical heat from ongoing reactions in a subsurface ocean. Perhaps it's residual heat from formation that dissipated more slowly than models predicted. Or perhaps it's some combination of all these factors, working together to keep Pluto just barely warm enough to maintain activity. The revelation that Pluto is geologically active transformed how scientists think about small worlds everywhere. If Pluto can remain active, what about other Kuiper Belt objects? What about small moons in the outer solar system? What about exoplanets orbiting distant stars? The lesson is that nature is more creative than our models. We build theories based on what we know, make predictions based on those theories, and then nature surprises us by doing something we didn't predict. The universe doesn't owe us the courtesy of behaving according to our expectations. New Horizons revealed that geology isn't just about size or distance from the sun or age. It's about complex interactions between composition, internal structure, heat sources, and boundary conditions. And those interactions can create activity in places we thought should be dead, can maintain dynamism in worlds we assumed were frozen. Pluto taught us humility. It reminded us that looking at something up close is fundamentally different from observing it from afar. And it demonstrated that the solar system still has secrets, still holds surprises, still rewards exploration with discoveries that challenge everything we thought we knew. When New Horizons analyzed Pluto's ancient surfaces, regions like Cthulhu Macula that appear billions of years old, based on their crater density, it found something puzzling: a deficit of small craters compared to model predictions. This observation has profound implications for understanding the Kuiper Belt's population structure and formation history. Impact craters form when objects from space collide with a surface. On airless bodies like Pluto, every impact leaves a permanent scar, unless subsequent geology erases it. The size distribution of craters reflects the size distribution of impactors. If there are many small objects in the region, you'll see many small craters. If small objects are rare, small craters will be rare too. Scientists have models predicting what the size distribution of Kuiper Belt objects should be based on theories of planet formation. These models generally predict a continuous distribution: lots of small objects, fewer medium objects, very few large objects, following something like a power law. But Pluto's ancient surfaces don't show this predicted distribution. There are fewer small craters than there should be, suggesting there were fewer small impactors than models predicted. This deficit tells us something fundamental about how the Kuiper Belt formed. If objects formed through gradual accumulation, dust sticking together into pebbles, pebbles into boulders, boulders into planetesimals, then there should be objects at all size scales, from meters to kilometers to hundreds of kilometers. But if objects formed through mechanisms like streaming instability, where clouds of small particles collapse directly into large bodies, then you'd expect a deficit of small objects. The building blocks went directly into making large objects, without spending much time as intermediate-sized bodies. The crater deficit on Pluto supports the streaming instability formation mechanism. It suggests the Kuiper Belt formed with objects that were born large, tens of kilometers across from the beginning, rather than growing gradually from smaller precursors. This finding extends beyond just Pluto. It tells us about the entire outer solar system's formation history. It constrains how quickly objects had to form, how dense the protoplanetary disk was, what mechanisms dominated in the cold outer regions. Of course, there are complications. Some of Pluto's surfaces are geologically young. They've been resurfaced recently, erasing any ancient craters. So scientists have to carefully identify which surfaces are truly ancient versus which ones just look old. And Neptune's migration might have selectively removed certain size objects from the Kuiper Belt through gravitational scattering. If small objects were preferentially ejected, that could also explain the crater deficit, even if the formation process created objects at all sizes. But the most straightforward explanation remains that small objects were simply rare from the beginning. The Kuiper Belt formed with a top-heavy size distribution, lots of large objects, few small ones, reflecting formation through rapid instability, collapse rather than gradual growth. This is detective work, reading history from craters, or rather, from the absence of certain craters. It's forensic geology, reconstructing ancient events from patterns in impact scars, using present observations to constrain past processes. Pluto's surface remembers, and what it remembers suggests that the Kuiper Belt's formation was different from what we initially imagined. That objects were born large in sudden collapses rather than growing slowly from dust. That the building blocks of the outer solar system, formed through mechanisms we're only beginning to understand. Pluto is one of the most colorful objects in the solar system. Enhanced color images from New Horizons reveal a surprising range: brilliant white nitrogen ice, deep charcoal black tholins, reddish-brown methane deposits, bluish-gray water ice, and everything in between. The colors aren't artistic interpretation or false color for emphasis. They're real, just enhanced to make the subtle variations visible to human eyes. If you could somehow see Pluto up close with perfect human vision under good lighting, you'd see these colors, though perhaps more mutedly than in the enhanced images. Each color tells a chemical story. The brilliant white of Sputnik Planitia comes from fresh nitrogen ice with very high albedo. It reflects about 90% of incident sunlight, making it one of the brightest natural surfaces in the solar system. The ice is pure, recently resurfaced by convection, uncontaminated by darker materials. The dark reddish-brown regions like Thulu macula get their color from tholins. Complex organic molecules formed when ultraviolet light breaks down methane. These molecules absorb most wavelengths of light, but reflect slightly more in the red end of the spectrum, giving them their characteristic dark red-brown appearance. The darker the region, the older and more processed the tholins, with billions of years of cosmic ray exposure gradually darkening the material. Methane ice appears as lighter reddish tints, especially on mountain peaks where methane frost has condensed. Fresh methane is colorless, but exposure to radiation quickly creates a slight red tint as the methane begins breaking down into more complex compounds. Water ice shows up as bluish-gray in enhanced color images. Pure water ice is actually white. It reflects all wavelengths equally. But Pluto's water ice is often mixed with trace amounts of other materials or has surface textures that scatter light preferentially, giving it a slight bluish tint in some lighting conditions. The boundaries between these color regions are sometimes sharp, almost painted-looking. The edge between Sputnik Planetia's white nitrogen and Cthulhu's dark tholins is particularly striking, a clear line dividing brightness from darkness, young geology from ancient geology, volatile ices from refractory organics. This color diversity makes Pluto one of the most contrastive bodies in the solar system. The difference in reflectivity between Sputnik Planitia, 90% albedo, and Cthulhu Macula, 5 to 10% albedo, is enormous. The bright regions reflect 10 to 20 times as much light as the dark regions. For comparison, Earth's albedo varies from about 5%, dark ocean, to maybe 80%, fresh snow, and most surfaces fall between 15% and 40%. Pluto's range is larger, more extreme, creating a world that looks almost painted, with stark boundaries between geological provinces. The colors also change over time. As Pluto orbits and seasons progress, nitrogen ice sublimates from some regions and condenses in others. Fresh white ice appears in areas that were dark. Dark surfaces emerge from beneath sublimating ice layers. The color map shifts slowly, repainting itself over decades and centuries as materials redistribute. If you could watch Pluto in time-lapse over a full 248-year orbit, you'd see the colors shifting. White expanding here, retreating there. Red regions darkening as tholins accumulate. Methane frosts appearing and disappearing on mountain peaks. It would be like watching a very slow kaleidoscope, colors flowing and changing in patterns driven by sunlight, temperature, and the patient chemistry of surface ices. Pluto doesn't just have color, it has a palette, a range of hues that maps directly onto its chemical and geological diversity, making visible the complex processes that shape its surface. New Horizons operates on approximately 200 watts of power, about the same as two 100-watt incandescent light bulbs. That's all the energy available to run everything. The computers, the communication system, all 7 scientific instruments, the heating systems to keep critical components warm, and the attitude control to keep the spacecraft properly oriented. This power comes from a single radioisotope thermoelectric generator, RTG, a device that converts heat from the radioactive decay of plutonium-238 into electricity. There are no solar panels. At Pluto's distance, sunlight is 900 times weaker than on Earth, and solar panels large enough to generate useful power would be impractically massive. The RTG contains about 11 kilograms of plutonium-238 dioxide. As the plutonium decays, it produces heat, about 4,400 watts of thermal energy when the spacecraft launched. Thermocouples convert a small fraction of this heat into electricity. The rest is radiated away as waste heat. When New Horizons launched in 2006, the RTG produced about 240 watts of electrical power. By the time it reached Pluto in 2015, radioactive decay had reduced output to about 200 watts. By 2025, it's down to around 170 watts. The power will continue declining by about 4 watts per year as the plutonium decays. Eventually, probably in the 2030s, power will drop below the threshold needed to operate the spacecraft's systems. The transmitter won't have enough power to send signals strong enough to reach Earth. The computers won't be able to run. New Horizons will go silent, drifting forever through space with no way to communicate, no way to send back data even if its instruments could still observe anything. But until then, that declining trickle of power is enough. The spacecraft was designed with extreme power efficiency in mind. Instruments only turn on when needed. The rest of the time, they're powered down to conserve energy. The main computer is a radiation-hardened processor that's slow by modern standards, but extremely power efficient. Communication requires the most power. The transmitter needs about 12 watts to send signals back to Earth, which might not sound like much, but that's 6% of the spacecraft's total power budget. When transmitting data, other systems have to be carefully managed to avoid exceeding available power. The Deep Space Network antennas on Earth that receive New Horizons signals are among the most sensitive receivers ever built. They can detect signals as weak as 10 more to 16 watts, 1/10,000,000th of a watt. Without these extraordinarily sensitive receivers, communicating with New Horizons would be impossible. The combination of the RTG's steady power output and the spacecraft's miserly power consumption is what makes deep space exploration possible. You can't plug in when you're 5 billion miles from Earth. You can't recharge batteries. You need a power source that works continuously for decades without maintenance in the vacuum and radiation of space, at temperatures that swing from extreme cold to moderate warmth. RTGs are that power source. They're not efficient. Only about 6% of the heat gets converted to electricity, with 94% wasted, but they're reliable. No moving parts, no chemical reactions that can stop, just plutonium slowly decaying, producing heat, generating electricity through the Seebeck effect year after year, until there's not enough plutonium left to generate useful power. 2 light bulbs worth of power, carefully managed, rationed to instruments and systems as needed, transmitted across billions of miles of space, received by antennas the size of football fields, decoded and turned into images and data that reveal worlds we've never seen. That's the engineering achievement that makes New Horizons possible. Doing more with less, stretching every watt as far as it can go. Scientists still don't fully understand what powers Pluto's ongoing geological activity after 4.6 billion years. Small bodies should have frozen solid long ago, yet Pluto shows evidence of surfaces younger than 10 million years. Some regions possibly as young as 180,000 years. Let's examine the energy budget. Pluto's rocky core contains radioactive elements, primarily uranium-238, thorium-232, and potassium-40, that decay slowly, releasing heat. This radiogenic heating is continuous and doesn't diminish quickly. The half-lives of these isotopes are billions of years. Computer models estimate that Pluto's core currently generates somewhere between 0.3 and 3 gigawatts of thermal power from radioactive decay. That sounds like a lot, but distributed across Pluto's entire volume, it amounts to only a few milliwatts per cubic meter, barely enough to notice. On Earth, radiogenic heating combined with residual heat from formation keeps the interior molten, despite 4.6 billion years of cooling. But Earth is much larger, about 170 times more massive than Pluto. Large bodies retain heat much more efficiently than small ones, because volume, which generates and stores heat, increases faster than surface area, which radiates heat away. Pluto should have cooled much faster than Earth. Early models suggested Pluto's interior would have frozen completely within the first billion years, with only a thin layer near the surface remaining even slightly warm from solar heating and radioactive decay in the crust. Yet New Horizons found evidence of recent geological activity. Sputnik Planetia's convecting nitrogen ice requires heat from below to drive the circulation. The possible cryovolcanoes, Wright Mons and Picard Mons, need an energy source to drive eruptions. The lack of craters on young surfaces means ongoing resurfacing, which requires energy. Where is this energy coming from? Several mechanisms have been proposed. First, the insulating properties of Pluto's ice layers might be trapping heat more efficiently than models predicted. If there's a layer of methane clathrate, that ice-like compound we discussed earlier, with thermal conductivity 5 to 10 times lower than normal ice, it would act like a blanket, preventing heat from escaping to the surface and space. Second, there might be ongoing chemical reactions in Pluto's interior generating heat. If a subsurface ocean exists and interacts with the rocky core through processes like serpentinization, reactions between water and certain minerals that release heat, this could provide additional energy beyond just radioactive decay. Third, the heat might be distributed unevenly. Perhaps most of Pluto's interior is cold and frozen, but localized regions, maybe beneath Sputnik Planitia, retain pockets of warmth that drive activity in those specific areas, while the rest of the world remains geologically dead. Fourth, perhaps our models of how quickly small bodies cool are wrong. Maybe there are physical processes we don't fully understand that allow small worlds to retain heat longer than simple thermal diffusion equations predict. Maybe ice behaves differently under Pluto's specific conditions of pressure and temperature than laboratory experiments suggest. Or perhaps, and this is a more radical possibility, Pluto is actually slowly freezing right now, and the geological activity we observe is a transitional phase. Maybe a billion years ago, Pluto was even more active, with more widespread cryovolcanism and more vigorous convection. And maybe a billion years from now, it will be completely frozen, with all activity ceased. We just happen to be visiting during the slow decline from active to dead. The honest answer is, we don't know. The evidence clearly shows that Pluto is geologically active in ways it shouldn't be according to simple thermal models. But identifying the specific energy sources and mechanisms that maintain this activity remains an open question. This uncertainty is what makes science exciting. We have observations that contradict our theories, which means our theories are incomplete. We need better models, more detailed observations, perhaps future missions that can measure heat flow directly, or probe Pluto's interior with seismic instruments or ground-penetrating radar. Pluto is teaching us that small worlds can remain active longer than we thought, through mechanisms we don't fully understand, powered by energy sources we're still trying to identify. It's a mystery written in young surfaces and convecting ice, waiting for us to solve it. We've explored less than 0.01% of Kuiper Belt objects, probably much less than that, actually. perhaps only 0.01% or 0.01%, depending on how you count. We've discovered about 3,000 Kuiper Belt objects so far, objects large enough and bright enough for our telescopes to detect at distances of 30 to 50 AU. But estimates suggest there are hundreds of thousands of objects larger than 100 kilometers across in the Kuiper Belt, and millions of objects larger than 10 kilometers. Of those 3,000 discovered objects, we have detailed observations of exactly one: Pluto. New Horizons is the only spacecraft that has ever visited a Kuiper Belt object up close, though it did perform a distant flyby of Arakoth, formerly called Ultima Thule, in 2019, a much smaller object about 36 kilometers long. So our detailed exploration fraction is approximately 2 objects out of an estimated population of millions to tens of millions. That's about 0.01% to 0.01%, 100,000th of 1% at most. Everything else we know about the Kuiper Belt comes from telescopic observations, measuring brightness, colors, orbital elements. We can infer compositions from spectroscopy, estimate sizes from occultations, calculate masses if objects have moons. But we can't see surface details, can't measure geological features, can't determine whether these objects are active or dead, young or ancient, simple or complex. Each discovered Kuiper Belt object is a world in its own right. Even the small ones, the ones only 100 or 200 kilometers across, have enough surface area to contain diverse geology, interesting chemistry, possibly subsurface oceans, or ancient impact structures or cryovolcanic features. And we visited one of them up close. One. This is the frontier. Not metaphorically, literally. The Kuiper Belt is the edge of direct human exploration, the boundary where we transition from places we've seen to places we've only imagined based on mathematical models and distant observations. Every new discovery in the Kuiper Belt raises more questions than it answers. When we discover a binary system, 2 objects orbiting each other, we wonder how they formed, whether they're contact binaries that merged and separated, whether they represent capture events or collision remnants. We don't know. We have theories, but no close-up observations to test them. When we discover an object with an unusual orbit, highly inclined or extremely distant, or in an unexpected resonance, we wonder what dynamical history produced that configuration. We can run computer simulations, but we can't verify them without observing the object's detailed characteristics. When we discover an object with spectral features suggesting methane or water ice or other compounds, we wonder about the geological processes operating on its surface. Is it geologically active like Pluto? Frozen solid like most asteroids? Something in between? We don't know. And we won't know until we send spacecraft to visit them. But sending spacecraft to the Kuiper Belt is extraordinarily difficult. It takes 9 to 10 years just to reach Pluto at 40 AU. Reaching objects at 50 AU takes even longer, and many interesting Kuiper Belt objects, the scattered disk objects, the detached objects, the extreme ones that orbit at hundreds of AU, are completely beyond our current reach with flyby missions. Orbiting a Kuiper Belt object would require even more time and energy. New Horizons couldn't slow down at Pluto. It would have needed exponentially more fuel to break from 31,000 mph to orbital velocity. A mission designed to orbit a Kuiper Belt object would probably need nuclear propulsion or electric propulsion operating for decades, slowly spiraling outward from the inner solar system. Such missions are being studied. Future spacecraft might use advanced propulsion systems to reach multiple Kuiper Belt objects, performing slow flybys or even brief orbital captures. But these missions are decades away from launch and decades more from arrival. In the meantime, the vast majority of the Kuiper Belt remains unexplored. Unknown worlds orbiting in the darkness, each one potentially as interesting as Pluto, each one with its own geological history and chemical composition and mysteries waiting to be discovered. We've scratched the surface. Literally, we've observed the surface of one major Kuiper Belt object in detail and briefly glimpsed one minor one. Everything else remains unknown, waiting patiently for the day when human spacecraft venture deeper into the solar system's third zone and reveal what's really out there. Pluto's demotion from planet to dwarf planet changed its significance in a way that's actually more scientifically meaningful than its original planetary status. When Pluto was the 9th planet, it was always the odd one out, the runt, the misfit that didn't fit the pattern, too small compared to the other planets, smaller than 7 planetary moons, orbit too elliptical, more eccentric than any other planet, orbit too tilted, 17 degrees, more extreme than any planet, composition too icy, more like a large comet than a terrestrial or gas giant world. Textbooks struggled to explain Pluto. Teachers had to add caveats. Well, Pluto is different because planetary scientists wrote papers trying to understand why one planet was so unlike all the others. Some proposed it was a captured Kuiper Belt object pulled into planetary status by Neptune's gravity. Others suggested it was an escaped moon of Neptune, ejected by some ancient collision. The underlying assumption was that Pluto was supposed to be a planet, and its weird characteristics needed explanation. It was a problem to be solved, an anomaly to be understood. But when Pluto was reclassified as a dwarf planet and recognized as a member of the Kuiper Belt, suddenly everything made sense. It wasn't an anomalous planet. It was a normal Kuiper Belt object. It was large for the Kuiper Belt, the largest known member, but not bizarrely so. Its orbital characteristics matched other Plutinos. Its composition matched other icy Kuiper Belt worlds. Pluto transitioned from being the worst planet to being the best dwarf planet, from anomalous outlier to representative exemplar, from problem to prototype. And scientifically, this is far more valuable. We have 8 planets closer to the Sun. We understand the planetary realm reasonably well. But the Kuiper Belt was barely known until recently. Having Pluto as the largest, most well-studied member of this population gives us a template for understanding thousands of other objects. When we discover a new Kuiper Belt object and measure its size, composition, and orbit, we can compare it to Pluto. Is it more or less icy, more or less geologically active, larger or smaller? The comparison provides context, helps us categorize and understand the diversity of the Kuiper Belt. Pluto is no longer competing with Jupiter or Earth. It's representing its true peer group, the icy worlds of the outer solar system, the frozen remnants of planetary formation, the population that outnumbers the planets by thousands to 1. From this perspective, Pluto's demotion wasn't a loss. It was a homecoming. It was recognizing Pluto for what it actually is, rather than forcing it into a category where it didn't belong. And being the king of the Kuiper Belt, the largest known member of the solar system's third zone, The first object discovered in this vast region, the ambassador for an entire population of worlds, is arguably more significant than being the smallest, most distant, most anomalous planet. Pluto gained kinship and lost isolation. It went from being alone, the only object in its region of the solar system, to being part of a family. It found its true context, its proper place in the cosmic hierarchy. The runt of the planets became the king of the Kuiper Belt, and in that transformation, Pluto became more scientifically important than it ever was as a planet, more representative of a major component of the solar system, more valuable as a window into understanding planetary formation and the outer reaches of our cosmic neighborhood. Pluto takes 248 Earth years to complete one orbit around the Sun. It was discovered on February 18, 1930, which means Pluto won't complete its first orbit since discovery until the year 2178, 153 years from now. Think about that time scale for a moment. Everyone alive today will be gone. Your children will be gone. Your grandchildren will likely be gone. Your great-great-great-grandchildren might be elderly when Pluto returns to the position where Clyde Tombaugh first spotted it, moving against the background stars. When that anniversary arrives in 2178, what will humanity be like? Will we still remember Pluto's discovery? Will we care about a dwarf planet discovered 248 years earlier by a civilization that must seem ancient to our descendants? Perhaps by then, we'll have visited Pluto multiple times. Maybe there will be permanent research stations there, or mining operations extracting nitrogen ice, or tourists visiting Sputnik Planitia. Or perhaps Pluto will have faded from consciousness, replaced by more interesting discoveries in other star systems as humanity spreads beyond the solar system. Or maybe, and this seems more likely, Pluto will still hold the same fascination it does today. The underdog world, the boundary marker, the first object discovered in the Kuiper Belt, forever significant as the gateway to understanding the solar system's outer reaches. The date will be February 18th, 2178, assuming we're still using the same calendar system. It will be 248 years to the day since Pluto's discovery, and Pluto will be back where it started, having completed one enormous circuit around the Sun, tracing out its eccentric ellipse through the outer solar system, crossing Neptune's orbit twice, experiencing 2 complete cycles of its century-long seasons. During that one Pluto year, the Earth will have completed 248 trips around the Sun. Humans will have experienced 248 summers and 248 winters. Approximately 10 human generations will have been born, lived, and died. The entire history of photography, spaceflight, computers, and internet will have occurred during less than half of one Pluto year. From Pluto's perspective, if a world can have a perspective, humanity is moving in fast forward. We rush around our tiny planet, orbiting the Sun 248 times, while Pluto orbits once. We discover Pluto, argue about whether it's a planet, send a spacecraft to visit it, and potentially establish a presence there, all within a fraction of Pluto's year. When Pluto completes its first post-discovery orbit in 2178, it will also be completing its first orbit since being visited by New Horizons. The spacecraft flew past in 2015, about 85 years into Pluto's current orbit. By 2178, it will be 163 years past the flyby, longer than the time between New Horizons' launch and the discovery of photography. Will there be ceremonies in 2178 marking the anniversary? Will people gather, physically or virtually, to celebrate one complete Pluto year since discovery? Will astronomers take measurements to compare Pluto's position, atmosphere, and surface to what we observed at the beginning of the orbit? Perhaps someone in 2178 will read these words, written in 2025, and smile at how we speculated about a future that, for them, has already happened. Perhaps they'll know things about Pluto we can't imagine, have answered questions we haven't thought to ask, have encountered surprises that make our current understanding look quaint. Or perhaps they'll be frustrated that we still haven't sent another mission to Pluto, that the 2015 flyby remains the only close-up observation, that budget constraints or political changes or simple neglect left Pluto unvisited for an entire orbital period. Either way, Pluto will complete its orbit in 2178, indifferent to human attention or lack thereof. It will arrive back at the starting point, having traveled approximately 23 billion miles, about 37 billion kilometers through space, following the same elliptical path it's followed for billions of years, continuing the patient journey that began long before humans existed and will continue long after we're gone. The year that started in 1930 hasn't finished yet. We're living through it, about 40% of the way complete. And it won't finish in our lifetimes, or our children's lifetimes, or for several generations more. But it will finish eventually, and Pluto will begin its next 248-year circuit, as it always has, as it always will. Pluto reminds us that the cosmos saves its surprises even at the edge of familiarity, that cold, distant, forgotten places can harbor beauty, complexity, and wonder we never expected. Before New Horizons, most people thought of Pluto as an abstract concept, a dot on a chart, the last entry in the list of planets, or the first entry in the list of dwarf planets, depending on when you learned astronomy. It was significant because of what it represented, the boundary of the planetary system, the frontier of our solar neighborhood, not because of what it actually was. No one expected beauty. No one anticipated that a world so small, so cold, so far from the sun would be visually stunning. But the images New Horizons sent back transformed Pluto from abstraction to place, the frozen heart that captured global imagination, the blue atmospheric haze layers glowing in backlit images, the stark contrast between brilliant white ice plains and dark ancient terrain, the mountains of frozen water rising thousands of meters, the red polar cap on Charon, the shadows through the atmosphere cast by peaks illuminated by the distant sun. These images are beautiful in the way landscapes on Earth are beautiful, not just scientifically interesting, but aesthetically moving. They evoke emotional responses, not just intellectual ones. They make you feel something about a world 3 billion miles away that you'll never visit, that no human will likely ever visit. That's a rare achievement. Most planetary science is about data, numbers, spectra, measurements. Beauty is usually secondary, a fortunate byproduct when the geology happens to create visually striking features. But on Pluto, beauty seemed intentional, as if the universe decided to create something stunning precisely where no one expected it. The heart especially, Tombaugh Regio, became iconic instantly. It's the perfect example of pareidolia turning scientific discovery into cultural phenomenon. We see a heart shape in a geological accident, and suddenly Pluto isn't just a dwarf planet in the Kuiper Belt. It's the world that wears its heart on its surface, the place that feels emotionally significant beyond its scientific value. And maybe that's appropriate. because Pluto has always been the dwarf planet, that captured hearts, the underdog, the outcast, the one that didn't fit, the one people defended passionately, despite having no personal stake in its classification. When Pluto was demoted, people felt genuine loss. Children protested, adults argued, state legislatures passed resolutions, not because Pluto's classification materially affected anyone's life, but because Pluto meant something emotionally. It represented something about fighting for the small, defending the misunderstood, refusing to let categorization systems diminish what we love. And then New Horizons showed us that Pluto deserved that emotional investment. It revealed a world that justified the affection people had always felt, that proved the underdog was actually fascinating and complex and beautiful in ways no one anticipated. Pluto taught us that beauty doesn't require warmth or proximity to Earth or familiar conditions. It can exist in frozen nitrogen plains far from the sun. It can emerge from geological processes operating at temperatures that would freeze every gas in Earth's atmosphere solid. It can surprise us precisely where we thought everything would be simple, dead, boring. The lesson extends beyond Pluto. It suggests that everywhere we look in the universe, no matter how cold, how distant, how seemingly inhospitable, we might find complexity and beauty we didn't expect. That nature's creativity extends to the very edge of our solar system and presumably beyond, into regions we haven't explored yet, worlds we haven't imagined yet. Pluto is a reminder that exploration rewards us with more than just data. It gives us new landscapes to marvel at, new perspectives on what's possible, new appreciation for the universe's ability to create beauty in unlikely places. And perhaps that's the most important discovery of all, not the geology or the atmospheric chemistry or the orbital mechanics, but the simple realization that even here, even in this cold, dark place at the edge of the sun's influence, there is wonder waiting for those patient enough to look. Everything we know about Pluto, every measurement, every image, every data point, comes from either telescopic observations or one spacecraft that flew past for a few hours in 2015. That's it. That's the sum total of human direct observation of Pluto. Decades of telescope time, plus one brief encounter, plus continued telescopic follow-up. No sample return missions, no orbiters studying the system for years, no landers measuring surface composition directly, just distant observation and one high-speed flyby. And from this limited data, we've constructed elaborate theories about Pluto's interior structure, its geological history, its atmospheric evolution, its formation mechanism, its future trajectory. We've written hundreds of scientific papers, created detailed computer models, made predictions that extend billions of years into past and future. How reliable is this knowledge? How much are we inferring beyond what we can actually measure? The honest answer is that much of what we know about Pluto is provisional, built on limited data, subject to revision, when better observations become available. This is true for all planetary science, but it's especially true for distant worlds we've barely observed. Consider the subsurface ocean. We have good indirect evidence. The way Pluto reoriented itself suggests a liquid layer between crust and core. But we haven't detected it directly. We can't send seismic waves through Pluto's interior to map density variations. We can't drill through the ice to sample the water. We can't even measure the ice shell thickness directly with certainty. The ocean might exist. It probably exists, but probably is not the same as definitely. Our knowledge is inference stacked on inference, models built on assumptions, conclusions drawn from limited data points. Or consider the cryovolcanoes. Wright Mons and Picard Mons look like volcanoes. They have the right morphology: domes with summit depressions, young surfaces, size consistent with large volcanic constructs. But we haven't observed them erupting. We haven't measured heat flow from their summits. We haven't sampled their composition to verify they're made of volcanic rather than impact materials. They're probably cryovolcanoes, but we can't be certain without more data. This uncertainty is inherent to exploration. When you visit a place once, briefly, you see a snapshot, one moment frozen in time, one configuration out of billions of possible states that world might occupy over its history. You make the best inferences you can from that snapshot, but you're always extrapolating, always guessing about what you didn't see. New Horizons observed Pluto during northern summer, southern winter, at one point in the 248-year orbital cycle. We don't know what Pluto looks like during other seasons. We don't know if the geological features we observed are typical or exceptional. We don't know if the atmospheric pressure we measured is higher or lower than average. We observed Charon's North Pole stained red with tholins, but we barely saw the South Pole. Does it look the same? Different? We don't know. We observed Pluto's 4 small moons tumbling chaotically, but we saw them at one moment in their tumbling cycles. Do they maintain these rotation rates, or do perturbations change them significantly over decades? We don't know. The limit of direct knowledge is sobering. It reminds us that planetary science is harder than it looks, that confident statements about distant worlds are often educated guesses rather than certain facts, that everything we think we know could be overturned by one new observation that contradicts our models. This doesn't mean our knowledge is worthless. Even limited observations are vastly better than no observations. Even brief encounters reveal truths about worlds that speculation alone could never uncover. Even provisional theories guide research and make testable predictions. But it does mean we should hold our knowledge lightly, remain humble about what we actually know versus what we've inferred, and stay open to being wrong when better data arrives. Pluto has surprised us repeatedly. It will probably surprise us again when we, or our descendants, return for a second look and find that things have changed, or that our interpretations were incomplete, or that the truth is stranger than our limited observations suggested. The limit of direct knowledge is also an invitation. It reminds us that there's more to learn, more to discover, more reasons to return. One flyby isn't enough. One snapshot isn't sufficient. We've scratched the surface, literally, and found wonders beneath. Imagine what we'd find if we could stay longer, observe more, dig deeper into the mysteries Pluto holds. When you look at Pluto's orbit, that elongated ellipse stretching from 29.7 AU at perihelion to 49.3 AU at aphelion, you're seeing a trajectory established billions of years ago, sculpted by Neptune's migration, stabilized by gravitational resonance, and destined to continue essentially unchanged for billions of years more. Pluto has completed this orbit approximately 18 million times since it formed 4.6 billion years ago. 18 million circuits around the Sun, each one taking 248 years, adding up to an almost incomprehensible span of time. During those 18 million orbits, Earth has completed approximately 4.6 billion orbits. The difference in timescales is staggering. While Earth races around the Sun once per year, Pluto takes its time, slowly tracing out its elliptical path, experiencing seasons that last longer than human civilizations. From Pluto's perspective, again, if a world can have a perspective, the inner solar system is a blur. Earth orbits 248 times while Pluto orbits once. Mercury orbits more than 1,000 times per Pluto year. The inner planets are spinning like a whirlwind, constantly changing positions, while Pluto moves with patient deliberation through its slow circuit. And from an even broader cosmic perspective, both timescales are vanishingly short. The Sun will remain relatively stable for another 5 billion years, enough time for Pluto to complete roughly 20 million more orbits. Then the Sun will expand into a red giant, its outer layers reaching perhaps as far as Earth's orbit, dramatically increasing solar radiation throughout the solar system. When that happens, Pluto's fate becomes uncertain. It's far enough that it won't be engulfed by the expanding Sun, but the increased radiation will dramatically heat its surface. The nitrogen ice will boil away. The water ice will sublimate. The methane will be lost to space. Pluto might develop a thick atmosphere, thicker than anything it's experienced in the past 4.6 billion years, as all its volatile materials turn to gas simultaneously. Or perhaps Pluto will be ejected from the solar system entirely. When the Sun loses mass as its outer layers disperse, the orbits of all the planets will expand. The changes in the gravitational field might destabilize Pluto's orbit, especially given its resonance with Neptune. Small perturbations amplified over millions of years could send Pluto into an unbound orbit, ejecting it into interstellar space. Or perhaps Pluto will survive largely intact, settling into a new orbit farther from the dying Sun, eventually orbiting a white dwarf, the dense stellar remnant left after the Sun sheds its outer layers. In this far future, Pluto might be cold again, frozen solid, all its atmospheric gases condensed back onto the surface, returning to the deep freeze that characterized most of its past. These aren't hypothetical scenarios from alternate universes. They're Pluto's actual future, billions of years from now. But as certain as anything can be in astronomy, Pluto will exist then, assuming no catastrophic collision destroys it. It will experience these transformations, and it will continue orbiting, or not orbiting if it's ejected, long after Earth is gone, after the Sun becomes a white dwarf, after the inner solar system has been transformed beyond recognition. This cosmic perspective is both humbling and elevating. Humbling because it reminds us how brief our existence is compared to planetary timescales. Humans have existed for a few 100,000 years, not even one Pluto orbit since anatomically modern humans evolved. Civilization has existed for maybe 10,000 years, about 4% of one Pluto orbit. Spaceflight has existed for 68 years, about 27% of one Pluto orbit. We're seeing Pluto at one moment in its immense history, moment number roughly 18,562 Sarn out of perhaps 40 million total, before the Sun's death transforms everything. We're visitors observing a tiny slice of Pluto's story, a few frames from a film, billions of frames long, but it's also elevating because we're here at all, able to observe and understand these vast timescales. We're creatures that live 70 or 80 years, and yet we can comprehend billions of years. We orbit the Sun at 30 kilometers per second, and yet we can understand the physics of a world that orbits at 4.7 kilometers per second, and takes 248 years to complete one circuit. We're small and brief, but we contain the universe. We're temporary, but we can grasp eternity. We're bound to Earth, but we can visit Pluto through our instruments and our mathematics, can know it in ways no other species on Earth ever will. Pluto will outlast us. It will still be there, still orbiting, still slowly tracing its elliptical path, long after humanity is gone, whether through extinction or transformation into something we wouldn't recognize. That's both melancholy and reassuring. Melancholy because it emphasizes our transience. Reassuring because it suggests the cosmos continues regardless of our presence, that beauty and complexity persist whether or not anyone is there to appreciate them. Pluto is lonely. It's 3 billion miles from the Sun, 40 times farther than Earth, orbiting in a region of space that's nearly empty. The nearest planet, Neptune, is at least 2.5 billion miles away at closest approach, and that's when Pluto crosses inside Neptune's orbit every 248 years. Most of the time, Neptune is even farther. The Kuiper Belt contains thousands of other objects, but they're spread across an enormous volume of space. On average, Kuiper Belt objects are separated by millions of miles. If you could stand on Pluto and look at the night sky, you'd see stars, lots of stars, undiminished by light pollution or atmosphere, but you wouldn't see any other worlds. The nearest Kuiper Belt objects would be too distant and too faint to see with the naked eye. Charon is Pluto's only close companion, hanging 12,000 miles away, always showing the same face, permanently fixed in the sky if you're on the Charon-facing hemisphere. But even Charon is a lonely presence, a silent companion in the darkness, tidally locked in eternal mutual gaze, unable to offer anything but gravitational partnership. This loneliness is part of what makes Pluto evocative. It's the outcast, the distant one, separated from the planetary family, orbiting alone at the edge of the Sun's influence. It's the world that exists in the cold and dark, with minimal sunlight, minimal warmth, minimal connection to the busy inner solar system. And yet, and this is the paradox, Pluto is connected. Connected to Neptune through orbital resonance, their periods synchronized by billions of years of gravitational interaction. Connected to the entire Kuiper Belt as its largest known member, the exemplar of a population numbering in the thousands or millions. Connected to the solar system's formation history, carrying information about how the outer regions evolved. Connected to Earth through the photographs we've taken, the data we've collected, the spacecraft we sent to visit. Connected to human consciousness through the name we gave it, the meanings we've attached to it, the emotions it evokes. New Horizons created a connection that never existed before. Before 2015, Pluto was observed but never visited. Light from the Sun traveled to Pluto, reflected off its surface, traveled back to Earth over 4.5 hours each way, and entered our telescopes. But nothing physical traveled from Earth to Pluto, just observation, just the passive receipt of reflected light. Then New Horizons flew past, carrying material from Earth, plutonium from terrestrial uranium deposits, computer chips manufactured in Earth factories, cameras designed by human engineers, and Clyde Tombaugh's ashes. It created a physical connection, a thread linking Earth and Pluto through the trajectory of a spacecraft. That connection persists even though New Horizons is long gone, now billions of miles beyond Pluto, continuing into the Kuiper Belt and eventually beyond. The radio signals New Horizons transmitted from Pluto traveled at light speed back to Earth, carrying information, data, images, completing the loop between observation and return. In a universe that's mostly empty space, where the average distance between objects is vastly larger than the objects themselves, any connection is remarkable. The fact that matter from Earth reached Pluto, observed it up close, and sent information back creates a relationship that transcends the physical distance. Pluto is lonely in space, but not in meaning. It's isolated in physical proximity, but connected through gravity, resonance, observation, and the deliberate attention we've given it. It's distant, but not forgotten. It's cold and dark, but not unloved. There's something profound about that, about caring for a place you'll never visit, about studying a world you'll never walk on, about creating connections across distances so vast they defy intuition. It's uniquely human, this ability to reach across the void and make relationships with worlds that couldn't care less about our existence. Pluto doesn't need us. It was there long before we discovered it, and it will be there long after we're gone. But we need Pluto, in a sense, as a reminder of how far we can reach, how much we can learn, how even the most distant and inhospitable places become less lonely when we extend our attention and instruments toward them. The loneliness and the connection coexist. Pluto orbits alone, and yet it's bound to us through the meanings we've given it, the missions we've sent there, the knowledge we've gained about it. Separate but related, distant but known, isolated but part of the larger story we tell about the solar system and our place within it. Pluto is a time capsule, a preserved sample of the materials and conditions that existed in the outer solar system 4.6 billion years ago, when the sun and planets were forming. Unlike Earth, which has been geologically processed for billions of years, its surface recycled through plate tectonics, its interior melted and differentiated, its atmosphere transformed by life. Pluto has changed relatively little since formation. Its composition is still largely primordial. Its interior structure, while somewhat differentiated, hasn't been completely reorganized by extreme heat and pressure. Small worlds like Pluto don't generate enough internal heat to melt completely. They warm up from radioactive decay and impacts during formation, but they cool relatively quickly. Much of Pluto's interior probably never fully melted. It softened, allowed some differentiation where dense rock settled toward the center, and lighter ice floated outward, but never became fully liquid like Earth's mantle. This means Pluto's rock and ice retain information about their origins. The isotopic ratios, the relative abundances of different forms of elements, reflect the conditions in the protoplanetary disk where Pluto formed. The mixture of water ice, nitrogen ice, methane ice, and rock represents the materials available at 20 to 30 AU from the forming sun. Compare this to Earth, where virtually every rock has been melted, metamorphosed, or chemically altered multiple times over billions of years. When you find a rock on Earth, it might be made of material that was once part of ancient seafloor, then subducted into the mantle, then melted and erupted as lava, then weathered into sediment, then buried and transformed into metamorphic rock, then uplifted and exposed at the surface. The rock's history is complex, and tracing back to the original primordial material is nearly impossible. On Pluto, much of the material has a simpler history. It formed in the protoplanetary disk, accreted into Pluto, underwent some mild heating and differentiation, and has remained relatively unchanged since. When you analyze Pluto's composition, you're getting a more direct measurement of solar system formation conditions. This is why sample return missions from Pluto, if they ever happen, would be scientifically invaluable. Bringing back material from Pluto and analyzing it in Earth laboratories with exquisitely sensitive instruments could reveal details about solar system formation that are impossible to determine from remote observations. What were the temperatures and pressures in the outer protoplanetary disk? What was the ratio of gas to solid material? How quickly did the disk cool? What were the abundances of volatile elements like nitrogen and carbon? All of these questions could be answered, or at least constrained, by analyzing Pluto samples. Comets also preserve primordial material, and we've collected samples from comets, the Stardust mission, and analyzed them. But comets are typically smaller than Pluto and have spent time in the inner solar system where heating from the sun altered their surfaces. Pluto has remained in the cold outer regions its entire existence, preserving its primordial state more faithfully. The Kuiper Belt as a whole is a time capsule region. All the objects there preserve information about the outer solar system's formation. But Pluto, as the largest known member and the only one we've visited up close, is the most accessible and best studied of these time capsules. When New Horizons analyzed Pluto's composition, measuring the abundances of nitrogen, methane, carbon monoxide, water ice, and rock, it was reading a message written 4.6 billion years ago. The message is in chemical language. This is what the outer protoplanetary disk was made of. This is the temperature and pressure where these materials condensed. This is the environment where large icy worlds formed. That message is still legible after billions of years because Pluto preserved it. The freeze of the Kuiper Belt prevented decay. The lack of extreme geological processing prevented erasure. And now, having finally learned to read that message, we can use it to understand not just Pluto, but the entire process by which our solar system came to exist. Pluto is memory frozen in ice. The solar system's childhood preserved in a world that never grew up, never transformed into something unrecognizable, but instead remained essentially unchanged for eons, waiting for someone to visit and read the history written in its composition. Imagine standing on Pluto's surface, though of course you'd need a heavily insulated spacesuit to survive the 230°C temperature and the near-vacuum atmospheric pressure. The sky above you would be nearly black during the day. Pluto's atmosphere is so thin, 100,000 times less dense than Earth's, that it scatters very little light toward the ground. Unlike Earth, where the sky is blue from Rayleigh scattering, Pluto's sky would appear almost as dark as space itself when you're on the surface looking up. The sun would be visible, a brilliant point of light, far brighter than any star, bright enough that you'd need eye protection to look at it directly. But it wouldn't appear as a disk the way it does from Earth. It would be just a very bright star, roughly 300 times brighter than the full moon appears from Earth, bright enough to cast shadows, bright enough to illuminate the landscape, but not bright enough to feel like daylight in the way we experience it. The light would have a different quality, cold, dim, twilight-like even at noon. Colors would be muted, your eyes would adapt, and after a few minutes you'd be able to see clearly, but it would feel like perpetual dusk, the particular quality of light about half an hour after sunset on Earth. If you're on the Charon-facing hemisphere of Pluto, you'd see Charon hanging in the sky. It would be enormous, appearing about 3.8 degrees across, roughly 8 times the angular size of our moon from Earth. It would be a gray-white disk, showing phases as sunlight illuminated different portions of its surface. Full Charon would be impressively bright, probably casting noticeable shadows and contributing significantly to the ambient light level. Charon would never move from its position in the sky. It would hang there, fixed, for your entire life if you lived on Pluto. Over the course of 6.387 days, you'd see it go through all its phases: full, gibbous, half, crescent, new, crescent, half, gibbous, full again. But it would never rise or set, never shift position relative to the horizon. If you're on the non-Charon hemisphere, you'd never see Charon at all. It would be permanently below the horizon, and you'd have no way to observe it except by walking around to the other side of Pluto. The stars would be brilliant. With no light pollution, no thick atmosphere to dim them, and your eyes fully dark adapted to Pluto's dim conditions, the stars would appear more numerous and brighter than from the darkest locations on Earth. The Milky Way would be a stunning band of light across the sky. You could see thousands of stars, perhaps faint nebulae and galaxies visible to the naked eye that are too dim to see from Earth. Earth would be visible, barely. It would appear as a pale blue dot, magnitude 2 or so, visible to the naked eye but not particularly remarkable. You couldn't see any detail. No continents, no clouds, just a blue-white point of light close to the sun. The sun's glare would make Earth difficult to observe without blocking the sun's light. But if you could do that, you'd see Earth, and perhaps even the moon, as a separate point next to it. The landscape around you would depend on where you're standing. In Sputnik Planitia, you'd see flat nitrogen ice plains stretching to the horizon, divided into those enormous convection cells like tiles. The surface would be bright white, reflecting the dim sunlight, almost glowing compared to the darker terrain surrounding the basin. In the highlands, you'd see water ice mountains rising thousands of meters, casting long shadows, their peaks bright with methane frost. You'd see valleys carved by nitrogen glaciers, ancient impact craters, dark deposits of tholins coating ancient surfaces. The horizon would be closer than on Earth, only about 50 kilometers away due to Pluto's small size. You could walk toward the horizon in slow motion bounds, given the weak gravity, and reach it in a few hours, then look back and see your starting point had dropped below your new horizon. The silence would be absolute. Sound requires atmosphere to propagate, and Pluto's atmosphere is so thin that sound waves barely travel at all. You couldn't hear your own footsteps. If you tried to speak, the sound waves wouldn't propagate more than a few inches. Communication would require radio or physical contact, touching helmets so vibrations could pass through the solid material. Time would feel strange. Days lasting 153 hours, more than 6 Earth days. The sun moving so slowly across the sky that you could watch its motion with the naked eye if you were patient enough. Seasons lasting decades. A sense that everything happens at a different pace. That urgency has no meaning on a world where geological processes operate on timescales of millions of years. You'd be standing on the edge of the solar system, on the boundary between the realm of planets and the vast Kuiper Belt beyond, looking at a sun that appears as little more than a bright star on a world that has preserved the conditions of the solar system's formation for billions of years. In a landscape that no human will probably ever visit, but that exists regardless, patient and indifferent to observation. On New Horizons, alongside Clyde Tombaugh's ashes and the not yet explored stamp, there's a small collection of other mementos, including a compact disc containing the names of 434,000 people who signed up to have their names flown to Pluto. This was a public engagement project by NASA, allowing anyone to submit their name to be included on the spacecraft. The names were inscribed onto a CD and mounted inside New Horizons, creating a passenger list of sorts for 34,000 Earth residents who made the journey to Pluto, at least symbolically. It's a modern version of an ancient human impulse, the desire to leave a mark, to say, "I was here," to be remembered. Humans have been carving their names into stone, writing them on walls, inscribing them on monuments for as long as we've had the ability to make permanent marks. But this is perhaps the most permanent mark ever made. The names on that CD are now traveling through the Kuiper Belt aboard a spacecraft that will never return. They've moved beyond Pluto, beyond the main concentration of Kuiper Belt objects, heading toward interstellar space at 31,000 MPa. In roughly 300,000 years, New Horizons will pass within a few light years of another star. Probably nothing particularly special, just a random encounter with a distant neighbor as the spacecraft drifts through the galaxy. The people whose names are on that CD will have been gone for thousands of generations. The civilization that built New Horizons might not exist anymore, or might have transformed into something unrecognizable. But the CD will still be there, carrying those 434,000 names. If it encounters nothing catastrophic, no collision with dust grains fast enough to destroy it, no close pass by a star whose tidal forces shred the spacecraft, it could persist for millions or even billions of years, potentially outlasting Earth itself. Is this meaningful? Does it matter that these names are traveling through space, unread by anyone, preserved on a disk that will never be recovered? Perhaps not in any practical sense. The names serve no function. They don't help the spacecraft navigate or collect data. They don't communicate anything to anyone because there's no one out there to receive the message. But perhaps meaning doesn't require an audience. Perhaps the act of sending something beyond the boundaries of our world, knowing it will persist longer than any human monument could ever survive on Earth, is meaningful in itself. Every name on that CD represents a person who felt some connection to the mission, who wanted to participate, however symbolically, in humanity's exploration of distant worlds. They're not scientists or engineers or astronauts. They're just people, teachers, students, office workers, retirees, who thought it would be cool to have their name fly to Pluto. And now those names have traveled farther than any human has ever traveled, have visited a world none of them will ever see, and will continue outward into the unknown, carrying a tiny piece of human identity into regions where no human will ever go. It's both grand and absurd. Grand because it represents the human spirit of exploration, the desire to reach beyond our limitations, the impulse to mark our existence on the cosmos. Absurd because, in the scale of the universe, a spacecraft carrying names is infinitesimally tiny, essentially invisible, mattering to no one and nothing except the beings who created it. But perhaps that's exactly the point. We do these things not because they matter to the universe. The universe doesn't care about us or our names or our spacecraft, but because they matter to us. Because we're creatures who create meaning even in meaningless contexts, who find significance even in symbolic gestures, who can look at a spacecraft vanishing into the darkness and feel connected to something larger than ourselves. Those 434,000 names are a message for the future, not for alien civilizations or distant observers, but for ourselves and our descendants. They're a reminder that we were here, that we reached out beyond our world, that we cared enough about exploration to send something of ourselves into the unknown. And maybe, someday, billions of years from now, when the sun has died and Earth no longer exists in any form we'd recognize, new horizons will still be drifting through the galaxy, carrying those names, the last remaining trace that humanity ever existed. A small disk with 434,000 signatures, still traveling, still preserved, still whispering into the void that we were here, we explored. We dared to send ourselves beyond the edge of the known world. Pluto teaches patience in a way few other objects in the solar system can. Everything about Pluto operates on time scales that dwarf human experience, that require patience, measured not in minutes or hours or even years, but in decades, centuries, millennia. A single day on Pluto lasts 153 hours, 6¼ Earth days. If you lived there, you'd wait almost a week for the sun to rise and set once. Imagine planning your life around rhythms that slow, where morning and evening are separated by 3 full days of Earth time. A single orbit, one Pluto year, takes 248 Earth years. No human has ever lived long, enough to see Pluto complete one orbit since its discovery. The people who will witness that completion in 2178 haven't been born yet. Most of them haven't even been conceived. Their parents probably haven't been born. The geological processes on Pluto operate on even longer timescales. The convection cells in Sputnik Planitia complete one turnover cycle every 500,000 years. The nitrogen ice rises from the bottom, spreads across the surface, cools, and sinks back down over a span of time, roughly 5 times as long as anatomically modern humans have existed. The tholins that coat ancient surfaces like Cthulhu Macula have been accumulating for billions of years, layer upon microscopic layer, building up the dark red-brown coating one molecule at a time, so slowly that meaningful change takes millions of years. The seasonal nitrogen transport, sublimating from one hemisphere, traveling through the atmosphere, condensing in the other hemisphere, happens over the course of decades. The deposits that form during 1 century-long winter sublimate during the next century-long summer, in cycles that repeat every 248 years, slowly enough that entire human civilizations rise and fall between depositions. This extreme patience is antithetical to modern human experience. We're accustomed to instant communication, rapid change, immediate results. We measure success in quarters, plan projects in years, consider decades to be long-term thinking. The idea of waiting 248 years for a single cycle to complete, or 500,000 years for a geological process to finish one iteration, is almost incomprehensible. But Pluto doesn't care about our timescales. It operates on the rhythms of celestial mechanics and planetary geology, processes that unfold according to physics, not according to human convenience. There's a lesson in that, a reminder that the universe operates on its own schedule, that some things simply cannot be rushed, that patience isn't just a virtue, but a fundamental requirement for understanding certain phenomena. The scientists who studied New Horizons data had to practice patience. The spacecraft took 9.5 years to reach Pluto, longer than some graduate programs, longer than many careers at a single institution. The team members who designed the mission in the 1990s and early 2000s had to wait until 2015 to see if their ideas would work. Some of them retired before the flyby. Some died before seeing the results of their work. And the data transmission took over 15 months. Every day, for 15 months, a tiny trickle of data arrived from Pluto, a few kilobits per second, slowly building up the complete picture. There was no way to speed it up. The distance imposed fundamental limits. You had to wait, day by day, for the full data set to arrive. This is patience of a different order than what most people experience. It's not, I'll wait 30 minutes for the pizza to be delivered, or I'll wait a year for my child to start walking. It's, I'll wait a decade for this spacecraft to arrive, or I'll wait my entire career for one crucial observation. And yet that patience was rewarded. The wait revealed a world more fascinating than anyone imagined, more geologically active than models predicted, more beautiful than expectations suggested. The patience wasn't wasted. It was essential, the only way to achieve the goal. Pluto is still teaching patience. It's still orbiting, still changing slowly, still undergoing seasonal transformations that won't be complete for decades. If we want to understand those changes, we need patience. We need to observe over multiple seasons, multiple Pluto years ideally, letting the full cycle play out before drawing conclusions. Future missions to Pluto will require even more patience. An orbiter would take 10 to 15 years just to arrive, then would need to observe for at least one Pluto rotation, 6.4 days, to see both hemispheres, probably much longer to see seasonal changes. The scientists who propose such missions today might be retired or deceased by the time results arrive. This is the lesson of Pluto, that some things worth knowing require patience, that understanding comes to those willing to wait, that the universe reveals its secrets on its own timescales, not ours. We can send our instruments, our spacecraft, our best efforts into the darkness, but then we must wait, years, decades, lifetimes sometimes, for the answers to return. In an age of instant gratification, where we expect immediate results and become frustrated by delays measured in seconds, Pluto stands as a monument to patience, a reminder that the most profound discoveries often require the most profound waiting. Pluto's meaning has transformed over the decades from its discovery to now, reflecting changing scientific understanding and cultural attitudes toward the solar system's frontier. In 1930, when Pluto was discovered, it represented completion. The solar system was whole. 9 planets, the final one found, the search for Planet X successfully concluded. Even though, as we now know, Planet X doesn't exist, and Pluto wasn't what Lowell was looking for. Astronomy textbooks could present a complete list. Children could memorize 9 planets and feel they'd learned the full inventory of worlds. Pluto was the period at the end of a sentence, the boundary marker saying, this is where the solar system ends. Beyond Pluto was just empty space, or so everyone thought. Through the mid-20th century, Pluto represented mystery. It was too distant to observe clearly, too small to show much detail through telescopes. Its mass was uncertain, its composition unknown, its surface invisible. It was the mysterious world, the one we couldn't quite understand, always just beyond the reach of our instruments. This mystery made Pluto romantic in a sense. It was the ultimate frontier, the place we could imagine anything about because we knew so little. Science fiction writers set stories there, imagining civilizations or strange phenomena or anything their creativity suggested, unconstrained by observed facts. In 2006, when Pluto was reclassified as a dwarf planet, its meaning shifted to controversy. It became the planet that was demoted, the world we rejected, a symbol of how scientific consensus can change, and how that change affects public perception. Pluto represented loss, specifically the loss of simplicity, the loss of the 9-planet system generations had memorized. But the controversy also made Pluto more culturally prominent than it had been before. When it was just the 9th planet, it was the least important one, the smallest, the most distant, the one barely mentioned in textbooks beyond, and finally, Pluto. But when it became the demoted planet, it became the people's planet, the underdog that everyone wanted to defend. Then in 2015, New Horizons transformed Pluto's meaning again. Suddenly, it wasn't just a controversy or a distant mystery. It was a real place, a world with geography, with colors, with active geology. The heart-shaped region made it feel personal, almost friendly, no longer cold and distant, but warm, metaphorically, and welcoming. Post-New Horizons, Pluto represents complexity. It's the world that shouldn't be geologically active, but is. It's the dwarf planet that's more interesting than many full planets. It's the king of the Kuiper Belt, the exemplar of a population we're only beginning to explore. And perhaps most importantly, Pluto represents surprise. It represents the idea that no matter how much we think we understand, nature can still astonish us. That small, distant, supposedly boring worlds can harbor beauty and complexity. That our predictions are often wrong and reality is more interesting than our models. This evolution of meaning, from completion to mystery to controversy to complexity, mirrors humanity's evolving understanding of the solar system itself. We once thought it was simple: sun, planets, done. Then we discovered it was complex. Asteroids, comets, Kuiper Belt, scattered disk, Oort cloud. We thought small worlds were dead and boring. Then we found they can be active and fascinating. Pluto's meaning will continue to evolve. Perhaps future discoveries will reveal even more surprising characteristics. Perhaps missions that haven't been conceived yet will show us aspects of Pluto we can't currently imagine. Perhaps in 100 years, Pluto will mean something entirely different to the people studying it, viewing it through scientific and cultural frameworks we haven't developed yet. But today, right now, Pluto means possibility. It means that the edge of the known world is more interesting than the center. It means that being small doesn't mean being insignificant. It means that places we've barely explored can teach us profound lessons about planetary science, about solar system formation, about the diversity of worlds in the cosmos. Pluto has transcended its astronomical classification to become a symbol of exploration, of underdog resilience, of the rewards that come from looking closely at things others dismiss as unimportant. And that meaning, more than any technical definition of what counts as a planet, is why Pluto continues to capture imagination and inspire wonder. There's something melancholy about knowing that no one alive today will ever see Pluto with their own eyes. not as New Horizons saw it, not up close, not as a resolved world with visible surface features. The journey is too long. Even with the fastest spacecraft we can currently build, the trip takes nearly a decade. By the time a spacecraft launched today reached Pluto, most people reading this would be significantly older. Many would have moved on to different phases of life. Some would have died. And that's just for a flyby. An orbiter would take even longer to arrive, and staying there would require years more. A crewed mission, humans actually traveling to Pluto, is so far beyond our current capabilities that it's not even seriously discussed, except as distant speculation. The children born today might live to see robotic missions return to Pluto, if funding is approved and missions are launched in the coming decades. But they almost certainly won't live to see humans land there. That achievement, if it happens at all, is probably centuries away. Perhaps never, if humanity decides that robotic exploration is sufficient and crewed missions to the outer solar system are too expensive, too dangerous, too difficult to justify. So Pluto will remain a world known only through instruments, only through cameras and spectrometers and radio signals transmitted across billions of miles. No human will walk on its nitrogen ice plains. No one will stand beneath its blue atmospheric haze and look up at Charon hanging motionless in the black sky. No one will climb its water ice mountains or watch nitrogen glaciers flowing at speeds measured in centimeters per year. The images we have, the photographs New Horizons sent back, are as close as we'll ever get. They're beautiful, detailed, scientifically valuable, but they're not the same as being there, as experiencing the landscape directly, as having the physical presence that transforms abstract knowledge into visceral understanding. This isn't unique to Pluto, of course. The same is true for most worlds in the solar system. Humans have stood on the moon, but that's the only world beyond Earth we've set foot on. Mars might be next, potentially within the lifetime of people alive today. But the giant planets, the moons of the outer solar system, the asteroids and comets, these will remain robot-only destinations for the foreseeable future, possibly forever. Still, there's something particularly poignant about Pluto. Maybe it's because Pluto has captured public imagination in a way other distant worlds haven't. Maybe it's because the New Horizons images were so stunning that they made people wish they could visit. Maybe it's because Pluto feels significant in ways that transcend its size or distance. The world at the edge, the boundary marker, the place that represents the farthest we've reached. Or maybe it's simply that humans want to explore, want to go places, want to see things with their own eyes rather than through cameras. And knowing that a place exists, a real place, with terrain and features and landscapes, but that we can never go there, creates a kind of longing that's fundamentally unsatisfiable. Future humans might have different capabilities. If humanity spreads through the solar system, establishing permanent settlements on the Moon, Mars, asteroids, moons of Jupiter and Saturn, then perhaps Pluto won't seem so impossibly distant. Perhaps with advanced propulsion, with spacecraft that can accelerate continuously rather than coasting for years, the journey time will shrink from decades to months. Perhaps virtual reality will become so sophisticated that experiencing Pluto through simulations built from orbital data will feel nearly indistinguishable from being there physically. Perhaps consciousness uploading or other transformative technologies will make the question of going there physically obsolete. But for us now, with our current technology and current lifespans and current understanding of physics, Pluto is unreachable. We can send our robots, our instruments, our cameras. We can know about Pluto, can understand it scientifically, can admire it aesthetically. But we can't go there. We'll never walk on its surface, never see its landscapes with our own eyes, never experience directly what it's like to stand at the edge of the solar system and look back at the sun as just a bright star among millions. The eyes that will see Pluto, if any ever do, haven't evolved yet. They belong to future humans or post-humans or artificial intelligences or whatever successors eventually inherit the solar system from us. We're the pioneers who discovered the world, who first revealed it, who gave it names and meanings. But we're not the ones who will walk there, and perhaps that's appropriate. Exploration has always been a multi-generational endeavor. The people who first imagined going somewhere are rarely the ones who arrive. The vision precedes the journey by decades or centuries. We're the visionaries, the dreamers, the early explorers who send scouts ahead. Our descendants, biological or otherwise, will be the ones who actually make the journey, if it's ever made. So we look at the images from New Horizons, and we wonder what it would be like to be there, and we acknowledge that we'll never know. The closest we can come is imagination, informed by data, constrained by physics, but still fundamentally limited to the realm of thought rather than experience. Pluto exists, real and solid and geological, orbiting patiently in the darkness. But for us, it remains forever out of reach, close enough to study, too far to visit, known in mind, but unknowable in body. Everything we know about Pluto, every image, every measurement, every insight, is an inheritance we're passing down to future generations. The data from New Horizons, carefully archived and preserved, will be analyzed for decades, possibly centuries, by scientists not yet born, using techniques not yet invented, answering questions we haven't thought to ask. This is how science works across time. The observations we make today become the foundation for understanding tomorrow. The spacecraft we send become permanent records, their data stored in archives that outlast the careers of everyone involved in the mission. Consider what happened with Voyager data. Those spacecraft flew past Jupiter, Saturn, Uranus, and Neptune in the 1970s and 1980s, sending back images and measurements. At the time, scientists analyzed what they could with the tools available, relatively primitive computers by today's standards, limited understanding of planetary processes, constrained by the theoretical frameworks of that era. But the data wasn't exhausted. Decades later, scientists are still finding new discoveries in Voyager data, analyzing images with modern software, applying new theoretical models, comparing with observations from later missions. The same photons captured 40 years ago keep yielding new insights because our ability to interpret them keeps improving. New Horizons data will follow the same pattern. The images of Pluto that were analyzed in 2015 and 2016 will be reanalyzed in 2035 using machine learning algorithms that don't exist yet. They'll be re-examined in 2055 in light of observations from future missions to other Kuiper Belt objects. They'll be studied in 2105 by people whose entire scientific framework might be different from ours, who might see patterns and meanings we couldn't recognize. The data is an inheritance, a gift from one generation of scientists to all future generations. It's not consumed by use. It doesn't depreciate or wear out. Every time someone analyzes it, it remains available for the next person, unchanged, ready to reveal new secrets to those with fresh eyes or better tools. This creates a kind of immortality. The scientists who designed New Horizons instruments, who planned the flyby sequence, who processed the first raw images. Most of them will be gone within a few decades. But their work persists. The data they collected outlives them, continuing to contribute to human knowledge long after the people who gathered it have died. There's something profound about that, about creating something that transcends your own lifespan, that continues to matter centuries after you're gone. Most human creations decay, buildings crumble, books deteriorate, even memories fade as those who remember die. But scientific data, properly archived and curated, can persist essentially forever, copied from one storage medium to the next, migrated across technological generations, always preserved because it continues to have value. Future scientists studying Pluto will probably never know the names of most people who worked on New Horizons. They'll cite the mission collectively, acknowledge the teams abstractly, but won't remember individuals. That's fine. Science is cumulative, building on countless contributions from countless people, most of whom fade into anonymous history. But the data remains, the measurements remain, the images remain. And through those data, the work continues, the discoveries continue. The inheritance continues to pay dividends to descendants who never met the people who made it possible. This is true for all planetary science, all astronomy, all science really. Every observation ever made, properly recorded and preserved, becomes part of humanity's permanent knowledge base. Every measurement adds to the collective understanding that future generations inherit. When we look at New Horizons images of Pluto, we're not just seeing a world. We're seeing the culmination of decades of work by thousands of people. The engineers who designed the spacecraft, the scientists who planned the observations, the technicians who built the instruments, the programmers who wrote the software, the administrators who fought for funding, the mission operators who commanded the spacecraft. All of those people contributed to the inheritance. And all of them, whether they realize it or not, are giving a gift to the future, to scientists not yet born, to students currently in elementary school who will become the planetary scientists of 2050, to people in 2100 who will analyze this data with tools we can't imagine. The inheritance extends beyond just the data. It includes the mission design, the engineering solutions, the operational techniques, the scientific methods. Other missions learn from New Horizons, what worked well, what could be improved, how to design flyby sequences for distant objects, how to manage power budgets over decades, how to transmit data efficiently across billions of miles. This knowledge compounds over time. Each mission makes the next one slightly easier, slightly better, slightly more capable. The inheritance grows with each generation, building on what came before, enabling achievements that would have been impossible without that foundation. So when we look at Pluto, at those stunning images, at that unexpected geology, at that frozen heart, we should remember that we're seeing not just a world, but an inheritance. A gift from the past, from the people who discovered Pluto in 1930, from the visionaries who proposed missions to explore it, from the teams who actually built and flew New Horizons, and a gift to the future, to everyone who will study Pluto in decades and centuries to come. We're stewards of this inheritance, temporarily. We're the generation that received it from those before us, and will pass it to those after us. Our responsibility is to preserve it, to add to it if we can, and to ensure it reaches the next generation intact and accessible. The data will outlive us all. Long after everyone currently reading these words is gone, the New Horizons data will still exist, still be available, still be revealing secrets about Pluto to curious minds. That's the inheritance. Not just what we learned, but the permanent record that will keep teaching long after we're gone. Could there be life on Pluto? Almost certainly not, but the almost is worth examining. Pluto's surface is hostile to any form of life we can imagine. Temperatures of 230 degrees Celsius would freeze any liquid water instantly. The thin atmosphere provides no protection from cosmic rays and solar radiation. There's no obvious energy source. Sunlight is 900 times weaker than on Earth, far too dim for photosynthesis. But life, as we've learned from studying Earth, is astonishingly adaptable. It exists in boiling hot springs, in Antarctic ice, in deep ocean trenches without sunlight, in highly acidic or alkaline environments, even in nuclear reactor cooling pools, absorbing intense radiation. The subsurface ocean on Pluto, if it exists, is the only place where life might theoretically survive. Liquid water, even supercooled water mixed with ammonia antifreeze, is the one known requirement for life as we understand it. And if that ocean interacts with Pluto's rocky core through hydrothermal chemistry, there might be chemical energy available. On Earth, hydrothermal vent ecosystems support complex webs of life in total darkness. Bacteria metabolize chemicals like hydrogen sulfide, methane, and iron compounds, extracting energy from chemical gradients rather than sunlight. These bacteria form the base of a food chain that includes tube worms, crabs, fish, entire ecosystems that function without photosynthesis. Could similar processes occur in Pluto's ocean? Theoretically, possibly, but it's extremely unlikely for several reasons. First, Pluto's ocean is probably very cold, around 70 degrees C, with ammonia antifreeze, possibly colder. On Earth, life exists in cold environments, but the coldest habitats where life is found are around 20 degrees in permafrost and sea ice. Below that, biochemical reactions slow so dramatically that metabolism becomes essentially impossible with chemistry we know about. Perhaps there's exotic biochemistry that can function at 70 degrees C, chemistry we haven't discovered because Earth doesn't provide environments that cold with liquid water. But we have no evidence for such chemistry, and it's hard to imagine how it would work given that molecular motion slows with temperature. Second, the energy available in Pluto's ocean is probably very limited. Hydrothermal activity requires heat, and Pluto's interior is cold. There might be slow chemical reactions between water and rock, but these would provide minimal energy, far less than Earth's vigorous hydrothermal systems. Life requires energy not just to exist, but to reproduce, to repair damage, to compete with other organisms or chemical processes. In a low-energy environment like Pluto's ocean, even if life could theoretically survive, it might not be able to do more than barely maintain itself. And that's assuming it could get started in the first place. Third, the origin of life probably requires conditions that Pluto never had. On Earth, Life likely originated in environments with cycles, day and night, wet and dry, freezing and thawing, that concentrated organic molecules and drove the chemistry toward increasing complexity. Pluto's ocean, if it exists, has been stable and unchanging for billions of years. No cycles, no concentration mechanisms, no obvious way for simple chemistry to become complex biology. So while we can't completely rule out life in Pluto's ocean, we simply don't know enough about the limits of biochemistry to say it's absolutely impossible. It's extraordinarily unlikely. The conditions are far more extreme than anywhere life exists on Earth, and there's no obvious energy source or origin mechanism. Still, extraordinarily unlikely is not impossible, and that tiny possibility is enough to make Pluto interesting from an astrobiology perspective. If life could exist there, if we somehow discovered evidence of even simple microorganisms in Pluto's ocean, it would revolutionize biology. It would tell us that life is even more adaptable than we thought, that biochemistry can function in conditions we considered impossibly hostile, that the habitable zone extends much farther into cold, dark, low-energy environments than our current theories predict. And if life exists in Pluto's ocean, then it probably exists in similar environments throughout the solar system and beyond. In the oceans of Europa, Enceladus, Titan, in countless Kuiper Belt objects, in exoplanets orbiting distant stars. Life might be common in the universe, not despite the cold and darkness, but because of its ability to adapt to those conditions. This is pure speculation, of course. We have no evidence for life on Pluto, and we probably won't get any without landing missions that can drill through the ice shell and sample the ocean. Missions that are decades away at minimum, possibly centuries, possibly never. But the question remains open. The tiny possibility persists. And as long as we can't completely rule it out, Pluto remains not just a geological curiosity, but a potential harbor for life. A remote, cold, dark oasis in the Kuiper Belt, where, against all odds, biology might have found a way. If Pluto teaches us anything beyond the specifics of its geology, its atmosphere, its history, it's this: that nature's creativity extends everywhere, that complexity can emerge in the least expected places, that the universe is more interesting than our models predict. We thought Pluto would be simple, a frozen ball of ice and rock, geologically dead for billions of years, covered in ancient impact craters, preserving the conditions of the early solar system. Without modification, we thought we understood what small, distant worlds should be like. We were wrong. Pluto is geologically active. It has convecting ice plains younger than 10 million years. It might have active cryovolcanoes. It has dune fields and flowing glaciers and nitrogen snow and methane frosts on mountain peaks. It has an atmosphere with dozens of haze layers that somehow defies our predictions by being colder than it should be. Every major assumption we made about Pluto before New Horizons turned out to be incorrect. Every confident prediction was contradicted by observations. Every model that said small worlds should be dead and boring was proven wrong by this one small world that refused to be boring. This is the lesson: humility. The acknowledgement that no matter how much we think we understand, nature can still surprise us, that our theories are approximations, our models are simplified, our predictions are educated guesses that might be completely wrong. Science progresses not just by confirming what we expect, but by discovering what we don't expect. The surprises teach us more than the confirmations. When observations match predictions, we learn that our understanding is probably correct. But when observations contradict predictions, we learn that our understanding is incomplete. And that's when real progress happens. Pluto surprised us in ways that changed planetary science. It forced us to reconsider how long small worlds can remain geologically active. It challenged our assumptions about the energy sources required for geology. It expanded our ideas about where and how complexity can emerge. And if Pluto can surprise us, a world we've observed for 95 years, that we've visited with spacecraft, that we've studied intensively, then imagine what else might surprise us in places we haven't looked yet. Imagine what might exist on other Kuiper Belt objects, or in the moons of the outer planets, or on exoplanets orbiting other stars. The universe is vast. We've explored an infinitesimally small fraction of it. And if our experience with Pluto is any guide, most of what's out there will be different from what we expect, more interesting than our predictions, full of surprises that force us to expand our understanding. This should be exciting rather than frustrating. Yes, it means our current theories are incomplete. Yes, it means we have more to learn, but it also means exploration continues to matter, that sending spacecraft to distant worlds continues to reveal new truths, that the cosmos hasn't exhausted its ability to astonish us. Pluto is a reminder that we live in a universe worth exploring, not just because we might find specific answers to specific questions, but because we might find questions we didn't know how to ask, that we might discover phenomena we hadn't imagined, that we might be surprised by beauty and complexity in the most unlikely places. So when we look at Pluto, at that frozen heart, those blue skies, those convecting ice plains, we should see more than just one world. We should see a promise that exploration rewards curiosity, that the unknown remains full of wonders, that no matter how much we learn, there's always more to discover. Pluto was supposed to be the last planet, the boundary marker, the end of the solar system. Instead, it became a gateway, the first member of the Kuiper Belt we explored, the prototype for understanding thousands of other worlds, the proof that the edge of the known is more interesting than the center. And perhaps that's the most important lesson of all, that frontiers matter, that edges are where discoveries happen, that the places we think will be boring often turn out to be fascinating if we're brave enough to look closely. Pluto looked back at us across 3 billion miles and whispered, "I'm not what you expected. Come closer. See what I really am." And when we did, when New Horizons flew past and showed us the truth, we discovered that this tiny, distant, supposedly insignificant world held wonders we never imagined. That lesson will stay with us. Long after the details of Pluto's geology are forgotten, long after the specific measurements fade from memory, the core truth remains. That nature is more creative than we are, that reality exceeds expectation, that the universe saves its best surprises for those patient and curious enough to explore it. Pluto taught us to look closely at the places others dismiss, to value the small and distant, to expect complexity everywhere, to remain humble about what we think we know, to stay curious about what we haven't discovered yet, and maybe, just maybe, to remember that sometimes the underdog, the outcast, the world that doesn't fit the categories we created, turns out to be the most interesting one of all. There's a sound Pluto makes that no human will ever hear, because it makes no sound at all. Sound requires atmosphere to propagate. On Earth, sound travels through air at about 343 meters per second. The vibrations of vocal cords or instruments or any mechanical motion create pressure waves that propagate through the medium of atmosphere, eventually reaching our ears and registering as sound. But Pluto's atmosphere is so thin, 100,000 times less dense than Earth's, that sound barely exists there. The pressure waves dissipate almost immediately. If you could somehow stand on Pluto's surface without a spacesuit and scream, the sound wouldn't travel more than a few inches from your mouth before fading into nothing. The nitrogen glaciers flowing at centimeters per year make no sound. The convection cells in Sputnik Planitia, slowly rising and sinking over hundreds of thousands of years, are utterly silent. The methane snow falling on mountain peaks drifts down without a whisper. The seasonal atmospheric surges at the poles when nitrogen ice sublimates explosively and pressure increases 1,000-fold. Even these dramatic events happen in silence. Impact. Events on Pluto. Meteorites striking the surface at cosmic velocities probably make brief sounds, the impact energy creating momentary pressure waves in the thin atmosphere. But those sounds fade quickly, absorbed by the surface or dissipating into the near vacuum, heard by nothing and no one. There's no wind noise even when winds blow at 20 mph, creating the dune fields we discussed. The air is too thin to make sound as it flows past obstacles. You could stand in a Pluto windstorm and hear nothing, feel nothing either, because there's not enough atmosphere to exert noticeable pressure on your body. This silence is profound, absolute in a way we rarely experience on Earth. Even in the quietest places on Earth, deep caves, isolated wilderness, soundproof chambers, there's always some noise, your heartbeat, your breathing, the rush of blood in your ears. But on Pluto, if you could somehow exist there without a spacesuit, without life support, you'd experience true silence. Not just the absence of environmental sound, but the absence of sound itself as a meaningful phenomenon. It's a silence that's been unbroken for billions of years. Since Pluto formed, since the solar system coalesced from a cloud of gas and dust, Pluto has orbited in this silence. The only sounds it's ever experienced, if a world can experience sound, are the impacts, the brief moments when meteorites strike with enough energy to create temporary pressure waves. New horizons passed in silence. The spacecraft racing by at 31,000 mph made no sound in Pluto's thin atmosphere. There was no sonic boom, no rush of air past the spacecraft body. Just silent motion, a human-made object crossing Pluto's sky unheard, observing but never announcing its presence except through radio signals that Pluto couldn't detect or care about. If humans ever go to Pluto, if astronauts land there centuries from now, they'll experience this silence. Inside their suits, they'll hear mechanical sounds, air circulation, suit servos, radio communications. But outside, nothing. They could bang on rocks, could drop tools, could try to make noise, and they'd hear nothing beyond the vibrations conducted through their suits from direct contact. It would be profoundly eerie. Humans are accustomed to sound as a sense that provides spatial awareness. We hear things before we see them, hear them behind us or around corners, use sound to navigate and understand our environment. On Pluto, that sense would be almost entirely absent. You'd rely on vision alone with no audio cues about what's happening beyond your field of view. The silence would be isolating in a way that's hard to describe, even more than the visual isolation of the dim sun and the empty landscape. The acoustic isolation, the complete absence of any sound from the environment, would emphasize how far from Earth you are, how alien this place is, how fundamentally different from the world where sound and atmosphere and life are ubiquitous. But perhaps there's also something peaceful about that silence. No noise pollution, no unwanted sounds, just pure, absolute quiet, the kind of silence people seek in meditation or solitude, taken to its ultimate extreme. Pluto orbits in this silence, has always orbited in this silence, will continue to orbit in this silence for billions of years more, until the sun's death changes everything, or until, impossibly, improbably, someone arrives to briefly interrupt the quiet with the contained sounds of their machinery and their presence, before leaving again and restoring the eternal soundlessness. The silence of Pluto is the silence of space itself, the default state of the universe in places where atmosphere is too thin to carry pressure waves, where no one exists to hear even if sounds could propagate. It's a reminder that sound is a local phenomenon, a quirk of dense atmospheres and evolved sensory organs, not a fundamental property of reality. And in that silence, Pluto continues its patient orbit, its geological processes operating in perfect quiet, its atmosphere cycling between surface and sky without wind noise or rain sounds, its ice flowing and convecting and sublimating all in absolute soundlessness. A world where nothing is heard and nothing needs to be heard, where events happen in visual and thermal and chemical languages, but never in acoustic ones. We are the only beings in the universe, as far as we know, who are aware of Pluto's existence. This creates a responsibility, strange as that might sound. Pluto doesn't know it exists. It has no consciousness, no awareness, no capacity to appreciate its own geology or atmosphere or moons. It simply is, matter arranged into a particular configuration, following physical laws, orbiting the sun without thought or intention. But we know Pluto exists. We've observed it, measured it, photographed it, named its features, studied its processes. We've assigned it meaning beyond its physical properties, cultural significance, historical importance, emotional resonance. This knowledge creates responsibility, not legal or moral responsibility in the traditional sense. Pluto doesn't need protection or advocacy. It will continue existing regardless of what we think about it. But epistemic responsibility, the responsibility that comes from knowing something, from being the only witnesses to certain truths. We are responsible for preserving the knowledge we've gained about Pluto. The data must be archived, maintained, kept accessible for future generations. The images must be preserved. The scientific papers must remain available. The story of Pluto's discovery and exploration must be told and retold, so it doesn't fade from collective memory. This isn't automatic. Knowledge can be lost. Ancient civilizations made astronomical observations that weren't recorded or weren't preserved, and we'll never know what they saw. Libraries burn. Digital archives become corrupted. Formats become obsolete and unreadable. Without active curation, even carefully gathered data can disappear. NASA and other space agencies understand this responsibility. They maintain archives of planetary data going back decades. They migrate data across storage media as technologies evolve. They ensure that New Horizons data will remain accessible for as long as human civilization persists. But the responsibility extends beyond just preserving data. It includes communicating what we've learned, making Pluto's story accessible to people who aren't scientists, who will never read technical papers, but who might be inspired by images or narratives or the simple fact that we visited a world 3 billion miles away. It includes educating future scientists, the students who will study Pluto using our data, who will build on our discoveries, who will ask new questions we haven't considered. They need not just access to data, but context, understanding of how it was collected, awareness of its limitations and uncertainties. It includes honest representation, not overhyping discoveries, not making claims beyond what the data supports, acknowledging what we don't know as clearly as we state what we do know. Pluto deserves accurate representation, not sensationalized mischaracterization. And perhaps most importantly, it includes maintaining the capacity and will to continue exploring. We are responsible not just for preserving past knowledge, but for expanding future knowledge, for supporting missions to other Kuiper Belt objects, for developing technologies that enable deeper exploration, for maintaining public and political support for planetary science. This might seem grandiose, claiming responsibility for a distant world that doesn't need anything from us. But consider the alternative. If we don't maintain this knowledge, if we don't continue exploring, if we allow what we've learned to be lost or forgotten, then Pluto returns to being just a point of light in telescopes. Its complexity, its beauty, its scientific significance, all of that exists only in our awareness. Remove the awareness, and it might as well not exist from a human perspective. We are Pluto's witnesses. For 4.6 billion years, Pluto orbited unseen, unknown, unappreciated. For 95 years, we've known it exists but understood it poorly. For the past decade, we've actually known what it looks like up close, have understood something of its nature. That knowledge is precious. It represents centuries of technological development that made observation possible, decades of mission planning and execution, billions of dollars of societal investment, and the intellectual labor of thousands of people across multiple generations. To let that knowledge be lost, to allow Pluto to fade back into obscurity, would be a kind of cosmic negligence, a failure to honor the effort invested in understanding this world, a waste of the opportunity we've been given to witness something remarkable. So we have responsibility to remember, to preserve, to communicate, to continue exploring when possible, to treat the knowledge we've gained with the care it deserves, not because Pluto needs anything from us, but because we need to be the kind of civilization that values knowledge, that preserves understanding, that honors the effort to comprehend the universe we inhabit. Pluto doesn't care whether we remember it or not, but we should care. We should care that we're the only beings who know this world exists, that we're the temporary custodians of knowledge about it, that we have the privilege and burden of being Pluto's chroniclers and advocates and witnesses. The responsibility is light. It requires no personal sacrifice, no great hardship, just attention, just care, just the commitment to ensure that what we've learned isn't lost, that future generations inherit our understanding and build upon it, that this tiny, distant, wonderful world remains known and appreciated for as long as human consciousness persists. Even after new horizons, even after all we've learned, Pluto remains distant in ways that transcend mere physical distance. It's 3 billion miles away, yes. Light takes 4.5 hours to travel from Pluto to Earth. A spacecraft takes a decade to make the journey. These are staggering physical separations, distances so vast they challenge intuition. But there's another kind of distance, epistemic distance, the gap between what we know and what we don't know, between observations and understanding, between data and truth. We have high-resolution images of one hemisphere of Pluto, the side that was illuminated and facing new horizons during the flyby. The other hemisphere we've seen only in lower resolution or not at all. What's there? Are there features as interesting as Sputnik Planitia? Ancient terrain like Cthulhu Macula? Something entirely unexpected? We don't know. We observed Pluto at one moment in its 248-year orbit, northern summer, southern winter, at a particular point in the seasonal cycle. What does Pluto look like at other times? How much does it change over decades or centuries? We've seen one snapshot from a billions of frames long movie, and we're trying to understand the plot from that single image. We measured atmospheric properties at one time, from one location, under one set of conditions. But we know the atmosphere changes dramatically with seasons, potentially collapsing and reforming over time. How much variation exists? What's the range between maximum and minimum atmospheric pressure? We have hints, but we don't have comprehensive observations. We detected evidence for a subsurface ocean, but we haven't confirmed it directly. We can't measure its depth, its salinity, its temperature, whether it's global or localized, whether it connects to surface features through cryovolcanism. It's a hypothesis supported by evidence, but not proven beyond doubt. We've identified possible cryovolcanoes, but we haven't observed them erupting. Are they active, dormant, extinct? We can't tell from static images. We need long-term observations, repeated visits, monitoring over years or decades. We've measured the composition of surface ices, but only at the resolution of New Horizons spectrometers from a fast flyby. Detailed chemical analysis, the kind you get from landers with sophisticated instruments or from returned samples analyzed in laboratories, remains beyond our reach. So despite all we've learned, despite the revolutionary discoveries from New Horizons, Pluto remains mostly unknown. We've scratched the surface, literally and figuratively, but the bulk of what could be known about this world still eludes us. This distance between observation and understanding is perhaps more significant than the physical distance. Physical distance can be crossed with technology and time, but epistemic distance requires not just visiting, but staying. Not just observing, but measuring comprehensively. Not just seeing, but truly understanding. And true understanding of a world requires more than one brief flyby. It requires orbital missions that observe over multiple seasons. It requires landers that measure surface properties directly. It requires sample returns that bring material back for exhaustive laboratory analysis. It requires time, years, decades, potentially centuries of continued observation and study. For Pluto, we haven't even begun that deep understanding. We're still at the reconnaissance stage, the initial survey that reveals the broad characteristics but misses the details. We know Pluto is interesting, but we don't fully understand why it's interesting. We know it's active, but we don't know what drives that activity. We know it's complex, but we don't know the extent of that complexity. The distance still remaining isn't measured in miles, but in questions. Hundreds of questions, thousands maybe, about Pluto's interior structure, its atmospheric dynamics, its seasonal evolution, its geological history, its chemical composition, its relationship with Charon, its role in the broader Kuiper belt. Each question represents a gap in knowledge, a distance between where we are and where we want to be in understanding. And closing those gaps requires not just time and money, but priority. The collective decision that Pluto matters enough to continue studying, that the remaining distance is worth crossing. That decision hasn't been made yet. The funding for return missions doesn't exist. The priority among competing scientific targets hasn't been established. The timelines for such missions stretch decades into a future where different people will make different decisions based on different priorities. So Pluto remains distant, close enough that we've seen it, far enough that we barely understand it, near enough to tantalize us with glimpses of complexity, remote enough that the full picture stays hidden, discovered but not known, visited but not explored, observed but not comprehended. The distance still remaining is the distance between curiosity and understanding, between seeing and knowing, between the first encounter and the deep familiarity that only comes from sustained attention over time. And that distance might never be fully crossed. Not because it's impossible technically, but because it requires resources and commitment that might never be allocated. Pluto might remain forever at this intermediate distance, known well enough to be interesting, not known well enough to be understood, close enough to inspire wonder, far enough to remain mysterious. Perhaps that's appropriate. Perhaps some things should remain partially unknown, should retain their mystery even after discovery. Perhaps the distance, both physical and epistemic, is part of what makes Pluto meaningful, what keeps it in our imagination as the distant world at the edge, the frontier that beckons but never fully reveals itself. The distance still remaining is also a promise that there's more to discover, more to learn, more to understand. That exploration isn't finished just because we visited once, that Pluto still holds secrets waiting for the day when we, or our descendants, return with better instruments, longer observation times, and the determination to finally cross the remaining distance and know this world as fully as we know our own. After all our observations, after new horizons, after years of analysis and modeling, we still don't know what powers Pluto's ongoing geological activity. This isn't a minor detail. It's one of the central mysteries about this world. The energy budget doesn't add up. When you calculate how much heat Pluto should have, from radioactive decay in its rocky core, from residual warmth from formation, from any other known source, the numbers are too low to explain what we observe. Nitrogen ice convecting in Sputnik Planitia requires heat to drive the circulation. The warm ice rising from below has to be warmer than the cold ice above, and maintaining that temperature difference requires continuous energy input. The convection we observe suggests heat flow higher than our models predict. The possible cryovolcanoes, if they're real, if they've erupted recently, require even more energy. Melting or partially melting ice, erupting it to the surface, building mountains kilometers high. These processes need significant heat sources operating relatively recently in geological terms. The young surfaces, regions with ages of only 10 million years or less, indicate that resurfacing processes have operated throughout Pluto's history, not just in the distant past when the world was warmer. This implies ongoing energy sources, not just the slow dissipation of primordial heat. Where is this energy coming from? Radioactive decay provides some heat. Uranium, thorium, and potassium in Pluto's rocky core decay slowly, releasing energy. But calculations suggest this heat is insufficient by itself. Pluto is too small, too cold, with too little radioactive material to generate the heat we're inferring from observations. Tidal heating is negligible. The Pluto-Charon system is tidally locked. There's no ongoing flexing, no tidal friction generating heat, the way there is on Jupiter's moon, Io, or Saturn's moon, Enceladus. Whatever tidal heating occurred happened billions of years ago during the locking process, and that heat should have dissipated long since. Solar heating is far too weak. At 40 AU, the sun provides only 1/1600th the heating it provides to Earth. This is enough to drive atmospheric circulation and surface sublimation, but it doesn't penetrate deep enough to heat the interior, where convection and possible cryovolcanism are driven. Chemical heat from reactions in a subsurface ocean might contribute. If water interacts with certain minerals in the rocky core through serpentinization, reactions that consume rock and produce new minerals while releasing heat, this could provide additional energy. But would it be enough? And would these reactions continue for billions of years without exhausting the available reactants? Perhaps the interior hasn't cooled as much as we think. Maybe our thermal models are wrong. Maybe ice under Pluto's specific conditions of pressure, temperature, and composition conducts heat differently than laboratory measurements suggest. Maybe there are insulating layers we don't know about that trap heat more efficiently than predicted. Or perhaps the energy source is intermittent rather than continuous. Maybe Pluto goes through cycles, periods of high activity when stored heat is released, followed by quiescent periods when heat slowly builds up again. We might be observing Pluto during an active phase, seeing processes that won't continue indefinitely. There's also the possibility that we're misinterpreting the observations. Maybe the surfaces aren't as young as we think. Maybe the convection is slower and requires less heat than our models suggest. Maybe the features we interpret as recent cryovolcanoes are actually something else, perhaps modified impact structures or other geological formations that don't require recent volcanism. But taking the observations at face value, accepting that Pluto really is geologically active, really does have young surfaces, really does have convecting ice plains, we're left with an energy budget problem. The heat has to come from somewhere, and we don't know where. This is frustrating, but also exciting. It means there's something fundamental we don't understand about small, icy worlds. Either there are heat sources we haven't identified, or heat retention mechanisms we haven't accounted for, or processes operating on Pluto that don't operate on other worlds we've studied. Solving this mystery requires more data. Orbital missions that can measure heat flow directly by observing infrared emission from the surface over time. Seismic instruments on landers that can probe interior structure and potentially detect convection currents or volcanic activity. Gravitational measurements during close flybys that can reveal density variations indicating liquid layers or compositional differences. Until we get that data, if we ever get it, the energy source remains one of Pluto's great unsolved mysteries. We know the world is active. We can observe the effects, but we don't understand the cause, don't know what's powering these processes, don't fully comprehend how a world this small and cold can maintain geological activity for billions of years. It's a reminder that observation and understanding are different things. We can see what Pluto does without knowing why it does it. We can measure effects without identifying causes. We can describe phenomena without explaining mechanisms. The energy mystery is Pluto's way of telling us, you've looked at me, but you don't truly know me yet. You've seen my surface, but you don't understand my interior. You've measured my present, but you don't comprehend my past or predict my future. And until we solve this mystery, until we identify the energy source that keeps Pluto geologically alive, our understanding remains incomplete. We're still missing a fundamental piece of the puzzle, still lacking the key insight that would make everything else make sense. The energy is there. We can see its effects, but its source remains hidden, waiting for some future observation or theoretical breakthrough to reveal what we're missing, to explain how this tiny, distant, cold world maintains warmth and activity when by all rights it should have frozen solid billions of years ago. For every Kuiper Belt object we've discovered, including Pluto, there are probably thousands or tens of thousands we haven't found yet. These undiscovered worlds orbit in the darkness, unknown, unobserved, waiting for telescopes sensitive enough to detect them. The largest undiscovered Kuiper Belt object might be comparable to Pluto in size. Our surveys aren't complete. There are regions of sky we haven't searched thoroughly, and objects at certain distances or with certain orbital characteristics are harder to detect than others. There could be another Pluto-sized world out there right now, orbiting somewhere between 50 and 100 AU, and we simply haven't found it yet. Not because it doesn't exist, but because we haven't looked in the right place at the right time with sufficient sensitivity. And beyond the largest objects, there are certainly thousands of worlds in the 500 to 2,000 kilometer size range that remain undiscovered. These are worlds large enough to be geologically interesting, possibly spherical, possibly differentiated, possibly with subsurface oceans or cryovolcanic features or complex surface chemistry. Each one is unique. Each one has its own composition determined by where in the protoplanetary disk it formed, its own thermal history based on its size and internal structure, its own surface features shaped by billions of years of impacts, sublimation, and possible geological activity. And we know almost nothing about most of them. We don't even know they exist, much less what they look like or what processes operate on their surfaces. This is humbling. We've explored one Kuiper Belt object up close, Pluto. We've done a distant flyby of one more, Arakoth. That's it. 2 objects out of potentially millions. It's like trying to understand Earth's ecology by studying 2 species, say, a human and an ant. You'd learn something certainly, but you'd miss the vast diversity of life, the range of adaptations, the complexity of ecosystems. You wouldn't understand how limited your sample was until you discovered the other millions of species. The Kuiper Belt is the same. Pluto showed us one example, an active, complex, geologically diverse world. Arakoth showed us another, a contact binary, primitive and unprocessed, shaped by gentle accretion rather than violent collision. But what about the rest? Are they more like Pluto or more like Arakoth? Or are they completely different, with surface features and geological processes we haven't imagined yet? We don't know, and we won't know until we explore more of them. But exploring the Kuiper Belt is difficult and expensive. Each mission takes a decade or more to arrive. We can only launch so many missions, visit so many targets, so the vast majority of Kuiper Belt worlds will remain unexplored for the foreseeable future. They'll orbit in obscurity, known only as points of light in telescopes, their characteristics inferred from brightness and color, but never directly observed. There might be worlds out there more geologically active than Pluto, worlds with thicker atmospheres, with more dramatic surface features, with colors we've never seen, with phenomena we haven't predicted. There might be binary systems even more extreme than Pluto-Charon, worlds orbiting so close they're almost touching, or so far apart they barely influence each other. There might be worlds with multiple large moons, creating complex gravitational interactions. There might be worlds with rings, like miniature Saturns composed of ice particles. There might be worlds with subsurface oceans far more extensive than Pluto's, potentially harboring, however unlikely, some form of life we haven't imagined. Worlds where chemical processes create complexity we'd recognize as biology or quasi-biology, or something so alien we wouldn't know how to categorize it. All of this might exist, and we don't know about any of it. The Kuiper Belt is a region of the solar system we've barely begun to explore, where discoveries await anyone with telescopes sensitive enough to detect faint objects or spacecraft capable of reaching them. Planet 9, if it exists, is out there somewhere, a world 5 to 10 times Earth's mass, orbiting in the distant darkness, influencing other objects through gravity, but remaining invisible to our searches so far. Finding it would revolutionize our understanding of the outer solar system. But even if Planet 9 doesn't exist, there are certainly other large worlds waiting to be discovered. Worlds in unusual orbits, worlds at extreme distances, worlds that happen to be in regions of sky we haven't surveyed carefully yet. Every time we discover a new Kuiper Belt object, we expand our understanding of what's possible out there. Each discovery reveals something new about the diversity of small worlds, the range of compositions, the variety of orbital characteristics, and every discovery reminds us how much we still don't know. The Kuiper Belt is vast, millions of cubic AU of space, thinly populated but containing countless objects, most of which we'll never see, never visit, never understand. The worlds we haven't found outnumber the worlds we have found by factors of thousands or millions. They orbit invisibly, patient and indifferent to discovery, waiting for the day when human telescopes or spacecraft might reveal them. Or waiting forever, if we never happen to look in the right direction at the right time with sufficient sensitivity to detect their faint reflected light. Pluto is the flagship, the largest known member, the ambassador for this population. But it's one world among multitudes, representing a diversity we've barely sampled, standing in for thousands of other worlds we haven't met yet. The Kuiper Belt remains the solar system's greatest unexplored region. Not empty space, but a populated realm we've only glimpsed, full of worlds that orbit unseen, waiting for explorers who may never come. Looking at Pluto, studying it, understanding it, appreciating it, changes how we see ourselves and our place in the universe. From Pluto, Earth would be barely visible, a pale blue dot close to the sun, requiring a telescope to see it all, showing no detail, no continents, no clouds, just a faint point of light. Everything humans have ever done, every civilization that's ever existed, every person who's ever lived, all of it contained in that invisible speck. This perspective matters. It's humbling. It reminds us that Earth isn't the center of anything, that we're not particularly special from a cosmic viewpoint, that our world is one small planet among many, orbiting an average star in an unremarkable region of a typical galaxy. The famous pale blue dot photograph taken by Voyager 1 from 4 billion miles away, showing Earth as a tiny pixel suspended in a sunbeam, captured this perspective powerfully. Carl Sagan's meditation on that image remains one of the most profound statements about human significance and insignificance simultaneously. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, on a mote of dust suspended in a sunbeam. From Pluto's distance, Earth would appear even smaller, even more insignificant, and Pluto, itself from Earth, is just a point of light, barely distinguishable from background stars without careful observation. This mutual invisibility is profound. From Pluto, Earth is invisible. From Earth, Pluto is invisible without telescopes, two worlds orbiting the same star, separated by distance so vast that neither can see the other clearly, both insignificant from the other's perspective. And yet both exist. Both have geological complexity, chemical diversity, physical processes. Both have histories stretching back billions of years. Both will persist for billions more years into the future, indifferent to whether anyone observes them. This should change how we think about significance. We tend to equate visibility with importance, to assume that what's prominent must matter more than what's obscure. But Pluto, invisible from Earth without instruments, ignored for most of human history, turned out to be fascinating, complex, scientifically valuable. What else are we missing by assuming that what's distant or small or difficult to see must be unimportant? How many other Plutos are out there, literally or metaphorically, waiting to be discovered and appreciated? The perspective also changes how we think about home. When you look at Earth from Pluto's distance, even hypothetically, since no human will likely ever make that observation directly, it emphasizes how rare and precious our world is. Earth is the only planet we know with life, the only one with liquid water oceans covering most of its surface, the only one with an atmosphere that's breathable, the only one warm enough, wet enough, stable enough to support the kind of complexity that leads to consciousness. Pluto reminds us that most worlds aren't like Earth. Most places in the solar system, and presumably in the universe, are cold, dry, airless, hostile to life as we know it. Worlds like Earth are exceptions, rare configurations of matter that happen to fall within the narrow range of conditions compatible with biology. This should make us value Earth more, not less. Knowing that we live on an unusual world, one of perhaps only a handful of habitable planets in the entire solar system, should inspire us to protect it, to preserve it, to recognize its fragility and uniqueness. But the perspective also reveals our potential. We're a species that can study Pluto from 3 billion miles away. We can send spacecraft across the solar system, can build instruments that reveal worlds we can't see with unaided eyes, can understand physics and chemistry well enough to interpret observations of places no human will ever visit. We're small, confined to one planet, living brief lives measured in decades. But we're also expansive, reaching across light hours with our technology, comprehending timescales of billions of years, understanding processes operating on worlds utterly unlike our own. Pluto gives us this dual perspective. It shows us how small and insignificant we are in the cosmic scale, and simultaneously, it shows us how remarkable our capacity for understanding is, how far our curiosity can reach, how much we can know despite our limitations. This perspective, this ability to hold simultaneously the knowledge of our insignificance and the appreciation of our capability, is perhaps what makes us unique in the universe. Not that we're physically special, but that we can recognize our place in the cosmos, can feel wonder at our smallness, while simultaneously taking pride in our ability to explore and understand. Looking at Pluto from Earth, or imagining looking at Earth from Pluto, creates this perspective. It's a gift that exploration provides. Not just knowledge of other worlds, but a better understanding of our own world and our relationship to the universe we inhabit. From Pluto, Earth is a pale blue dot. From Earth, Pluto is a pale brownish dot. Both are tiny, both are distant. Both are, from certain perspectives, utterly insignificant. And yet both matter. Both are worth studying, worth appreciating, worth caring about. Not because they're central or important in any cosmic sense, but because we're here to witness them, to understand them, to find meaning in their existence and ours. The perspective Pluto gives us is the perspective of honest humility, combined with justified pride. The recognition that we're small but capable, insignificant but conscious, temporary but able to comprehend eternity. And that perspective might be the most valuable thing we gain from exploring distant worlds. Pluto's demotion from planet to dwarf planet in 2006 changed its classification, but paradoxically, it increased its scientific and cultural significance. When Pluto was the 9th planet, it was always the least important planet, the smallest, the most distant, the most poorly understood, the one that barely fit the category. Textbooks mentioned it almost as an afterthought. And finally, Pluto, a small, icy world at the edge of the solar system. Teachers glossed over it because there wasn't much to say. Scientists studied it less than other planets because it was difficult to observe and seemed less scientifically interesting than Jupiter's massive storms or Mars's potential for life. Being a planet wasn't doing Pluto any favors. It was stuck in a category where it was the worst example, constantly compared unfavorably to worlds vastly larger and more prominent. It was the runt, the oddball, the one that didn't quite belong. But reclassification changed everything. Suddenly, Pluto wasn't the worst planet. It was the best dwarf planet, the largest known member of its category, the king of the Kuiper Belt, the prototype for understanding an entire population of worlds that outnumber the traditional planets by thousands. Scientifically, this made Pluto far more important. Instead of being an anomalous planet that contradicted our understanding of planetary formation, it became a key example that helped explain the Kuiper Belt's structure and history. It went from being a problem to being a solution, from contradicting theories to confirming them. The controversy itself generated attention. Before 2006, most people couldn't name all 9 planets or tell you anything about Pluto beyond it's small and far away. But the debate about planetary status put Pluto in headlines worldwide. Suddenly, everyone had opinions about this distant world, whether it deserved planetary status, whether the IAU had made the right decision, whether size mattered or orbital characteristics mattered or historical precedent mattered. This attention persisted through the New Horizons mission. When the spacecraft approached Pluto in 2015, it wasn't just scientists who were excited. It was the general public. People who'd never cared about astronomy suddenly cared about Pluto because of the demotion controversy. They felt invested in this world, wanted to defend it, wanted to see what it really looked like. And when the images arrived, when we saw the heart, the blue skies, the young surfaces, the geological complexity, it felt like vindication. Pluto had been dismissed as unimportant, and it turned out to be one of the most interesting worlds in the outer solar system. The underdog proved its worth. This narrative is powerful. It resonates with people who felt underestimated, dismissed, told they didn't belong or weren't important enough. Pluto became a symbol of the idea that classification systems don't determine worth, that being small doesn't mean being insignificant, that surprises await in places others overlook. Culturally, Pluto's significance grew enormously after demotion. It appeared in cartoons, memes, popular music, fashion. Pluto is a planet became a statement of loyalty, a refusal to accept arbitrary changes, a defense of what people grew up believing. Even people who understood the astronomical reasoning felt emotionally attached to Pluto's planetary status. This cultural prominence is itself significant. Most planetary bodies don't inspire emotional responses. People don't have strong feelings about Makemake or Haumea or even Neptune. But Pluto became personal, became something people cared about beyond its scientific properties. And from a scientific perspective, Pluto's reclassification focused attention on the Kuiper Belt as a region worthy of study. Before Pluto's demotion, the Kuiper Belt was a relatively obscure topic, studied by specialists but not prominent in public discourse. After reclassification, people wanted to know, what is the Kuiper Belt? What other objects are there? Why does this region matter? This increased attention has led to more funding for Kuiper Belt surveys, more proposals for missions to explore these objects, more public interest in the outer solar system. Pluto's changed status catalyzed broader interest in the entire region where it resides. If Pluto had remained the 9th planet, it would probably be less famous today. The New Horizons mission might have received less public attention. The discoveries might have been appreciated by scientists, but not celebrated by the general public. The images might have been filed away in archives rather than becoming viral phenomena. The controversy gave Pluto a story, and humans love stories. We remember stories better than facts, care about narratives more than data. Pluto's story, discovered, celebrated, demoted, defended, explored, vindicated, is compelling in ways that simple planetary classification never could be. This is the paradox. By losing planetary status, Pluto gained significance. By being reclassified to a less prestigious category, it became more prominent, more studied, more loved. By being told it didn't matter as much as we thought, it proved that it mattered more than we imagined. The The changed significance is permanent now. Pluto will always be known as the world that was demoted, the dwarf planet that captured hearts, the small world that proved size doesn't determine worth. That narrative is inseparable from Pluto's identity, part of what makes it meaningful beyond its physical properties. And in that narrative, we see ourselves, our tendency to champion underdogs, our resistance to dismissive categorization, our belief that overlooked things can be valuable, our hope that significance isn't determined by conventional measures. Pluto's changed significance reflects our values as much as it reflects Pluto's actual properties. The ninth planet became the first dwarf planet. And in that transformation, it became more important, not less, more representative, not less, more studied, more loved, more significant in ways no one predicted when the IAU voted in Prague in 2006. Pluto won't complete its first orbit since discovery until 2178, 153 years from now. But there's another cycle that's equally significant, the cycle of human exploration. New Horizons flew past Pluto on July 14, 2015. That moment marked the first time humans had ever seen this world up close, the culmination of 85 years of curiosity since its discovery. When will we return? When will another spacecraft visit Pluto, providing updated observations, showing us how the world has changed, revealing what we missed during that brief first encounter? The honest answer is probably not in the lifetime of anyone reading these words. Consider the timescales. Proposing a mission takes years. Scientists must develop concepts, write proposals, compete for funding. Getting approval takes years more, review processes, budget battles, political negotiations. Building the spacecraft takes 5 to 10 years. The journey takes another 10 to 15 years. So even if a Pluto mission were approved today, which it isn't, it wouldn't arrive until the 2050s at the earliest. More realistically, if a mission is proposed in the 2030s, approved in the 2040s, built in the 2050s, it might arrive in the 2070s. That's 50 plus years from now. People born today would be in their 50s or 60s. Most people currently alive would be elderly or deceased. The scientists who worked on New Horizons would almost all be gone. And there's no guarantee such a mission will be approved at all. Space exploration competes for limited budgets with countless other priorities. Mars sample return, Europa landers, Venus missions, exoplanet studies, Earth science, plus all the non-space priorities like healthcare, infrastructure, education, defense. Pluto, having been visited once, is no longer a top priority. The argument for returning is scientifically compelling. We need long-term observations, seasonal monitoring, repeated measurements, but it's not urgent. Other targets that have never been visited might receive priority over returning to Pluto. So it's entirely possible that the 2015 flyby will remain the only close-up observation of Pluto for 50 years, or 100 years, or longer. Perhaps for the rest of the 21st century, perhaps beyond. This means that everyone currently alive who cares about Pluto, everyone who was excited by New Horizons, everyone who followed the mission, everyone who saw those first images and felt wonder, will probably never see another spacecraft visit this world. The images we have are the images we'll have. The data New Horizons collected is the data we'll analyze for the rest of our lives. The discoveries made in 2015 are the baseline that our generation contributes to Pluto science. Future observations will be made by future people, our children's children, people not yet born, scientists who will build on our work but won't include us in their teams because we'll be gone. This is both sad and appropriate. Exploration is always a multi-generational endeavor. The people who dream of visiting a place aren't usually the ones who arrive. The people who first explore are rarely the ones who conduct detailed studies. The pioneers move on, and successors follow, each generation building on the work of previous ones. We're the generation that first saw Pluto up close. That's our contribution. We're the ones who turned it from a point of light into a real world, who revealed its heart and its haze layers, who discovered its geological activity and atmospheric complexity. Future generations will refine that understanding. They'll observe seasonal changes we can only model. They'll measure heat flow we can only infer. They'll land on the surface and sample the ice directly, conducting analyses we can only dream of. But we won't be there to see it. The return won't happen in our lifetimes. There's something melancholy about that realization. We're living in a special time, the era when Pluto was first explored, when humanity first reached the Kuiper Belt, when we transitioned from imagination to observation. It's a brief moment in the long arc of exploration, and we're fortunate to be alive during it. But it's only the beginning, the full exploration of Pluto, the comprehensive understanding, the long term, monitoring, the detailed surface studies. That work belongs to future centuries, to people we'll never meet, to a time when our contribution will be historical footnote rather than active research. Still, being present for the beginning has value. Being the generation that first saw Pluto clearly, that first understood it was geologically active, that first appreciated its complexity, that's meaningful even if we don't live to see the full arc of exploration. We're passing the torch. Our observations become the baseline. Our discoveries become the foundation. Our excitement becomes the inspiration for future missions that we won't be here to celebrate. The return won't happen in our lifetimes, but knowing that future humans will return eventually, someday, when technology improves and priorities shift and funding becomes available, provides comfort. The work continues. The exploration doesn't end with us. The story of Pluto and humanity spans centuries, and we've contributed our chapter even if we won't read the ones that follow. So we look at the New Horizons images one more time, knowing they might be the best images of Pluto we ever see. We appreciate them fully, study them carefully, share them widely, preserve them diligently. Because these images are our generation's glimpse of Pluto, fleeting, incomplete, but precious for being the first. The next glimpse belongs to another generation. We won't see it, but knowing it will come eventually to people who inherit our curiosity and continue our work. That knowledge connects us across time, makes us part of something larger than our individual lives, ensures that our brief encounter with Pluto contributes to an understanding that will grow long after we're gone. Pluto reminds us that the cosmos saves surprises even at the edge of familiarity, that cold, distant, forgotten places can harbor beauty, complexity, and wonder we never expected to find. In revealing an active, colorful, geologically vibrant world where scientists expected frozen stillness, Pluto teaches us that nature's creativity extends far beyond our expectations, to the very edge of the sun's light and beyond. When Clyde Tombaugh found that faint moving speck in 1930, he discovered more than just a new world. He opened a gateway to an entire region of the solar system we didn't know existed. The Kuiper Belt, with its thousands of frozen worlds, its primordial composition, its preserved record of solar system formation. For 85 years, Pluto was mysterious, a point of light that refused to reveal its secrets to telescopes, that existed in our imagination as much as in reality, that meant different things to different people, but remained fundamentally unknown. Then New Horizons arrived, and in one extraordinary day, July 14, 2015, Pluto transformed from abstraction to place. The images arrived. The heart appeared. The blue skies emerged. The young surfaces revealed themselves. And we understood, suddenly and viscerally, that we'd been wrong about what this world was. It wasn't the dead, boring, frozen ball we expected. It was alive, geologically speaking, with convecting ice plains, flowing glaciers, possible volcanoes, dune fields, and complexity that challenged every assumption we'd made. This is Pluto's greatest gift, the reminder that wonder waits everywhere, that beauty exists in unexpected places, that nature doesn't organize itself for our convenience, but constantly surprises us when we look closely enough. For 9.5 years, New Horizons journeyed through the darkness, traveling 3 billion miles, crossing the entire solar system to reach the small world at the edge. That journey, that commitment of time, money, effort, and human ingenuity was rewarded with discoveries that exceeded every hope. Pluto could have been boring. It could have confirmed our expectations, shown us ancient cratered terrain and nothing more, validated our assumptions about small dead worlds. That would have been scientifically valuable but not emotionally moving. Instead, Pluto astonished us. It showed us a frozen heart that became a global icon. It showed us blue skies that reminded us of home despite being made of completely different chemistry. It showed us surfaces younger than humanity, proving that worlds we thought were finished can still be changing, still be active, still be creating new landscapes. And in doing so, Pluto taught us humility, the recognition that our models are incomplete, our predictions are often wrong, our understanding is always provisional. It taught us that exploration matters precisely because it challenges our assumptions, forces us to expand our thinking, reveals truths we couldn't have discovered through theory alone. This lesson extends beyond Pluto. It applies to everywhere we haven't looked yet, to every world we haven't explored, to every phenomenon we haven't observed. If Pluto, small, distant, supposedly simple, can surprise us this much, what other surprises await? What will we find on Europa when we drill through the ice and sample the ocean beneath? What exists on Enceladus, where geysers spray material into space from a subsurface sea? What landscapes cover Titan, where methane rain falls from organic haze layers onto seas of liquid hydrocarbons? What will we discover in other star systems when we finally develop technology to visit exoplanets orbiting distant suns? What forms of geology, what atmospheric chemistry, what possibilities for life exist on worlds we can currently only imagine? Pluto is a promise that exploration rewards curiosity, that the unknown is worth investigating, that wonder waits for those willing to look. It's proof that small investments in understanding can yield enormous returns in knowledge and inspiration. It's evidence that beauty and complexity pervade the universe, appearing in places we'd otherwise dismiss as unimportant. We are the species that sent spacecraft to the edge of the solar system to study a world most people had never heard of. We are the beings who looked at a faint point of light and said, "I want to know what that is." We are the explorers who spent decades and billions of dollars to satisfy curiosity about a place no practical consideration suggests we need to understand. And we were rewarded, not with resources to exploit or land to colonize, but with knowledge, with beauty, with the profound satisfaction of understanding something we didn't understand before. That's what Pluto represents, the human impulse to explore, not for profit, but for understanding, to reach beyond the comfortable and familiar into the distant and difficult, to refuse to accept that anything in the universe is unworthy of attention and study. Pluto teaches us that wonder exists at the edge, that the places others dismiss can be the places most worth exploring, that size doesn't determine significance, proximity doesn't determine value, convenience doesn't determine merit. It teaches us to look at the forgotten, the overlooked, the distant and small, to give them attention, to study them carefully, to appreciate them fully. Because if we've learned anything from Pluto, it's that the things we think we can ignore often turn out to be the things most worth knowing. At the edge of the solar system, where sunlight fades to twilight and warmth becomes memory, there is a small frozen world with a heart on its surface and mysteries in its interior. It spins slowly through the darkness, completing its patient orbit, indifferent to human attention, but forever changed in human consciousness by our brief encounter. We saw it. We understood a little. We fell in love with it. And in doing so, we proved that wonder isn't limited by distance, that beauty isn't diminished by cold, that the edges of the known world are exactly where we should look when we want to be surprised, to be humbled, to be reminded of how much remains to be discovered. Pluto is wonder frozen in ice, complexity preserved at the boundary of the known, beauty waiting 3 billion miles away for anyone curious enough to look, and having looked, having seen, having understood even a fraction of what this world truly is, we are forever changed, expanded in our conception of what's possible, humbled in our assumptions about what's interesting, grateful that we live in a universe where worlds like Pluto exist. The edge of familiarity is where wonder lives, and Pluto, small and distant and supposedly insignificant, proves that truth with every convection cell, every blue haze layer, every frozen heartbeat that marks the rhythm of a world that refused to be boring. Closing. And now, as our journey through these 101 facts comes to an end, Pluto continues its patient orbit, indifferent to our fascination, unchanged by our attention, eternally circling in the cold darkness at the edge of the sun's light. In 248 years, it will return to where Clyde Tombaugh found it. In 500,000 years, the nitrogen ice in Sputnik Planitia will complete another convection cycle. In billions of years, the sun will swell and die, and Pluto will witness transformations we can only imagine. But for now, for this moment, Pluto is the world we discovered, explored, and learned to love. The frozen frontier that taught us to expect wonder everywhere, even at the very edge of the known. Sleep well, knowing that far beyond the warmth of our world, beyond Neptune's orbit, beyond the boundary of the familiar, there orbits a small world with a heart, waiting patiently in the darkness, holding secrets we've only begun to uncover, reminding us that the universe is vast and full of wonders, and that no place, however distant or cold, is beyond the reach of human curiosity. Good night.